Hi everyone. Let's make 5 more minutes for remaining participant to come. Can we- yeah.
Delayed federation. Oh, okay. So that's why I told him to. Yeah, yeah. Excellent. You're going to talk about that? Yeah. You did some topological reaction with Azaidan. That's right. Yeah, yeah. That's giving you right. Solid polymers, which is after delayed federation. That's giving some theoretical statistics. Oh, okay. I'm looking forward to hearing about that. Good to see you. Yeah.
Good morning to everyone. Uh, First of all, I would like to thank the organizers for making me part of this wonderful conference. I and Rishika are chairing this session called as Crystals That Move and Deform. As you can see here, one crystal is moving this side, other crystal is deforming that way. Before I start inviting the speakers to deliver their lectures, as a tradition we have started in previous ICOS in New York, I would like to briefly introduce the topic to the audience. Here the topic is crystals that move and deform. Chemistry is a science of changing things in terms of chemical constituent modification by using reactions. These reactions involve reactants, solvents, and conditions. This has been beautifully established by the world of molecular machines, molecular switches, and molecular rotors. Of course, this cannot be used for the static objects such as crystals. Why? Crystals are known to be the rigid bodies, and also they are called as dead bodies of the crystals. Okay, if a molecule becomes a crystal, if a molecule becomes a crystal, that's it, it can't do anything. For example, if you take any other molecule other than rotors, if it has a triphenyl group, tertiary butyl group, or trifluoro group, it can perform some kind of rotation or motion. And this can be easily detectable in both solution and solid state. But we cannot anticipate more than that when it comes to crystal because, as I said earlier, crystal is a dead body. And also, crystal itself gives a clear images of hard, transparent, and well-established faces. This is what we all used to think about crystals till before few years. Later, when we started working in dynamic crystal, we have to change our perception toward the understanding of these crystal rules. I would like to present some characteristic exceptions for these crystals. There are so many characteristic exceptions are there, which I will be presenting two here. The first one is regular shape. When it comes to regular shape, nowadays you can find so many crystals with irregular shapes. All these are single crystals. You can see candlelight from Bolivia, coccolith crystals, sea urchins which are based on calcite minerals, yo-yo-like single crystals, and perfectly hexagonal shaped single crystals, brain-like texture containing egg-shaped crystals, perfect ring-shaped crystals. All these are called single crystals, but with irregular shapes. When you look at the other one, hard and brittle, but nowadays you can find super soft materials, also super hard materials. I don't want to go into the details in this case. Last few years, we have seen several dynamic effects with several different systems. We have not imagined that all these are possible with crystals. Why? Because all these stunts are only possible in cartoon show, but not in a chemistry lab. As you can see here, jumping, popping, twisting, bending, curling, walking, crawling, and rolling. These are the dynamic effects. But all these are based on single crystals, and mostly they are all based on organic-based materials, except this one. Does anybody can say that, what is this material? This is my favorite, ice crystals. So apart from these routine dynamic crystals, we do have some very peculiar behaviors which I would like to show here. As you can see here in the next slide, this is peeling, where when you irradiate a crystal with a light, the top layer gets peeled and the peeled layer eventually it becomes coiled. This is shape transformation, this is shape memory, this is self-healing. This is the first example in self-healing of organic crystals. Later there were very few examples which are mainly based on this mechanism. And this is mechanically induced jumping, crystal swimmers, enormous reversible expansion and contraction in thermosalient solids, and vivid color changes in mertensitic transitions. All these materials are, I would say, the dynamic effects have been serendipitously discovered, not by design. And these are discovered by mostly organic solid-state chemists who are working on dynamic crystals. For now, I would like to say them as dynamic organic solid-state chemists. When we expose these dynamic crystals to external stimuli, such as heat, light, mechanical, there are two more stimuli is there. One is chemical vapor, other one is humidity, which I don't want to discuss because they are still debatable. We are waiting for more and more stimuli to add on. So basically two types of mechanisms are possible. One is relaxation with fragmentation and reshaping. The other one is relaxation with mechanical reconfiguration. When it comes to fragmentation and reshaping, basically these things are possible: jumping, fragmentation, shape change, splintering, expansion or contraction during the phase transition. On the other hand, relaxation with mechanical configuration goes with two types. One is plastic deformation, other one is elastic deformation. Bending, twisting, coiling, all these three you can see in both deformation, both plastic and elastic deformations. Superplasticity is actually belongs to plastic deformation. Of course, there is another term called ferroelasticity that is also belongs to plastic deformation, but I have not included. Can anybody say why I did not include? Obviously, there is no space. Okay. And superelasticity is actually belongs to elastic deformation. I would like to present the timeline discoveries in this dynamic crystal world. I know you cannot read anything. This is massively filled up. But I would like to highlight a few points here. The first one, the stress-induced phase transition was reported in 1975 by Professor William Jones. Later, metencytic transition in biological process were reported in 1982. This is very interesting work from Irie on the beginning of photomechanical crystal in 2001. This is plastic crystals which were published in 2005 from Professor Desiraju and Mallareddy. This is very interesting paper published from Christopher Bardeen and Rabi Salkaisi on photomechanical crystals with modified habit behavior. In 2010, this is the full evaluation of thermosalient solid, which is known as, oxytropium bromide from Professor Bernstein and Professor Namov. And this is very interesting example. Of course, this has been done by me. And also, this is on self-shape memory, and in 2016, it is from Patrick. This is on self-healing behavior in organic crystals. And I cannot exactly say like who discovered first and associate the claim to an individual. Why? In literature, there are so many examples. They were overlooked due to the experimental limitations, methodology to identify the phenomena, and terminology to describe the phenomena. I'm sure if you go to the literature, you will find plenty of compounds. They are buried under the literature just because they have used some other terminology where we cannot find them. For example, if you look at this particular molecule, this is known as terephthalic acid. This has a phase transition. But when you do normal DSC experiment, we actually compress the DSC crucible and we do the experiment. When you compress the crucible, you see there is no signal. But you invert the lid, you do the phase transition of DSC experiments, you see there is a nice sawtooth behavior. This is one such example. And another example which I would like to show here is almost who are working on dynamic crystal, they know that this tetrabromobenzene is a thermosalient solid. From 2000 later, in 2013, it was fully evaluated. But who knows about this paper? When was it published? This is a phase transition they have done on this tetrabromobenzene. This was actually published in 1956. The thing is that they have reported the phase transition, but they did not look at under the microscope what is happening to the crystals. So who knows? There could be so many examples. And this was super buried under the literature. How many times it was accessible, you can also see it. And when it comes to thermally responsive materials and thermosalient solid, the first initial jumping behavior, the word jumping has been used in this particular paper which describes on manganese, cobalt, germanium. Later, another example, even though it was not mentioned as a jumping, but this is another thermosalient solid in 1983 from Peggy-Etter and all. And in this paper, this is a carbohydrate derivative, this myo-inositol derivative. In this, Jig and Jig reported this thermosalient behavior in this particular compound in 1987. In 1991, this perhydropyrin also reported for its thermosalient behavior. In 1994, this was claimed to be the third compound, but in fact, it is not true. This was from Professor Bernstein and Professor Namo. Later, it was fully explored in 2010. So nowadays, we are seeing so many thermosalient solid every month. Every month, where there is one new compound is getting added. What is important is, we are seeing this thermosalient phenomena or this thermally responsive behavior from smallest molecule possible to the complex molecules. You can see here, this is a tetrabromobenzene. This compound, this 4-amino benzonitrile from Len Barber's group. This is a gold complex from Hijimi et al. All these phenomena are showing the same thing. And I would like to show one very interesting case. This is an amphidynamic crystal. This has both rotor and stator. Apart from its rotation, this has a thermosalient phase transition. The others have been very successful in rationalizing the phase-specific behavior with structural dynamics. And what is important is, after publication of this paper, Professor Stoddart, who is a Nobel laureate in 2016 chemistry, has published a spotlight article on this particular work, highlighting the importance of dynamic crystals in designing artificial molecular machines. We as dynamic crystals, we are a very small community. Getting recognition from all over the world, it is really appreciable. And this is also shape memory organic crystals. In the literature, there is only one compound is available. This is known as a shape memory material, which is very, very similar to titanium nickel alloy. If you take any stride crystal, you define a shape. For example, you bend the crystal, you heat it, it goes to stride shape. When you cool it, it has to come back to its predefined shape, which is a bent shape. So this is only one compound which is showing similar to the titanium nickel alloy. I can see in the literature there are so many reports, they are claiming that they have obtained shape memory materials, but they are not shape memory materials, they are just shape transformative materials. Others have proposed the mechanism and they have also proved the mechanism. If you look at the other behavior from the same material, this is terephthalic acid crystals. These are known for its mechanosalience behavior. Mechanosalient, okay, these crystals are at room temperature, they are metastable. When you touch these metastable crystals, they actually jump. Only one example available. Of course, there are few unpublished works are there. I'm sorry I couldn't show the structures here. Basically, it is from me. And apart from reporting these thermosalient crystals or thermosalient phenomena, what else can be done? Very few groups were successful in quantifying the force generated by these thermosalient crystals during the phase transition by using force sensor setup here. Here you can see the cantilever-based method here. This is a force sensor setup. After they perform these experiments, they have obtained the performance indices, and these performance indices were rationalized with the existing known actuator classes. This is force sensor setup. When you go to the other one, this is a steel ball setup where the people have used it to quantify the force. And also in this case, they have used these PDMS pillars. Again, they have rationalized the performance indices with the known existing actuator classes. So, as I said earlier, there are so many compounds are there in the literature which are responsive towards thermal and light, and they are known as thermosalient, thermally responsive materials, photosalient, photomechanically responsive material, maybe one or two mechanosalient materials. But this list we prepared in 2015, new list will be coming very soon from our group. So, what is the future? Future is ideas, and I don't want to share the ideas. So, if you look at here, this is the recently published work where they have used this photoresponsive material, and this has been used for photocarving method, cold photocarving methods. In other case, same photoresponsive material used for crystal walkers. In this case, they have used for crystal swimmers. Upon irradiation of the light, crystals can be swimming in a liquid medium. In this case, this particular example is not a crystal. This is actually a hybrid material. But the material which they have used in this is a photoresponsive material. If you look at this particular example, this is actually a photoresponsive material, but they have used two different types of photoresponsive material. One bends towards the light, other bends away from the light. When they put it together, they can actually use lift and maneuver the weights. In other case, as I said earlier, these thermosalient materials are reversible. So this reversibility can be used to create some kind of electrical fuses. This is from Pansenamo group, where they have used this thermosalient material for creating electrical fuses. And this is from Gasson-Smith's group, and they have also used pretty much the same idea they have used. These are photoresponsive materials. They tried to use these materials for drug delivery. Of course, they have not used drug delivery in this case. They have used a simple dye. Upon irradiation, it can release the dye molecule. This is a metancitic transition thermosalient containing compound. This can be used in flexible electronics. These are basically they have used for a flexible electronics. In this case, they have used for a flexible optoelectronics because these are optically active compounds. I mean, optically active in the sense like they are showing some response toward the light. Yeah. So these are highly elastic in nature and also highly conductive in nature. They can be used for flexible electronics. when it comes to superelasticity and superplasticity, ferroelasticity, these molecules can be used for controlled gas flow, because when we change the domains, we can actually control the change in the gas flow. This particular example, it shows enormous expansion and contraction towards the phase transition. I mean, when you heat this sample, it can expand and it can contract. But the interesting thing is, other than this thermal expansion behavior, this material has other different properties when it comes to conductivity and ferroelectricity. Not just the thermally responsive material, this material can be used for multifunctional materials. So there is one more hot area is currently going. This is known as waveguides. Nowadays, I can see many people, they can shine light at one end and show light at other end. They say this is waveguide. But this does not work in a real world application. If you have to use any molecule in telecommunication device, this has to be tested with the telecommunication radiation, which is infrared or far infrared. There are very few examples in the literature which they actually shown the transparency in the telecommunication region, where you can use these crystals in real world application, not these molecules. So finally, what is the outlook of these dynamic crystals? I want to give a disclaimer. My opinions are personal and does not reflect my group. So I have little bit fantasy towards about these movies. Okay, we are not targeting any group. A group in the sense we are not challenging any pre-existing areas such as polymers, metals, and composite materials. We, as a dynamic crystals, wanted to work in the areas where our counterparts have clear disadvantages, and we wanted to create futuristic functional materials. With this, I would like to conclude my introductory to this session, and now I invite the speakers to deliver their respective talks. And before I invite the speakers, I have an announcement for the audience. Please ask questions at the end of every talk. If you don't ask, I have to ask questions which I prepared after taking 2 vodka shots. I don't want to test which is good, me or my vodka shots. Okay, let's make a deal. Every first question gets a surprising gift from me for every speaker. Thank you. So now I invite Professor Mariana Ekovic from University of Jabrach to deliver her lecture. Please.
So thank you for the introduction, and before I walk you through a maze of crystal adaptility, which can still amaze us, let me just first thank the organizers for the invitation and for this slot, but most of all, let me thank Panche for inviting us all and organizing the conference in such a wonderful and lovely place, the town of Ohrid. So thank you, Panche. So, something is wrong. I cannot move the presentation. I mean, I can. No, no, I can move it here. It doesn't. Maybe we can. Maybe. No, no, it's different.
You push 2 times here.
So my apologies for this, and I can ensure that this is my laptop, from which I already ran the presentation several times, but anyway. So thank you, Pancho, for everything, and my apologies once more. So let's get back to crystals. For long, we've all been aware that crystals actually do not behave according to book, which means that the crystals are brittle and stationary objects which are very fragile and can be easily broken upon application of even smallest mechanical force. But on the contrary, during the last several decades, we were witnessing a growing number of examples where crystals behave completely differently. They were able to move, crawl, jump, flex, fragment, peel off, or explode. And most of those crystalline mobilities were actually responses or adaptability of crystals to a variety of external stimuli other than pure mechanical force. Typically, that was heat or irradiation. But there's a logical question. Why do crystals move? Apparently, they have much more in common with us humans than we previously thought. So, for example, if we are overly exposed to external stimuli, stress has been accumulated. And upon accumulation, it needs to be released. So there are typically two paths of stress relaxation, the abrupt one, and the other one, slow, continuous, and ideally controllable. So approximately the same is with crystals. Upon exposure to external stimuli, crystals' energy is being absorbed. It consequently causes slight structural changes, and when these are accumulated, they trigger mechanical responses. And the stress that is being accumulated during those processes can be, again, dissipated and released via two paths. Slow, and then we have bending or twisting or similar, typically or usually reversible processes, or via abrupt and spontaneous fast path when we observe fracture, jumping, creeping, or other typically irreversible processes. But more on that topic, you will hear, I'm sure, later during this conference from the experts in the field. And from now on, I will solely focus on mechanical force as an external stimulus that has been most recently identified as being capable of also inducing flexibility to single crystalline materials. And typically, two responses were found for mechanical force as a stimulus: plasticity and elasticity. What means that if the force is induced on a crystal, crystals deformed, but in case of plasticity, upon a removal of the force, crystals remains permanently deformed, while in the case of elastic response, they are capable of regaining their original shape. And those cycles can be repeated several or many times, depending on the sample. And while both responses were observed on crystals of specific morphology, that means needle-like elongated crystals, the question which remains is which structural prerequisites are required for those two responses to be targeted and deliberately delivered. In the case of plastic materials, in most of our samples, actually those so-called slip lanes are present, what means 2D regions, which allows which allow movement of neighboring domains over each other, similarly to that what we have in graphite or in mica crystals. But still, there is a question if these slip planes are really necessary to induce plasticity to single crystalline samples. On the other hand, for elastically bendable crystals, the situation is not as clear as for plasticity, since those crystalline samples in the literature are quite rare, and the conclusions are apparently made on substantially small data sets. And it can be depicted on the next two samples when, for example, we have isotropic interactions and interlocking claimed as crucial for organic molecular crystals to induce elasticity, while for metal organic crystals, something different was claimed and reported, and that was anisotropic interactions and no interlocking. So that was the point and the topic where we focused our attention and focused our research to try to decouple those two impacts and influences on crystalline mobility output. So we focused on slightly different materials. We opted for coordination polymers, and that is slightly different. It is still organic, but with metal-containing systems. So I would like again thank Pancho for allowing me to talk on metal-organic systems at this well-established conference on organic solid state. So why we opted for coordination polymers in the case for the reason because in this case we were able to retain the structural characteristics that were observed in both system organic and organic, zero-dimensional organic. For construction and building our building units, we opted for cadmium halides as their regularly deliver coordination polymers, but also as they allow us to control the distance between two knots within the structural spine by exchanging halide anions. Also, the coordination, octahedral coordination geometry of cadmium cation allows for attachment of supramolecular anchoring points via exchanging substituents on the organic ligand, but nonetheless, halide anions are known as good hydrogen bond donors and acceptors, and in this way they allows for cross-packing control, at least in certain directions. So in this way, we constructed, let's say, ideal model system for exploring structure prerequisites by exchanging just one tiny slight difference from one structure to the another. And ideally, we will be able to deliver isostructure compounds and test mechanical output and try to reduce and get to the point what makes the difference. So I will present you 4 examples where we just exchanged the supramolecular links within the group and mapped out the outcome of mechanical responsibility. So for the first example, we opted for halopyrazines, 3 halopyrazines, chloride, bromide, and iodide, and we combined them with 3 halides, and finally we obtained 7 isostructural coordination polymers. And then we started with testing mechanical output, and that was performed in oily medium to protect our samples, and experiment was kind of modified 3-point bending. So we, for the first time, observed difference in elasticity for the group of isostructural compounds. We were able to categorize our crystals, our materials, into 3 groups. In the first one, we had really slight elasticity, while further on, we observed modest elasticity and intensively elastic crystals. We had 3 of that kind. What was interesting, that we didn't observe any perceivable difference when the force was applied on 2 different bending phases. So to rationalize this, we went back to crystal packing and observed the arrangement of molecular as well as supramolecular features along those 2 directions of the force application. So here you can see the packing as looking from the bottom of the crystal, where each molecule represents the whole polymeric chain, and those lines represent the crystal faces perpendicular to the screen. And what we got, that we actually really do have the identical crystal packing along those 2 directions, which was apparently responsible for the same mechanical output. Not to stay just or leave with just visual inspection, we quantified the results, and what we've got, the numbers actually confirmed the bending strength values, confirmed the visual observation, and we really got 3 distinct groups of mechanical output. To rationalize those, as we had 7 isostructural compounds with 3 distinctly different outcomes, we were back to crystal packing. And what we observed, that while halogen bonds were persistent in all 3 groups of compounds running in this direction, it was actually a CHN hydrogen bond toward this pyrazine nitrogen atom, which made a difference. It was the most influential and the most bendable crystal, while the least influential in almost inelastic materials. So we clearly show that intermolecular interactions are those which made the difference in this group of compounds. So we moved forward.
What is the thickness
of the crystals? Yes, approximately 20-30 microns. So we moved forward and tried to get rid of this link, which was the weakest link in the crystal structure and which made a difference, by exchanging pyrazines with a pyridine core. And again, repeated the same set of experiment, but here we've got all 9 compounds separated into 2 groups of isostructural materials. So let's first focus on the group of 7. They developed equal 2 sets of phases of equal dimensions approximately, and then again we applied the force on both. In both directions we observed crystal flexibility, and what categorized them as 2D responsive. Apparently again no perceptible difference in mechanical output along those 2 directions. But what was really surprising this time, we've got a whole range of mechanical responses, starting from plastic to slightly elastic, via something, let's say, new. Again, we got 3 groups of distinct behavior, and within each group you can see the representative. While in the first case, at least at the first glance, we've got typical plasticity. In the second group, which we called elastic to plastic behavior, you can see that the crystal at the beginning was properly elastic, while later on started to be plastic, and in the end, it was broken, presenting typical brittle breakage. In the last group, there was no surprises. That was slight elastic behavior, similar to that what we got in the first example. But if we took a closer attention just to plasticity, we've got again a range of different behavior. While here you can see the representative from the previous slide, and compare the two materials 1 and 3 with this behavior, you can see that the first example was really extensively pliable. The crystals were so soft that it was very difficult even to take them out of a test tube or to mount them on a holder to collect the data and to determine the structure. While in the last case, you can see that the crystals are still slightly elastic, at least at the beginning, but later on they perform, let's say, properly plastically. But what was the difference between this crystal and those which we termed as elastic to plastic was that the crystal didn't break in the end, but instead behaved properly plastic to the end. Another thing which we noticed, but again, getting back to crystals and paying very attention to every detail in the crystalline behavior, we thought at the beginning as if the crystal is flowing actually over the metal tips. So to prove that, we slightly adjusted our experiments to resemble so-called 5-point bending, in a way just to add 2 additional supporters. In this way, we made a wavy path for crystal to travel and performed the experiment in a way just to pull the crystal instead of pushing them. And what we've got, that crystals immediately straighten out as they were leaving metal supporters. And that was observed in all 3 cases, but it was the most easily observable on that sample. The process actually resembled the straightening of the metal wire in a typical straightening process when it is moved through the 5 supporters. In addition to that, again, if we pay even closer attention to those samples, it seemed as if our crystals were slightly elongating during those, let's say, straightening process. To prove that, we again adjusted slightly our experiments in the way to add additional supporters and to mount the crystal with the ends fixed. In this way, we eliminated any impact of the medium, as well as crystal surface friction, and apply the force perpendicular to the crystal. In all 3 cases, we found the crystals of approximately the same length and thickness, and applied the force in a completely controlled fashion by moving the impactor in regular increments of 15 microns and at a constant velocity of 100 microns per second. And in the first 2 cases, we can clearly see that crystals were slightly elongated before they cracked. In those 2 cases, metal impactor traveled a path approximately 80 to 100 microns. While in the case of compound 1, we've observed something different. The impactor was traveling and traveling and traveling before we observed a proper cracking of the crystal, which ended up with fiber ends. While in the first two cases, actually, crystals displayed typical, let's say, brittle breakage. To emphasize the effect, we took a thicker crystal and repeated the experiment. So what we can see here, if we look closely, as if polymeric domains within the crystals are moving over each other. And that is the feature that causes actually elongation of our crystal. So to prove that, we performed microfocus single crystal X-ray experiment on both straight and bent crystal. To bend the crystal, we used, again, 3-point bending procedure. Bend the crystal in the U-turn shape, and then mount it on a metal needle. We examined the crystal in several points. At the point of maximal curvature, we didn't observe any substantial broadening of the Bragg peaks, no changes of the unit cell parameters as well. So we had approximately the same diffraction image as with a straight original crystal, while when we examined crystal at lateral points, we observed pronounced azimuthal elongation of the Bragg peaks, so-called asterism, which proved existence of smaller domains in the crystal itself. And as we moved from the point of maximum curvature to the end of the crystal, this azimuthal elongation of the Bragg peaks was substantial and substantial. So what we did more is to, we performed the AFM experiment and retrieved Young modulus, and it was surprisingly in a good correlation with the mechanical output we observed. Also, we examined surfaces and prior and after bending. And after bending, we noticed ridges of approximately 0.2 microns, which were parallel to crystal faces, and those ridges were mostly displayed at the kink of the crystal. So after that, we went back to the two remaining compounds and examined their mechanical output. Here, crystal displayed different bending phases, and we applied the force on both. Firstly, on the smaller phase, where crystal was placed on the larger one, and here the crystals were typically brittle, while on applying the force on the larger crystal phase, while crystal was standing, let's say, on the very tiny phase, we observed different mechanical outputs. While in this case we had elasticity, here we had typically plasticity of our samples. So that categorized the crystals as 1D responsive. And that was something that was that far typically observed on the crystal. That if you apply the force on one crystal phase, it bends, while you apply the force on the another set of crystal phases, it cracks. So let's say, apart from different output, we didn't have nothing spectacular with those two samples. So it can, I think that with this second example, we properly show that supramolecular interactions are again crucial and critical for inducing different mechanical output of crystalline materials. So then we moved to the third example by exchanging halides for cyano group in position 3 and 4. Here we had 6 samples with quite a difference in mechanical responses, while 3 and 6 were typically brittle and as such ruled out of further experimentation. Crystal 1 was behaving similarly to the first group of compounds. It displayed similar crystal phases, and it was 2D, consequently 2D isotropic. In this case, it was isotropic, elastically isotropic, with a bending strain of approximately 1%. While samples 2, 4, and 5 were almost identical in crystal packing, and they displayed 2 sets of crystal phases, and for the first time we observed anisotropic responses. No matter what the response was, elastic or elastic to plastic, in both cases we've got responsive crystals no matter on which set of crystal phases the force was exerted. Of course, if we try to bend the crystal over the larger crystal phases, we've got a smaller value for bending strain, but if we apply the force on the other set of crystal phases, we've managed to bend the crystal substantially. And the same was here with elastic to plastic response. And again, we can, let's say, accuse supramolecular interactions for such a difference in mechanical behavior. And yes, of course, we've been able to determine the at least unit cell parameters of our structures at the 2 points and inner and outer arc of the crystal, and we've got substantially different one parameter of the unit cell, what means that we've got elongation of the cadmium-cadmium distances at the outer arc and the contraction of those at the inner arc of our sample. In addition to that, we've got to the fourth example, where we pose the question if we can improve elastic extent of almost inelastic material. So we've got back to crystals from the very beginning of the presentation. This was the crystal which displayed the almost inelastic behavior, and we opted for improving this link, the weakest link in the structure. So we opted for co-crystallization as it proved very sufficient in improving a variety of other properties, and we ground our starting samples, checked it by powder X-ray, and finally we've got the structure with co-formers placed where we wanted. Actually, we've got the layers of parent polymer and co-former, which we selected, and in this way we really got the link which was missing in the starting structure. After that, yes, what was interesting here, we have got a new morphology, but let's get back to another sample. We took, to prove the process, we took another co-former, again with electron withdrawing groups, to make those hydrogen atoms as acidic as possible, and again got the same result. The layers of co-former, which helped linking to layers of the parent structure. So in the end, we tested the mechanical output in those two cases. And what we've got, we calculated bending strain, and starting from 0.4, we've got slight improvement here to approximately 6, slightly more when the force was applied on the larger crystal face, but in case of the cyanobenzene, we've got substantial improvement of elasticity. What means, if we get back to the crystal structures and compare the link, which was identified as the weakest link in the structure of the parent and the resulting structures, we really had surprisingly good correlation of the mechanical output and the length of the weakest link. So with that, I think we clearly demonstrated the importance of intermolecular interactions in gendering crystals with both range of different mechanical responses, as well as the extent of those. Also, we've seen that mechanical properties of crystals may resemble, let's say, analogous properties of softer materials to a substantially larger extent than was previously anticipated. And I think that maybe we as a community are at a point that we might probably slightly change the narrative in our books, as we are aware that crystals do not behave as it is written in the book, and as we are teaching kids and community as a whole, so maybe we can think about that. And with that, I would like to conclude and to acknowledge the team members, especially Matea Pisacic and Ozana Mishura, who made most of the work, financing, and to all of you for your kind attention.
Thank you, Professor Mariana, for your wonderful presentation. Now floor is open for question and answers.
Hi, I'm Hema from Weizmann Institute of Science. It's nice talk. So I never worked with dynamic crystals, so I am kind of curious to know regarding this plastic deformation. So I want to know two aspects. One is, when there is this permanent deformation, is there a chance that you may develop some amorphous region also along with this crystalline nature?
Probably there are amorphous regions. If you, let's say, ruin your crystal, then probably there are certain points in the crystal which are amorphous, but what we've got confirmation that we still do have substantially smaller domains present in the crystal.
So if it is converting a part of it to amorphous region, so you may be missing some vital information. So is there a chance to get that information?
Well, it probably depends on the sample. You know, and if the crystal is ruined and you have these very tiny fibers in the end, I don't see at the moment at least potential of using that kind of smashed crystal, but maybe we can extract those small domains and use that for something else.
Hello, Mariana. Tell me, are all of your measurements of elasticity done at room temperature?
Sorry?
Are all the
yes,
observations?
okay. Yes, they were made at room temperature. We also tried to reduce the temperature to let's say, 100 Ks. And what we've got, that the crystals got slightly more rigid.
So there is a temperature effect.
Yes, there is.
But the structure's not changing. And I wonder, do you see anything like a glass transition or some kind of effect in the heat capacity?
No,
with temperature?
we didn't notice that.
No.
No.
Okay, right. And it's okay. Thank you very much.
University of Leeds, a lovely talk. Thank you. You talked a lot about plastic deformation, but when we go back to the history of ICOS, we think of plastic crystals quite a lot. And the first thing that comes to mind is defects, lattice defects. And I was wondering if you have a view that some of the deformations you have, are they plastic as we understand plastic deformations by the movement of dislocations as the, if you like, the activation energy of it, or are they pure slip motion involving no creation of lattice defects?
At the moment, I cannot completely answer your question, as we have some other experiments on MOVE, with which we are, let's say, examining the facts in the crystals. As soon as we have final results on that, we'll try to get out with this.
Yeah, so it might suggest some electron microscopy of the defective materials might resolve what's happening at sort of the lattice imaging state of it.
Okay, yeah, thank you.
Can I? So maybe in continuation to what you were asked, let's assume the sliding of two sheets. So the question is whether when you leave it, like plastic deformation, do they land on specific locations such that you still have the third dimension ordering? Or it might be in the XRD data, but I didn't manage to
Yes,
see.
we've managed to get the same unit cell parameters even at the lateral part of the
In plane or also out of plane? Because this is
in all directions.
Ah, really?
Yeah.
Okay.
So in all directions. So it means that we have this.
So this may be the clue for what actually happens, because you slide them, there is no much energy for the sliding, but then it lands in the same ordering.
Yes, that's apparently what is happening, but we'll study that.
Yeah, over here. Alexei Tivansky from University of Iowa. Really nice talk. I was curious if you control the velocity when you were bending the crystals, and whether or not, if you did you try to do it at different velocities? Because I suspect that you can affect the stress or strain relaxation mechanism that way, and perhaps even what you define as flexible versus plastic may be different. Thank you.
Yes, we have a possibility to control the velocity, and of course, if you hit the crystal much strongly and to move this impactor at a higher speed or velocity, then of course the deformations are different. You can observe earlier the breakage, and etc. What means that the stress caused by the deformation can be accumulated within the crystal for a longer period if the force is smaller.
You compare different crystals, you just fix the velocity.
Yes, the same velocity.
Any other questions?
Alexander Tsvetkovsky from Goce University in Macedonia. I wish to ask you whether the nature of halogen atoms in terms of heaviness of atomic radius, have you perceived any correlation between heaviness of the atom, halogen atom, and the mechanical properties, actually how structure influences the properties?
It apparently is not, let's say, the heaviness of the halogen atoms, but the polarizability of this one, which causes halogen bonds to be much stronger. And what was observed so far, halogen bonds were very supportive in our crystals, But if we exchange the halide anions, in cases of cadmium iodides, typically crystals were not as responsive as in other two cases with chlorides and bromides. So that was what we managed to map out so far.
So can we take one last question? Okay, well, I have one question, okay. So you can judge whether it is a stupid question or not. So what is exactly happening in the bent section when you bend the crystal with respect to the crystal lattice?
You think about elastical bendable crystals?
Both elastic
Both.
or plastic.
So at one slide, I showed that we managed to get the information what's going inside. We've got elongation of the polymeric chains at the outer arc of the crystal, and the shortening of this, contraction of the polymeric chains at the inner side of the crystal. And for plasticity, it is not as clear as it is here. It depends how the crystal ends are fixed. If they are free to move, then we have movement of domains and the shortening of the crystal at the crystal ends. But if we have several kinks at the crystal, then there are differences in the domain flows along the crystal. So it seems that plasticity is slightly more complicated process than elasticity itself. But also what was shown here, and maybe I didn't stress it properly, that we didn't have sliding domains as 2D regions in our crystals, but we still do have crystals which are plastically deformable. What means that even one tiny fibers we can pull out of the structure. So what I think that is quite important.
Thank you. So please thank Professor Mariana for her beautiful presentation. So now I invite Yuki and Shadoi from University of Waseda, Japan to deliver their presentations. So this is actually a replacement presentation, so they will be sharing the presentation.
I use my own computer. Okay. Okay. No problem. Okay.
Yes, it's
Okay.
okay.
Okay, thank you for inviting to the lecture, Professor Panche Naumov and organizing committee. And thank you for kind introduction, Chairperson. I'm Yuki Hagiwara in Waseda University, Japan. I and Shodai Hasebe, a doctoral course student in Waseda University, Professor Koshima group, this space. Professor Koshima was invited in this lecture. However, unfortunately, she could not come here. So I and Shodai will present this lecture, Light-Driven Crystal Actuation. Let me introduce our research about light-driven crystal actuation. First, this slide summarizes our mechanically responsive crystals. In the last 2 decades, we have developed many mechanically responsive crystals based on photoisomerization, phase transitions, and recently, the photosummer effect. According to the previous slide, we have focused on the 3 crystal actuation mechanisms: photoisomerization, phase transition, and the photosummer effect. And all over the world, the many mechanical crystal development have been mainly focused on photoisomerization and some based on phase transition. Also, in our research group, have been focused on mainly based on photoisomerization and some based on phase transition. In 2020, we newly found that the crystal exhibit fast bending by the photosummary effect as a new crystal actuation mechanisms. In this lecture, we will explain about crystal actuation mechanisms, first, based on photoisomerization, and second, phase transition, and third, the photosummary effect. For the first time, let me explain the photomechanical crystals by photoisomerization. And 30 years ago, we first reported the photomechanical bending of azobenzene crystal by photoisomerization. This azobenzene molecules, transketo forms molecules exist in the crystals. Upon UV ray radiation to this azobenzene transformed azobenzene crystal, the crystal transformed isomerized to the cis form by the photoisomerization on the irradiated surface of the crystal. Then, the irradiated surface was deformed due to the photoisomerization. In contrast, the back surface did not change due to the no penetration of light. As a result, the crystal bent by photoisomerization, as shown in this movie. After this first finding, we focused on the typical photochromic compounds, such as salicylene adenine and fluoride, and many photomechanical crystals have been developed mainly by photoisomerization. These photomechanical crystals can convert light energy into mechanical motion. This is a great merit, and so they're applicable to actuators, sensors, and soft robots. And throughout our research, in 2018, we newly found that this chiral azobenzene crystal exhibits locomotion by summary phase transition. This chiral azobenzene crystal has a summary phase transition temperature at 145 degrees Celsius, and then, interestingly, upon heating and cooling near the summary phase transition temperature of these long, thick, and asymmetric rod-shaped crystals, the crystal exhibit locomotion like each one like walking and fast rolling by summary phase transition. This finding inspires us to find new crystals with photoisomerization and summary phase transition for creating various motions of crystals. However, this summary phase transition point is too high, 1.45 degrees Celsius for practical application. So therefore, we need to find new crystal with summary phase transition at low temperature, slightly higher than room temperature. After that, on continuing the new crystal with the summary phase transition, and 2019, we newly found that this chiral salicylene amine crystal exhibit both photoisomerization and summary phase transition at minus 80 and 40 degrees Celsius, and then transform to the alpha, beta, and gamma phases. And at 40 degrees Celsius is a suitable phase transition temperature for practical application, from beta to gamma phases. Interestingly, upon UV ray irradiation to this beta phase crystal, the crystal transformed to the identical gamma phase, as same as the summary phase transition, even at minus 50 degrees Celsius. We named this new phase transition the phototriggered phase transition, and in fact, we clearly observed the phase propagation into the thickness direction by the phototriggered phase transition, as shown in this movie. Upon UV irradiation from the top, the phase boundary was propagated by phototriggered phase transition. This slide shows the possible mechanism of this phototriggered phase transition. First, upon UV ray irradiation from the top of this beta phase crystal, the transketo molecules, as shown in red molecules, were generated by photoisomerization near the irradiated surface, and then the storage was accumulated near the irradiated surface. And then, on continuing the UV irradiation, the transketo molecule was accumulated continuously to the irradiated surface, and then the localized stress induces the phase transition to the gamma phase crystal into the thickness direction, like domino effect. And finally, this crystal completely transformed to the gamma phase. This is a possible mechanism. Therefore, we revealed that for the use of the phototriggered phase transition, we can combine the photoisomerization and phase transition. In fact, by using both phototriggered phase transition and photoisomerization, we can create stepwise bending of thin crystals, as shown in this movie. First, this is real time, quick twist, disappearance, and bending again. So stepwise, this is slow motion. By photoisomerization in beta phase, the crystal twist and phase transition, disappearance, the twist, and in the gamma phase, the crystal bending by the photoisomerization. Therefore, the photo-triggered phase transition can create various motion of crystals, we confirmed. However, the example of the photo-triggered phase transition is only this one, and therefore, we need to find new crystal with a photo-triggered phase transition. Whether this phase transition is general phenomenon or not is required to review it. At that time, I started to join the Professor Koshima group as a bachelor course student, and my first research theme is finding new crystal with a photo-triggered phase transition. And the minimum requirements of the photo-triggered phase transition are summer phase transition at slightly higher than room temperature and photoisomerization. For finding such crystals, I firstly focus on 31 salicylene arenes, as shown here. These molecules are known to undergo photoisomerization from enol to transketol by photoisomerization and UV light. However, whether the summer phase transition is occurred or not is not predictable. And therefore, I synthesized these 31 salicylene arenes, such 11 substituents were introduced to the also meta and para position of these phenyl rings, and the 31 salicylene aniline crystals were produced for finding summer phase transition. Let me explain the result. This slide shows a summary of the summer analysis of 31 salicylene anilines. DSG measurements among 31 salicylene anilines revealed that upon heating and cooling, only this crystal, a para-benzoyl salicylene aniline crystal, exhibits summer phase transition at slightly higher than room temperature. Therefore, I investigated this crystal in detail. For the first time, for enol 1 crystals, I characterized summer phase transition. The DSG measurements reveal that upon heating or cooling, this crystal exhibits summer phase transition at -3 and 25 degrees Celsius, and then transforms to the alpha, beta, and gamma phases. X-ray crystallographic analysis in the temperature range from -100 to 60 degrees Celsius reveals that in all phases, this crystal belonged to the monoclinic P2 bar N, and the unit cell parameters were discontinuously changed between summer phase transition. For the next time, we measured absorption change upon UV radiation to the gamma phase crystal by diffuse reflectance spectra. As a result, upon UV irradiation, the absorption at 510 nanometer increased slightly due to the slight photoisomerization from enol to transketol with a time constant of 8.6 seconds. Therefore, according to these characterizations, I revealed that this crystal exhibits summer phase transition and slight photoisomerization. However, unfortunately, this crystal did not exhibit phototriggered phase transition. However, this crystal exhibits summer phase transition, so upon heating and cooling, this crystal exhibits bending behavior by summer phase transition. So, I observed the bending behavior by summer phase transition. This crystal, this rod-shaped crystal, is a beta phase crystal. This crystal was put onto the glass plate, as shown in this movie, and heat and cooled from the bottom. This movie shows the 10 times speed. Let's start. So upon heating, the crystal right tip bent up at 30 degrees Celsius, and then upon cooling, this crystal right tip bent up again at 21 degrees Celsius, as shown in this. Therefore, by summer phase transition, this crystal exhibits reversible bending upon heating and cooling, I reviewed. And then, for the next time, we try to observe bending behavior upon UV irradiation in the beta phase crystals. So upon UV irradiation to the beta phase, lower temperature than the summer phase transition temperature from the temperature. Upon UV irradiation to this beta phase crystal from the top, this crystal also exhibits the bending behavior with a temperature increase to the gamma phase temperature. Therefore, we revealed that this crystal exhibits bending behavior by summer phase transition, even upon UV irradiation, without heating and cooling. And then I tried to irradiate UV light to this gamma phase crystal higher than summer phase transition temperature. And surprisingly, I newly found that this gamma phase crystal, even higher than summer phase transition temperature, exhibit only by the bending behavior only by the photosummer effect without summer phase transition, as shown in this movie. So upon UV irradiation, the right tip quickly bent down. Please look. Quickly bent down with the surface temperature increase, and then removing UV light, the crystal returned quickly. This is the first finding. And this graph shows the time dependence of bend angle, as shown in black, and surface temperature, as shown in red. Upon UV irradiation, the crystal bent down at 0.5 degree within 1 second, and then after removing UV light, the crystal returned to its initial shape at the same time. And focusing on surface temperature, the surface temperature starts at 30 degrees Celsius, the higher than summer phase transition temperature, and upon UV irradiation, the crystal the surface temperature reaches to 50 degrees Celsius at the same time as the bending angle. In addition, this bend angle, time constant of bend angle is 10 times faster than the slight photoisomerization, and therefore, I firstly revealed that the crystal bent quickly by the photosummer effect without summer phase transition. This is the first discovery of crystal bending by photosummer effect. Interestingly, upon visible light irradiation, the wavelength which is not related to the photoisomerization, the crystal also exhibits fast bending by photosummer effect. Visible irradiation, bend down quickly, and then after removing visible light, the crystal quickly returned. Therefore, I revealed that this crystal bent quickly by the photosummer effect, even upon visible light irradiation. Now, finally, for the use of the fast bending by the photosummer effect, the high-speed bending of 25 Hz was achieved. The pulsed UV light was generated by the optical chopper, and the pulsed UV light was irradiated to this gamma phase crystals. As a result, the right tip was oscillated at 25 Hz at a bent angle of 0.1 degree with a surface temperature change between 40 and 41 degrees Celsius. And therefore, for the use of the photosummer effect, the high-speed bending of 25 Hz was achieved. And throughout this research, I newly found that the crystal exhibits fast bending by the photosummer effect.
Okay, and last 20 minutes, I, Shodai Hasebe, present this presentation on behalf of Professor Koshima, and thank you for having us for such a nice organic conference, and thank you, Professor Panche and organizing committee. And here, I'd like to talk about this topic, elucidation of bending mechanism by the photothermal effect. And here, we focused on this compound, also aminosalicylidene aniline, or ENO2, and we tried to elucidate the bending mechanism by the photothermal effect. So let me explain the results. And this is the crystal structures and photoisomerization properties of ENO2 crystal. And as shown here, the ENO2 crystal has like this crystal phase indices, and the length direction was parallel to the b-axis, and top surface was 001 phase. And this is molecular packing. In the crystal, the molecules were connected by intermolecular hydrogen bond chain along the b-axis, which correspond to the length direction of the crystal. And then we measured temperature dependence of the length of b-axis, and it was found that the crystal expanded upon heating along the b-axis, and the thermal expansion coefficient was calculated to be 129 per megakelvin. And then we measured UV visible absorption spectra of a crystal upon UV light radiation to reveal the photoisolation properties. And upon UV light radiation, the absorption around 510 nanometer increased slightly. This result indicates that this NO2 crystal showed relatively fast and weak photoisolation. And based on these results, we then tried to observe the bending behavior. And this is an experimental setup for crystal bending observation. And a plate-like crystals was set with the front face of the crystal facing up, and the UV light was exposed to the crystal top surface from top side. And the bending motion was observed from the side face with a digital high-speed microscope. And the top surface temperature distribution was monitored with an IR thermography camera. Then let me explain the results. First, we observed bending of a thin NO2 crystal. And this thin crystal with a thickness of 10 micrometer, prepared by sublimation, was exposed to UV light from top side. And this crystal bent away significantly by photoisolation. And please focus on the movie on the left side. And by UV light, the crystal bent away quickly and returned reversibly. And the graph on the right top side indicates time dependence of the bend angle. And it was found that crystal bent away 20 degrees in 2 seconds and returned reversibly in 6 seconds. And this bending by photoisolation can be explained by this bimetal model, as shown here. When a thin crystal was irradiated with UV light, the molecule near the top surface absorbs light and undergoes photoisolation. As a result, the top surface expands along the length direction, in that case, b-axis. On the other hand, the molecule on the back surface doesn't undergo photoisolation because light doesn't penetrate into the deeper side of the crystal, and the length is remain. As a result, the crystal bent away. Then we observed bending of a thick NO2 crystal. And surprisingly, we discovered that a thick NO2 crystal bent away very quickly, not by photoisolation, but by the photothermal effect. And please focus on the movie and left tip of the crystal. And this crystal was exposed to UV light from top side. And the crystal bent away and returned quickly. Play again, bent away, and returned. Top surface temperature increased 11 degrees Celsius. And the graph on the bottom side indicates time dependence of the bend angle, black line, and top surface temperature, red line. And it was found that the crystal showed bending away motion with a bend angle of 0.22 degrees in 20 milliseconds. That was 100 times faster than bending by photoisolation. And similarly, the crystal bent away, returned quickly after removal of UV light. The time constant for bending and straightening was calculated to be 3.3 milliseconds and 5.9 milliseconds, respectively, which was faster than photoisolation-driven bending. And as for the temperature, the crystal temperature increased 11 degrees Celsius by UV light. And the time constant for temperature increase and decrease was calculated to be 58 milliseconds and 51 milliseconds, respectively. And Based on these results, we revealed that the bending speed was as much as 10 times faster than temperature increase speed. And this result suggests that this high speed of bending by the photothermal effect is not directly caused by the temperature increase of top surface. And here I investigated the thickness dependence of bending behavior in detail. As I explained, thin crystals less than 20 micrometer showed large, significant bending away motion by photoassimilation, as shown here. On the other hand, thick crystals, thicker than 40 micrometer, showed high speed of bending by the photothermal effect alone, as shown here. What is more, slightly thick crystals with a thickness of 20 to 40 micrometer showed two-step bending by the combination of photoassimilation and photothermal effect. And for example, as for this crystal with a thickness of 35 micrometer, upon UV light, the crystal first bent away quickly by the photothermal effect, which was followed by bending away motion by photoassimilation. After removal of UV light, the crystal returned quickly by the relaxation of the photothermal effect, and the crystal finally returned to its original shape, two-step bending. And here I summarize the thickness dependence of bending behavior. And the graph on the left side indicate thickness dependence of bend angle. And the blue triangles indicate bending by photoassimilation, and the red circles indicate bend angle by the photothermal effect. The bend angle by photoassimilation is significant for thin crystals, but decreased significantly in proportion to the thickness, and reached zero thicker crystals more than 40 micrometer. In contrast, the bend angle by the photothermal effect appeared for thicker crystals more than 20 micrometer and increased slightly in proportion to the thickness. The graph on the right side indicates thickness dependence of time constant or bending speed. And it was found that for all crystals, the time constants for photothermal effect was as much as 100 times faster than bending by photoassimilation. Then we investigated how heat is generated in the crystal, and we measured transient absorption spectra following UV light excitation, and this is a proposal for the dynamics of NO2 crystal upon UV light radiation. And it was found that heat is generated in picoseconds very quickly via non-radiative deactivation process of excited Frank-Condon NO1 and Cisquito2, this process. And based on these results, we propose a bending mechanism by the photothermal effect. When a thick crystal was exposed to UV light, the molecule near the top surface absorbs light and generates heat by the photothermal effect. Then the heat is conducted to the back surface by thermal conduction, and non-steady temperature gradient delta T is formed along the thickness direction. As a result, the top surface expands the back surface, and the crystal bent away quickly. After that, when the temperature difference delta T reached a steady state, the bend motion stops. And this is a mechanism by the photothermal effect. And then we try to elucidate this proposed bending mechanism by simulation. And this simulation is composed of two steps. Step 1, heat conduction simulation. The temperature difference between top and back surface, or delta T, was calculated with this one-dimensional non-steady thermal conduction equation, as shown here. Step 2, bending simulation. The bend angle theta was calculated based on delta T, which was calculated from step 1 and with using this equation. And as for the step 1, this one-dimensional non-steady thermal conduction equation was solved by using FDM, finite difference method. We partitioned the crystal, the time, and space or thickness with several meshes. And based on the measured top surface temperature, we calculated the time dependence of back surface temperature and temperature difference, delta T. And this is a result of simulation. The graph on the left side indicates time dependence of temperature. And based on the measured top surface temperature, the back surface temperature, orange line, and delta T, a gray line, is calculated. And the graph on the right side indicates time dependence of bending angle. And the black line indicates the measured bending angle, and the blue line indicates the simulated bending angle. And you can find that crystal bending motion was reproduced with a high precision and accuracy by simulation. And this simulation, the successful simulation, confirmed the validity of the proposed mechanism that non-steady temperature gradient, delta T, causes high speed of bending motion by the photothermal effect. And finally, we try to generate high speed bending by using this photothermal effect. Here, we irradiate this thick crystal with UV pulse from top side. And please pay attention to the movie. Because the bend motion was so fast and the play speed is 25 times slower. By pulse UV laser from top side, we have achieved 500 Hertz high speed bending by using the photothermal effect. And then let me move to the last topic, polymorph-induced diversification of crystal actuation by photoisomerization and photothermal effect. And here, we combine polymorphism and multiple mechanisms, in that case, photoisomerization and photothermal effect. And we try to generate diverse photomechanical motions from the same compound. And here, we focused on this compound, para-fluorosalacylidene aniline, hereafter denoted as ENO3. Here, let me explain the result. This is the information of crystal structure. It was revealed that ENO3 forms two polymorphic crystals, alpha form and beta form. And as shown here, the alpha and the beta crystal belong to different crystal system and space group each other. And as you can see here, each polymorph shows their unique molecular conformation, crystal shape, crystal color, and molecular packing. In the alpha crystal, the molecule were arranged in a head-to-tail manner, forming a one-dimensional motif along the A-axis. And this A-axis corresponds to the length direction of the bulk crystal. In contrast, in the beta crystal, the molecule were aligned in a zipper-type arrangement, like this. And the length direction was C-axis, C-axis. And then we investigated thermal contraction and expansion properties. And as for alpha crystal, the crystal contracted upon heating along the A-axis. In contrast, the beta crystal expanded upon heating along the C-axis, length direction. Then we investigated the photoisomerization properties of the alpha and beta crystals. As for the alpha crystal, upon UV light radiation, the crystal color changed from transparent to yellow to red. And the UV visible absorption spectra reveal that the absorption around 400 to 600 nanometer increased by UV light. This result suggests that this alpha crystal undergoes photoisomerization from ENO to trans-keto form in the crystalline state. However, the beta crystal didn't change crystal color change upon UV light radiation. Similarly, the crystal didn't show any spectral change upon UV light. This result suggests the beta crystal doesn't undergo photoisomerization in the crystalline state. And based on these results, we observed the bending motion of the polymorphic crystals. The first example is a bending of a thin alpha crystal. And please pay attention to the movie. By UV light from right side, the crystal bent away with twisting. And after removal of UV light, the crystal returned reversibly. And the graph indicates time dependence of the bend angle, and the crystal bent away about 20 degrees in 3 seconds and returned reversibly in 50 seconds. And this bending can be explained by here. By UV light, the molecule near the top surface absorbs light and undergo photoisomation radiation. As a result, the top surface expands along the diagonal direction. As a result, the crystal bent away with twisting. Then we observe bending of a thin beta crystal. And this thin crystal, beta crystal, was irradiated to UV light from the right side. And please focus on the right top tip of the crystal. However, no bending motion was observed upon UV light. And this was shown here. No bending motion was observed. This is because the beta crystal doesn't undergo photoisomation radiation as explained before. Hence, the crystal doesn't show any mechanical motion by light radiation. However, we found that the thick beta crystal showed high-speed bending by the photothermal effect. We prepared a thick beta crystal with a thickness of 34 micrometer and exposed the crystal from top side. And please focus on the left tip of the crystal. By UV light, the crystal bent away quickly and returned quickly as well, and top surface temperature increased 9 degrees Celsius. And here I show you time dependence or bend angle and top surface temperature. And this bending is caused by the photothermal effect and expansion of top surface along the length direction. And finally, we generated high-speed bending by using the photothermal effect. And this thick crystal was irradiated to pulsed UV laser from top side. And please focus on the movie. Because the bend motion was so fast and the play speed is 25 times slower. And by UV light, we achieved 500 Hertz high-speed bending. And what is more, we found that a thick alpha crystal showed two-step bending motion by the combination of photoisomation radiation and photothermal effect. And this crystal was irradiated to UV light from top side. And please focus on the right tip of the crystal. And by UV light, up and down. And after UV light was turned off, bent away further, and then returned slowly. I'll play that movie again. Please focus on the right tip. By UV light, the crystal up and down. And after turning off the lights, the crystal bent down and returned reversibly. The graph on the bottom side indicates time dependence of the bend angle and top surface temperature. And the crystal showed two-step bending as shown here. And this bending mechanism can be explained as follows. First, upon UV light radiation, photothermal effect takes place and the crystal bent up. Then, after that, photoisomation radiation takes place and the crystal bent away. Upon removal of UV light, the crystal bent away further by the relaxation of the photothermal effect, and after that, the crystal returned by thermal backisomation radiation. And this is the mechanism of two-step bending. This is the conclusion for today's this section. From one molecule, we successfully created 4 motions by the combination of 2 polymorphic crystals and 2 mechanisms, photoisomation radiation and photothermal effect. And here, let me summarize today's 40 minutes presentation. Here, I show you the crystal actuation mechanisms and its features, photoisomation radiation, photothermal effect, and phase transition. Over the past 15 years, various light-responsive crystals have been developed, mainly based on photoisomation radiation. However, photoisomation radiation has some drawbacks. First, target crystals is limited only thin crystals with photoisomation radiation. Besides, the stimulus is limited. In many cases, the UV light is used alone. Besides, the bending speed is relatively slow. It takes from seconds to several minutes. On the other hand, the photothermal effect has a potential to actuate any crystals absorbing light, and that can be achieved with various stimulus, any light, including UV, visible, and infrared light at very high speed, up to milliseconds. That was impossible by bending by photoelectron radiation. So the photothermal effect has a great potential to expand the versatility of crystals as actuation materials. In the future, we aim to apply these crystals to actuators and soft robotics. And this is the conclusion, and thank you for kind attention.
Thank you, Iki and Shodai, for your wonderful presentation. Now, floor is open for questions. Can we have some questions, please?
Very nice. Did you try to test your thermal gradient explanation by simply shining from both sides? So you can actually remove the issue of the gradient.
You ask when the crystal was irradiated from both sides, what happens?
Did you check that? Yes.
I've never checked, but it's expected the crystal didn't bend, but the crystal expands along the length direction.
So it will be an easy test, right?
Maybe easy. We have to buy another UV light. Yeah, but it's easy.
Okay.
Thanks for that nice talk. In the case where you use a constant illumination, I understand that the deflection must be due to one of those two effects, isomerization or photothermal effect. But when you're using an oscillating light source, there's a well-known phenomenon called the photoacoustic effect, which causes crystals to oscillate. It's the basis of, in fact, cantilevers in some atomic force microscopes are driven by this. Use a time-varying light source, and it drives a sound wave in the material, causes it to oscillate. I wonder, when you're using the varying light source in your case, how do you rule out the photoacoustic effect from being part of the response?
Sorry, I couldn't catch your question. So could you repeat the question again? Sorry.
I'm asking about whether or not, when you use a light source that varies with time, if part of the response that you see in the material is due to the photoacoustic effect, the generation of sound waves due to the absorption of an oscillating light source.
So your question means that upon various light irradiation, the crystal generates acoustic sound also?
Yeah, it oscillates due to the
Generate via the photothermal effect?
Sorry, I have not checked yet, so I'd like to ask a question on the coffee time. Thank you. Sorry.
Very, very nice talk, and a lot of implications here. The photothermal effect seems to be a direct coupling from the electronic modes of the crystal to the phonon bath, which acts as a huge heat sink. And I think that's why you're getting that rapidity of energy transfer into the lattice. You're observing, but I have a question, and that is, did you do any wavelength dependence? You did temperature dependence, but I didn't see wavelength dependence. You have N to pi star transitions as well as pi to pi star transitions in that molecule of the salicylene aniline, and I think that you might get an interesting wavelength dependence. Also, your absorption spectra are highly attenuated, so you're not getting the complete absorption band. Did you take just a free molecule spectrum and get the molar extinctions?
You asked, have we checked the free energy or so?
Sorry?
Sorry, could you repeat the question again? I'm sorry.
Okay, well, I'm sorry, it was a multiple question and observation. Let's start at the end. I think your absorption spectra are clearly attenuated. That means you're not getting the absorption peak in the crystal. The crystal is too thick and absorbing, so your spectral data isn't quite reliable. And you need solution spectra or gas phase spectra and get the molar extension coefficients to really calculate the depth of penetration of the light into the crystal. Second, the work has a very nice implication about the coupling between the electronic structure of the molecules and the crystal and the phonon bath of the lattice itself. And apparently what's happening in your effect is that you're getting the electronic excitation by your radiated light dumping energy rapidly into the phonon bath of the crystal. And that should be an interesting temperature-dependent study also.
Maybe I can help.
Thank you.
光の波長遠鏡があるかどうかという質問です。光の波長の遠鏡です。
波長が
wavelength.
Yes. We haven't checked the wavelength intensity, wavelength dependence, or bending behavior. But as for the up to now, we can say that photoisolation can be caused by UV light alone. But the photothermal effect can be induced any light, including UV, visible, and infrared light. But unfortunately, we have not investigated the difference between the different wavelengths and their bending behavior. Sorry.
Okay, thank you for the very, very nice talk. I'd like to know if, given that in the photothermal effect, a big part is played by how the thermal energy is passing through your crystal, right?
Yeah.
So I'm wondering if you ever thought about engineering your crystals in a way that you are engineering the thermal response. Because there might be some phonon, as mentioned by Professor Eckert, some phonon pathways, some way, for example, adding rotating groups that are dispersing heat and energy to really modulate the thermal response of the material. So you might end up with a tunable photothermal effect, basically.
This one?
Yeah, you mentioned also you mentioned that you are also adding in your equations to describe the thermal effect, right? There is a big part of the thermal transport. So I'm wondering if you ever thought about engineering your crystals to tune the thermal transport, basically. Instead of thinking about the electronic structure of the molecule or the photobending effect itself, to think about just tuning the thermal transport to have a tunable photothermal effect.
So your question means that by changing the compounds of crystals, the energy of photothermal effect can be tuned? Yes, okay. So we have tried it in detail, but the obvious tuning method of energy is not predicted. So this is a challenging task for me. Thank you for your nice question.
So, thank you. Please thank Yuki and Hoshoi for their wonderful presentation. So I have decided not to.
Thank you very much.
Not to squeeze your coffee time, so we'll be back here at 11:20. Running late.
So good morning, everyone. I hope everyone is back from the coffee break. I welcome you all to the second part of the first session of this conference. I am Rishika Rai from ISA Trivandrum, co-chair for this session. And I would like to thank the organizers once again for giving this wonderful opportunity. So in this session, we have 3 talks. We'll start with the first talk now. For that, I would like to invite Dr. Luca Catalano, Free University Bruxelles, to deliver his talk. Welcome, Luca. The stage is yours.
Hello, everybody. Yeah, it's working, yes. So, first of all, thank you for having me here. This, of course, iconic seminar. Today I'm going to talk about my research that is mostly focused on understanding martensitic-like organic crystals. So it's about polymorphism, it's about active materials that are behaving more or less like the crystal that I'm depicting in this brief video. So first of all, a little introduction of myself. And given the nature of the meeting, and given that one of the founders was Gerhard Schmidt, that is widely recognized as the founder also of crystal engineering, I'd like to give a crystal engineering trajectory of my career. So I started as an undergraduate or graduate student studying intermolecular interaction in crystals. I was focusing back in the day on halogen bonding. Then, with a very fruitful collaboration with Miguel, that is here in the audience, I started to apply this supramolecular principle to try to understand how to tune inner dynamics in organic solids. And afterwards, my attention shifted to macroscopic dynamics, for example, flexibility or polymorphic transition, with the overall goal to build up adaptive functional materials, so systems that can respond to external stimuli. Now, where am I now? I'm hosted by Yves Gertz at the Free University of Brussels. I have a Marie Curie Fellowship there. And I'm working in Brussels. That is a beautiful city. If you've never been, I will be happy to welcome you with some beer, chocolate, and fries. These are the 3 staples. As you can see, the city is beautiful, but don't get fooled by the picture, because very likely you will find something like this. Because while the city is amazing, the weather is, how to put, not ideal. So I want to start not really going straight into the crystal business, but with a little historical perspective that can give us also kind of a philosophical take on adaptive and active materials and why we are going in that direction. And everything is starting with sailing around the world. When in the 16th century, opening the golden era of exploration, they provided the last and definitive proof that the planet is not flat like a pizza, even though someone is not really convinced even nowadays about this. But we finally and definitive proof that our planet looks more or less like this. There was a major problem for people navigating around the world. And the major problem was if you want to navigate safely and efficiently, you need to know your position, of course. And when you are at sea, it's not a trivial issue to be addressed. And why this is important, of course, back in the days, naval transport was a key also to political, economical, and also military supremacy. So it was a very big issue back in the days. So when you want to know your position at sea, you need two parameters. You need the latitude and you need the longitude. Now the latitude is quite easy. You get the angle of the sun or the angle of the polar star, and you can get your latitude, so your position, your parallel position. But meridians are very, very difficult to calculate, especially if you don't have a reliable clock, because you need to know the time reference given a relative position, for example, to Greenwich. The British Empire established Greenwich as the reference point. But at sea, as you can imagine, the conditions are very harsh. You have a lot of mechanical stress, humidity, temperature change, pressure change, and till the 18th century, for about 300 years, it was not possible to solve this issue. And it was such an urgent matter that the UK established a commission for the discovery of the longitude. So they were just working to discover a way to measure this longitude. And the solution came not from physicists or chemists, but came from a clockmaker, a craftsman. This guy, John Harrison, you might know him, was here, there is a plaque at Westminster, it's John Longitude Harrison, was the guy who finally solved the issue and got also a very rich prize from the commission I mentioned earlier. He realized that the key is not really finding the right equation to describe what's really happening, but is working with the materials themselves. Working with the embedded properties of the materials and their active response. And working with this paradigm shift in mind, he came up, after 3 decades of working on it, he came up with the first prototype of a marine chronometer. How? By successfully design a system with wood and metal that is actively responding to the environment by, for example, thermal expansion or hygroscopic nature of wood. And by doing so, he's introduced for the first time the first example of a bimetallic strip that we know is a really staple in the world of active materials, because it's a metal strip made out of 2 different metals with different thermal expansion that is deforming thanks to the heat. Now, nowadays, we have a different take on materials, especially for mass-produced materials. In academia, yes, we are interested about active materials, but mass production is a different story. Even though there are some examples, for example, medical stents, that are responding to, for example, different temperatures, expanding and contracting, or thermostats. Analogic thermostats are still based on, for example, bimetallic strips. So they are active materials. Most of the materials that are like these brick walls, we want them robust, reliable, and not changing no matter what are the conditions. So of course we are thinking about the inner properties of the materials, but we are not really thinking about the materials as actors in the world of functional systems. So this is the first problem. We are kind of constraining the materials there. So we need to change our ideas about materials and the fact that materials, they can perform themselves some useful actions and functions. Another problem when we think about materials, there is we are going towards complexity and not simplicity. And to address this issue, if we think about intelligent and smart systems, we think about generally software-hardware interface, and probably is also a cultural bias, but we think about robots. And I can tell you about robots because I was in the lab that developed the first robochemist, Andy Cooper Group in Liverpool, back in 2020. I was working there. It's an amazing work, and actually it's amazing to work in a lab and looking at a robot that is performing your tasks even 10 times better and 10 times faster. So this is where, of course, we are going. It's amazing. But if you think about these robots from a materials perspective, it's made out of thousands of components that can fail. You need to plug in a sort of course, energy supply. In most of the cases, electrical supply. So what can we do as organic solid-state chemists? We can think about the materials themselves. And maybe we can, again, think about the paradigm shift following John Harrison. We can think about answering this question. Can we embed functionalities within the materials themselves? So can we, and if we look at this problem, and if we start to search for materials, and also where the research in this topic in this field is going on, then we realize that abiotic systems, so non-living systems, materials, they are very much alive. And indeed, there are several examples of active materials very successful, and the field is growing exponentially, but especially in other fields other than crystalline forms, organic crystalline forms. We have successful examples of liquid crystals as active materials or adaptive materials, elastomers, inorganic systems, for example, metal alloys. And here are a few examples of how they can readapt depending on different stimuli. We start with light, for example. It's a beautiful work from Ari Primaghi, where we have from Tampere University, we have a nice elastomer, photoactive. If you shine light on it, it's mimicking the Venus flytrap. Amazing. And it's working very well. If we put this very nice system engineered with different materials responding to temperature in different ways, the self-assembly lab at MIT that is actually combining architecture, design, biology, chemistry to build up new adaptive materials, you can start with a monodimensional system and end up with a two-dimensional system that is mimicking, for example, the MIT logo. Or one of the latest work from Takuzo Aida in Japan, you can start with a very simple polymer, and just by playing with intermolecular interaction, you end up with total self-healing just by hand pressure for 30 seconds. So materials, they can really be adaptive, and the advantage there is that with a single component or few component systems, you can get very complex responses. But in all this story, where are organic crystals? Now, if you think about adaptive response, we think about dynamic. And this topic has been touched by Aurora, by Durga, and also by the previous speakers. Of course, crystals are dead. The poor Leopoldo Rusiczka, we are all going after him, because he mentioned back in 1939 that crystals are a chemical graveyard. Okay, you have to take responsibility, is what you say, right? So by chatting with Jack Danitz, he mentioned that crystals are a chemical graveyard, so they are not really interesting. They are inert, they are unreactive, nothing really interesting is going on there. But thanks God, it's not me, but the superheroes of our field, they first defied this concept, starting with Gerhard Schmidt himself, with his amazing studies on topochemical reactions, Peggy Etter and his jumping crystals. We have jumping crystals, we've seen these examples also in the previous lectures, and also Jack Danitz himself, by his seminal studies on thermal ellipsoids and thermal motion in crystals, and how these can affect also the property of the crystalline systems themselves. So if it's true that crystals are dead, then it's also true that long live to the crystals. So crystals are very much alive. So can we challenge current materials technology by using adaptive organic crystals? Well, first of all, think that organic crystals, they possess a unique set of properties. Compared to elastomers, inorganic systems, liquid crystals, they have a unique set of properties that might be very useful in specific applications. First of all, long range order, of course, low weight, that could be useful for certain applications like soft robotics, high tunability. But we know that by changing a single atom, we're going to change the full structure probably, and also, of course, the properties associated with it. Defect-free, or at least lower defects compared to amorphous or partially amorphous systems, and they possess a set of mechanical properties that are sitting in between soft matter and inorganics. And this is making these kind of materials really attractive for that reason. So we know also from the previous talks that they also possess a broader adaptive response, depending, of course, on the systems you're picking. You can shine a light, you can heat a system, you can expose to chemicals, you can have mechanical force or humidity, and a lot of different classes of organic crystals, they will respond. How they will respond? There are different kind of responses. We already seen some of them. For flexibility, plastic elastic response, polymorphism, photoactuation, self-healing are just a few examples. So we have a rich dynamic landscape we can play with. Now, going into the topics, into the core of the topic, I'm studying martensitic like a transition, so polymorphism. There's not really need to introduce the topic, but I'd like to just quickly summarize it by borrowing a slide from Aurora that is, I think, is summarizing the field very nicely. We know the importance of polymorphism, right? We know that in pharmaceuticals, food chemistry, if you think about pigments, organic electronics, organic crystals are central, and playing with different crystallization conditions, starting with the same moiety, you can reach completely different crystal systems at the end, in terms of morphology, in terms of physical-chemical properties. So polymorphism is a central challenge that has not been fully addressed yet. So it's still an open challenge and is waiting for us, essentially, to be addressed and solved. So in this realm of polymorphism, I'm interested in solid-to-solid polymorphic phase transition that are particularly interesting because if you think about application, if you think about devices, you want a material that remain a material during your function or during your processing. So in this realm, you can have generally what you have is a two-stage mechanism of polymorphism. So you start with a phase, and by transforming it, by applying temperature or pressure, generally, what's happening, you have a nucleation and growth process that is associated with a molecule-by-molecule change. Generally, you have massive structural change in the structure, and this brings to starting with a single crystal and ending up with a polycrystalline system. So often you lose the single crystallinity of your system. You also might encounter very slow kinetics, up to days, months, depending on the conditions of the polymorphic process. And often these systems are also irreversible. So they are monotropic transitions. So it might be useful for some applications, but for others, its reversibility is a key. But there is a growing interest in a specific kind of solid-to-solid transitions that has been named martensitic, just to make a parallelism with an inorganic world. Probably the most general definition is cooperative phase transitions. You start with a single crystal, you end up with a single crystal with minimal structural changes, generally associated with also huge morphological rearrangement that can be extremely useful also from an application point of view. Very fast kinetics. Generally, these kind of kinetics are happening in the millisecond range for millimeter, centimeter-like crystals, and they are always reversible. So all these are very interesting parameters that we want to play with. But we want also to understand how can we exploit, how can we understand deeply what is happening, why it's happening in this very peculiar fashion, and how can we exploit, and maybe also how can we design system possessing these peculiar transitions. So I started my work in the field by working with tetrabromobenzene. At the time, I was a postdoc in Panche's group. Tetrabromobenzene, as has been shown by Durga, is known since the 50s to undergo a polymorphic phase transition around 45 degrees. Now, if you look at what's happening, it's interesting because you have an abrupt release of mechanical energy, mechanical stress, that is turning the crystals in jumping crystals that sometimes often are also splintering. Now, if you look closely to the structure, you realize that there are only minor changes in the unit cell parameters. The symmetry is retained, and you have just a slight reorientation of the aromatic planes passing from the low temperature phase in blue to the high temperature phase in red, called beta and gamma phases. So I was interested, okay, they are very, very similar, but how does it happen? How you can jump from one phase to the other? I was interested to address this question, and to do so, thinking about phonons again, thinking about the problem of vibrations, I started to move towards Raman spectroscopy. We started back in the day a very fruitful collaboration with Timothy Carter at Syracuse University that is working on terahertz and Raman spectroscopy, and we did the variable temperature Raman spectroscopy coupled with calculations, and we realized if you look at the low frequency region of the Raman spectra that are associated with phonons, so collective vibration of molecules within your crystalline system, we realized that there is a phonon at 18 centimeters minus 1 that is behaving pretty weirdly or has a unique behavior. If you follow the trajectory of this rotational phonon, 18 centimeters minus 1, you basically follow the trajectory of the transformation. So you start from the low temperature phase and you end up with the high temperature phase, geometrically speaking. But now we wanted also to see from the energetic point of view, if you basically optimize the structure in different points of this trajectory, you will start again with the beta phase, you will pass through a barrier, and you end up with the gamma phase. So it means that this rotational phonon is behaving really as a gateway vibration. So it's kind of driving the process itself. And this is a very interesting discovery. So phonons and vibrations are probably really having a key role in driving, or at least they are involved somehow in these martensitic or cooperative phase transitions. With this in mind, I started my Marie Curie in Brussels with Yves Gertz, and Yves Gertz published in 2018 this very nice work with studying these two organic semiconductor, a benzothiophene derivative with two terbutyl moieties as side chains, and TIPS pentacene. That is a very, very famous organic electronic system. Both systems at different temperature, around 70 degrees Celsius and around 130 degrees Celsius, they undergo this martensitic-like transition. How do we know? Because if you look at the videos of what's really happening single crystal by single crystal, you really see the front wave of cooperative and plane-by-plane transformation that is happening on the millisecond time scale. In this case, you have also a huge morphological reorganization with an expansion of about 10% of the length of the crystals. If you look at the crystal structures, you will see that this is an order-disorder phase transition. So basically what's happening, the symmetry in both systems is retained. You have just minor changes in the unit cell. And what's really happening, the big change passing from the low temperature to the high temperature phase is a lot of disorder of the side chains. So we started to think, okay, maybe this disorder, it's a key to get some information and maybe also to find a way to design a new system possessing these cooperative phase transitions. And Yin Diao, one of the corresponding authors of that paper, did a very interesting work where they exchanged the terbutyl moieties with the central carbon exchanged with the silicon atom. Now, silicon atom is bulkier, so you're expecting an effect on the overall dynamics. And indeed, the rotational dynamics is kind of frozen, or at least is slowed down, enough not to have anymore a martensitic transition. But you have a simple nucleation and growth polymorphic transition that is going from a single crystal to a polycrystalline system, and is also monotropic. So you really completely change the mechanism of what's really happening. So again, this is pointing at the direction that this rotational motion is key to understand what's really happening in these systems. So these studies has been done mainly by taking advantage of X-ray diffraction. And as you know, X-ray diffraction, especially to study dynamics, is an average technique. It's not really telling you what's really happening at the dynamic itself. You can follow just an average picture of what's happening from a dynamic point of view. So we wanted a more local perspective. And in that sense, again, I turned my attention to Raman spectroscopy, and I started a very fruitful collaboration with Omer Yaffe and his talented student, Maura Asher. They also hosted me for a month at the Weizmann Institute. What they do there is, with a very specialized equipment, is single crystal Raman spectroscopy. So we started to do single crystal Raman spectroscopy on the two systems, and we got this very beautiful spectra. With the red arrows, I'm pointing at the phase transition. As expectable, first of all, the phase transition is matching with whatever has been already published and reported with thermal analysis and X-ray diffraction. And second, the shift and broadening of the peaks, again, is pointing out that an order-disorder phase transition. So we are confirming what was already known. But interestingly, if you fit these peaks and you follow the shift and the broadening, you are expecting, especially before the phase transition, you're expecting to follow a linear behavior because you're expecting to follow a thermal expansion. But indeed, for certain peaks, like the first phonon, the phononic peak that we see here, the system is behaving non-linearly. And this is pointing at an anharmonic behavior of the vibration. Anharmonic means that whenever you are discussing about vibrations, the simplest approximation is harmonic approximation. So you are taking into account the vibrations like springs. But of course, this is a simplistic approach. Often, this is not really working. And in this case, for some of these phonons, this approach is not working. So, and if you closely look and assign the peaks, you discover that this is happening for all the phonons that are really centered on the side chains. These are the eigenvector. Without going into the details, they are showing how the atoms are moving within the molecule, but most of the motion is happening at the side chains. And these side chains, then, they are the only ones behaving in an anharmonic manner. And if you look at the theories pointing at that, it was mentioned the soft mode theories, for example. This is happening, especially in the inorganic world, when you have a phonon-driven process. We are still studying this into the details. As you can see, the work is not published yet. But we are now trying to fit this to existing theories to really try to find out what's the role of this rotational dynamics. But as far as our results are telling us, it seems that rotational dynamics, again, is kind of driving the process itself. So, very good. We have an extra proof that this rotation is key to understand what's really happening. So, can we build a model out of it? So if you look at these molecules, they might look different, but they are also similar in a certain way. And you can build a very simple model where you have a rigid aromatic core and you have some side rotating side chains, bulky side rotating side chains. And this reminds me of my time in Miguel's group, of course, because if you think about this, you might think about amphidynamic crystals. So systems that are possessing an isotropic Brownian rotation, you have some moving components and you have some static components. And what's nice about amphidynamic crystals and all the work that has been done in the field, that there are several design rules and there are several examples of series of compounds where you can really build series of compounds showing tunable dynamics. So I thought, let's try to get similar systems. Do they show this polymorphic transition, this cooperative phase transition? So we turned our attention to a first candidate, this simple model. Basically, the aromatic core is similar to the starting system here, the benzothiophene derivative, but we added phenyl groups in between the rotating side chains and the aromatic core. We are expecting the phenyl groups also maybe to participate even in the rotation, because it's known that phenyl groups, they might flip in solid state, especially with temperature. So we were excited. I didn't wait even to grow good quality single crystal. After the synthesis, after ascertaining the purity, I took some of the powder and I put it on the hot stage, and this happened. It's a very low quality crystal, but it's a single crystal. And as you can see, at 250 Celsius, it starts to move, to reshape, to change morphology. I was really excited. So is it working? Is it really working? But I like to have something better in my hands. So by sublimation, we grew better crystals. We got a nice single crystal. And again, this is a GIF, of course. It's going back and forward through the transition. And as you can see, you have a morphological rearrangement. And you have a change really in the morphology. I'm just showing an angle just to give you an idea that the change is prominent. In this case, about 6 degrees of this angle here. So the transition has also 200 degrees of hysteresis. That is kind of peculiar. We are, again, in the process of studying it. I'm just showing you really new stuff, so everything is unpublished. So we tried also to get some data from Raman spectroscopy, as I showed you before, but unfortunately, the systems start to be pretty complex, and the transition is happening at 250 degrees Celsius. So as you can imagine, if you start at 80 Kelvin, you get a lot of phonons, a lot of different normal modes of vibration, but if you heat up the system, you end up with merging of most of the phonons, so you lose a lot of information. But this is confirming that this is an order-disorder phase transition. There is a lot of dynamic going on. So we also got the single crystal structure of both phases, and it's showing what we are expecting. So a lot of disorder happening at the side chains, the terbutyl side chains, but also the phenyl groups. They start to flip as expectable. So can we generalize the strategy? Can we find other candidates? Can we build up a series? This will be a unique example of really when you start with a molecular design and you end up with inducing specific polymorphic transitions. So we start with the candidates that we know is working, and then we start to build a series of compounds. Let's start, for example, to expand the aromatic core and adding again terbutyl moieties. As you can see from the video, you have a contraction and expansion of a single crystal. Let's try to see if this is a robust strategy with the commercially available compounds, very simple compounds. This is a diterbutyl dipridyl ligand, very simple, structure is known, and this is expanding about 10%. And this is 3-terbutyl-benzene. Now, it might be not clear because I'm still managing to get good quality single crystal, but there is a front wave passing through the crystal once you reach minus 130 degrees, so pretty low temperature. And we also made a custom-made molecule. This was synthesized by us, following the model of 3-terbutyl-benzene. We just added an acetylene bridge and a 3-methylsilyl moiety. And again, you can see phase front, morphological reorganization, so a cooperative transition. It seems that this strategy is working. We are getting a lot of compounds. Keep in mind that in this field, finding Martensini transition is not easy, and it's mostly a phenomenological observation. You study a lot of systems, and you find out something that is working. In this case, it seems that we have a guide. Work are in progress, but so far we got the single crystal of all the structures. Some of them, they were already published, and without going into the details of the structure, but they all showing what are expected. So a lot of disorder of the side chains. In most of the system, the symmetry is retained, minimal changes of the unit cells, so they are really cooperative transitions. We are also studying them through, again, with the Weizmann, through Raman spectroscopy. And again, a lot of dynamics going on because you have very broad peaks. Look at 3-terbutyl-benzene after the transition is really behaving like a liquid almost. we are now following each of these phonons to try to understand, again, if there is some of these phonons are really driving the process. So what's the take-home message of all of this? Can we program crystals? Can we think about crystal engineering principles, also thinking about polymorphism? That we know that is a very, very tricky topic. It's difficult to predict polymorphism. But in this case, we found a way, just by looking at cooperative transitions, there are two main findings. First of all, we first described these specific phonons that are playing a key role in driving the transition. That's the first finding. And the second is that it seems that we are building up a pretty efficient strategy to induce specific polymorphic transitions in organic crystals. In this case, cooperative phase transition. What's next is really the frontier of my research, let's put it that way, is where I'm going in the next few months. Now that we are finding strong evidences that there are some phonons that are really involved in these polymorphic phase transitions, can we think about exciting them, specific excitation of single phonons to see, of individual phonons, to see if we can trigger a phase transition? So mode-selective excitation, starting with the polymorph and ending up with another polymorph. Transiently, maybe during just the excitation, or permanently. That's an open question, and I'm trying to address this challenge now. As I mentioned, all these are unpublished data, but I'm pretty sure that you won't reveal anything, because if you look close at the screen, you might realize, if you don't know the reference, this is a sci-fi movie, and this is a memory eraser. So, of course, I'm joking. I fully trust the community. And thank you all for your attention. I'm leaving you with some dancing crystals and, of course, a discussion.
Talk. So now the floor is open for discussion.
Luca, beautiful work, exciting. So thank you for sharing. So the question I have for you might be a little provocative, but there's always a question between the relation of cause and effect.
Yes.
So are your observations related to phonons behind the transformation, or they're a result of the transformation? Have you given any thought to that, and how are you going to sort that out?
Yeah, of course, it's a very nice question, because of course when we thought, I remember both with Panch and with Eve, certain times we sit at the table and we think, okay, this is really a kind of egg and chicken and egg question, right? Who's the responsible of what? So far, with the study that has been published, for example, in the Nature Communication paper of Yves Gertz, they used a lot of X-ray and a lot of solid-state spectroscopy, NMR spectroscopy on powders again. So again, averaging what's really happening. And in that case, you lose a lot of information. But if you go back to transition theories, for example, the Landau theory of, that is related to the soft modes, so that there are specific modes that are really driving transition in organic systems, for example, in ferroelectric, for example, systems also. If you think from that perspective, and you start to think at locally, so that's why we turned our attention to Raman, well, then the picture is becoming a little more clear. And you get a little more information if you link the anharmonic behavior of vibrations, and now you reach the transition. Because it's true, at the transition itself, you never know. You might end up with something that you are increasing the motion just because you have more space, you are lowering the density of the system. That's, of course, is difficult to decouple. But if you study what's happening going towards the phase transition, there you will find a lot of information there, and is there that we are digging into. So I hope I'm answered.
Luca, I have a question. So,
yes.
Very nice talk.
Thank you.
Fantastic, amazing. In your compounds that you can now see the transitions, what is the difference in the transition temperatures across those different compounds? Are they similar? Are they different? And have you seen any relationship between those and the structures of the crystals?
Yes, it's a good question. It's an amazing question, actually. Keep in mind that to get these compounds, it took me 2 years. So it's a long process. And I think to answer your question, first of all, I'll tell you the range of temperatures. It's huge. Because you have from minus 30 Celsius up to 250 Celsius. Now, a very quick rule of thumb is that the simplest molecules, the simplest systems, they show the lowest temperature. Like they have, probably because they are less constrained by pi-pi interactions, for example. But I wouldn't go into trying to find correlations because there are only 6 of them. Only. They are a huge number in terms of designing, but this is a small number in terms of statistics. So we have to collect way more data to have some idea of what's really happening. Yes?
Beautiful talk.
Thank you.
And work. Your dithiol compound was quite interesting, Raman, because at 100 wave numbers, it looks like you have something behaving like a soft mode.
Yes.
But it's becoming, but the crystal vibrational frequencies are becoming more anharmonic.
Yes.
And especially your low frequency ones around 30 wave numbers, they're moving to lower frequency. And that suggests to me that they're starting to couple with the acoustic modes of the solid. And the acoustic modes, of course, are directly related to the elastic constants, which would affect the geometry changes you see. Beautiful.
Indeed, the two approaches, the last approach that I mentioned to try to excite specific phonons can be taken from 2 different perspectives, and this is exciting. I think there are different groups that are working in different directions here. You can think about optically, so going into the optical phonons that we see with Raman, for example, or you can think about acoustic modes that are also, as you mentioned, related really to the deformation of the system. And in that case, of course, you need Brillouin scattering, in that case, to get also the anisotropic values and how the system mechanically is behaving. Whoop. It's working? Yes. So, but it's an excellent point. Acoustic phonons are also a key that I didn't mention here because we are not going in that direction. But of course, they play a key role, especially in dictating the overall mechanical properties.
But I think your evidence is there because the acoustic modes must be there. They're going to be around 20 wave numbers and below.
Yes.
And you're moving right into that region. There must be coupling.
Yes, yes, indeed. And this is pointing out that the anharmonic behavior, there should be a huge coupling. Everything, because a lot of people, when they study these systems, they tend to stick to the harmonic approximation. But the harmonic approximation doesn't hold, especially with these soft, low energy vibrations. You have to think a little more broader to what's really happening when you couple phonons together. So when you start to behave non-linearly, basically. So I totally agree. Thank you.
Thank you, Luca, for the nice presentation. So you say that you solved the crystal structure of the disordered phases.
Yes.
And could you solve them as a function of temperature to see if you have the dynamic disorder?
Yeah, that's also a good point. Of course, we solved for a couple of them at different temperatures, and you really see. I think there are, as I mentioned to Miguel, there is something going at the transition, but there is something going towards the transition. And it has been already shown, this softening of some modes. This is tell us that the system, you are looking at 2 different phenomena that are coupled. And it's also difficult to decouple them. Because if you look at this transition, for example, we have done dielectric spectroscopy measurements, sometimes you don't even see a peak, but you see a change, a continuous change. Starting from your system at, 30 degrees to 200, you see a continuous change. Now, this is going against the description of what's really happening, because what we have, these are, of course, first-order transition. We know that from DSC, for example, it's clear you have one peak going forward, one peak going backward. You have some enthalpy of a transition that is involved. So it's a classic first-order aneantitropic transition. But there is also continuous transition that is happening. That it reminds about ferroelectric system, for example. This is a kind of a second-order process that is going on that is linked to the dynamics of the system. That's exactly what we are trying to do. We are trying to couple the two. How can we take advantage of this continuous dynamic to try to influence the first-order transition? That's more or less where we are going.
Hi. Graeme Day, Southampton. My question actually picks up partly on Craig's question about I'm thinking with my modeler's hat on, and I'm wondering, because you're showing Raman data.
Yep.
And I'm not thinking about acoustic modes, but I'm thinking about the optic modes,
Yes.
but their dispersion through the Brillouin zone. So maybe you haven't been doing these sort of inelastic neutron scattering experiments, but what's your feeling on the weight, the length scale of these transitions? Because if we look at these modes and how they extend across, sort of go out to the edge of the first Brillouin zone, are you getting softening there? Or are you really going to get it when you just look at the optical modes with IR and Raman type experiments? So
that's an interesting point, and I think the response is that probably you have both happening. What we see from our experimental data is that the optical modes are clearly behaving like it's a clear parallelism with the soft mode theory. In this case here, you have some modes that are really going towards zero. They are not really behaving like Landau theory predicts, because Landau theory say you should go to zero, towards zero, but we never go towards zero. So it's, again, it's probably given the soft nature of the interactions going on, it's difficult to know what's really happening, but so far we don't know. But my take is that the lifetime of these excitations are in the picosecond realm. If you think about the below 100 centimeters to -1, these modes are first always excited, no matter the temperature we are looking at, unless you work at 20 Kelvin, they're always excited. So it's something that is always going on in the system, and given the phonon optical nature of the system, I think they extend towards basically the whole lattice. But there is a point. You have to think about also boundaries and the surface effects that we know they play a key role, because, as I mentioned, these systems are still described as a nucleation and growth process. And indeed, there has been many examples when you have a defect, and at the defect, you start your transition. So you have a lot of going on. You have the bulk, phonons, optical response of your material, and on the other way around, you have also the effects of defects and imperfections at the surface, or even in the bulk itself. So very difficult to decouple what's really happening. Very difficult, but I hope that by exciting these individual phonons, if we are able to deform the structure, we might have an answer. We might have that, yes, phonons, optical phonons, they might play a key role, kind of canceling the effects of whatever is around them.
Thanks.
Nearly a continuation of what was asked. In the acoustic phonons, you have also a very large dispersion usually.
Yeah.
So you may also pick up different Ks. On the other hand, with the optic phonons, you have usually very little
you are more
dispersion,
centered.
and you can see an harmonicity by the second order. So if you look at the second order, like the two phonons should go a little bit below the double of the frequency. So I think it will be very interesting to look at the double of the optics.
Yes, and that's what we are doing with Omer right now. We are looking at this, plus we are looking also, another thing that we are going into is to try to see the effect of polarization. As mentioned before, polarization has a key role. So far these are unpolarized data, but we are also looking at polarization, so the effect of the orientation of these phonons, and if there is a preferential orientation where the phonons are dispersing and are playing a key role there in driving the deformation.
So we have time for just one last quick question.
Simon Parsons, Edinburgh, really nice talk, thanks very much.
Thank you.
A couple of things, you say you don't really see a change in the unit cell.
Minor changes, not huge changes.
But you do see a jump if you measure the temperature of the fluid. You do see a distinct discontinuity in the trend.
You mean by DSC, for example, thermal analysis?
No, I mean by crystallography. If you measure the cell, you do see.
Generally, you have 1 or 2 parameters. For example, A, B, or C. You have maybe B changing by 10%, 15%, an angle that is changing by 3, 4, 5 degrees, 10 degrees. So. Okay. That's how it works.
All right.
We don't need a lot of the difference, because most of the time also the symmetry of the system is retained, so it's really...
So that's where I was leading. So the symmetry is always maintained. So presumably these modes that you're looking at are always totally symmetric, are they?
Mm-hmm.
Yeah.
They are.
So
They are
you
most
don't-
of the time, yes.
Yeah. But
We don't have the assignments of all of them, so I cannot put my hand on fire, but yes, they should.
Okay.
The one that we already checked, they are.
Okay, thanks very much.
Well, thank you so much, Luca, for such a lovely talk. I'm sure you will be around and people can catch you anytime
course.
for the discussion.
When you
So
want.
join me in thanking Luca once again. So now we have our next speaker, and I'm glad and so honored to introduce him as he was my PhD supervisor in ICER Trivandrum, India, Professor Kana M. Sureshan. Welcome, sir.
avoiding solution-based chemistry because that's very complex.
So first, I would like to thank the organizer for giving me the opportunity to present my results, and especially Prof. Nomov and his team for the really nice job they do on the organization of this event. So my crystal here will not move, sorry. So I will just study crystals in thin films, so close to surfaces. And so it will really be related to polymorphs. So we have heard a lot of polymorphism also. So the outline of my talk. So here, first introduction. So I will give you some reasons for my study. So basically, I will try to convince you that my work is worth being done. And then I will show you the context of the study. So it's study of an API, pyroxenamide. And then I will show the results. So the thin film fabrication and the silfins of the different compounds. So the compounds alone, and then also mixture between the API and the additives. And then I will drive some conclusion. Okay, so to illustrate my work, I have picked, in fact, an example from our own research. So it's on this compound, so diprofilin, which is in fact an API, which is chiral. Okay, so whether you consider it as a racemic mixture or a pure enantiomer, you have, yeah, it's because it's, I have to. Okay. Yes. Yeah, okay, like this. So if you consider the compound as a racemic mixture or a pure enantiomer, so you have some polymorphs, so stable polymorph, racemic compound at the left, and enantiomer crystal at the right, E1, R1. But if you crystallize this compound, so from the melt, so yeah, maybe it's because I have to. Yeah. So if I consider so this compound, so you have those forms that are possible, but if you crystallize it so from the melt and then you cool down, then you have metastable forms, R2 so for the racemic mixture and E2 for the enantiomer crystals. Okay, but in fact these metastable forms are obtained only most of the time if you in fact put a cover glass onto your powder. Okay, if you do not have this cover glass, so you won't see these polymorphs. So this shows the effect of the surface on polymorphism. And what happens, in fact, is that you have, in fact, a transient polymorph that is called the PC, so the primary crystals, which is first nucleated, and then this one is in fact favored when you have a surface, when you have the glass, the cover glass. And then this one transforms into either the R2 for the racemic mixture or the E2 for the enantiomer crystals. Okay, so this shows that in fact the surface can have an implication on the polymorphic selection. Okay, so the core of my talk, it concerns this compound, pyroxenamide. So it's an API which is used for the treatment of tuberculosis. It has 4 polymorphs, so alpha, beta, delta, and gamma. And so if you want to see the stability, so alpha is more stable at room temperature, and gamma is the most stable at high temperature. And so some jobs that we did, if you crystallize this compound, so in solution, so we use spray drying, for example, in addition with an additive like dimethylurea or dihydroxylurea, in fact, you obtain form gamma at room temperature, okay? But then this can be stabilized for more than 3 years, okay? If you do not put these additives, you have form gamma, but then it converts back to the stable form alpha within a few weeks. Okay, so these are the 2 additives. And so other things on that. So we try to see if there is something like co-crystals with these additives or solid solution. We did not reveal either of those things. And also what interesting result that we have, so when you grow single crystals by co-sublimation, so PZA with DMU, for example, So you heat up, so you sublime, and then so you let the vapor crystallize. Then you see that with your additives, you have some crystals which are, free from defects here on the surfaces, compared than with a DMU where you have a lot of defects. So then this drives us to see whether there is something at the surface between, an interaction maybe which is just limited to the surface between the additives and this PZA. Okay, and so this is why we try to make some thin films of PZA alone and also with these additives to see the effect of the surface and maybe the interface between the additive and the PZA. So how the thin films have been made? So with the spin coating method. So it's a really simple method. If you know, you just have to you have a solution of your compound. You just drop it onto a substrate. So for us, it's just the glass substrates. And then, so the sample holder of the spin coating just spins at a specific speed and at a specific time that you can change as you wish. And then, so after evaporation of the solvent, then you will have hopefully a film here. Okay, so these are the different parameters. So we can change the solvent, so the volume of the solution, solution concentration. We tried several concentration, and these are the spin coating parameters. Okay, so you see here you have things that I call mixed solutions and also bilayer films. So in fact, it's two ways of making films of the mixture of PZA and additive. So the first one that I call mixed solution films is just, in fact, so you put the two in the solution, so in a 1:1 mass ratio, and then you just proceed with the spin coating procedure. And then the second one, so in here you do not impose anything on for the mixing. And for the second one, the bilayer, is just that you put first a film of PZA, so you do all this with PZA in solution, in a solvent, so in a methanol. So these are the conditions, methanol, okay. And then after you obtain the film of PZA, then you put now a solution of DMU, this time in a dichromethane, because normally PZA is not soluble in dichromethane, so not to dissolve the first layer. Okay, and then so if you want to check, this is, you see here, this is a glass substrate. You see the white powder is in fact your deposit, your film. And so all these films have been in fact characterized by standard characterization technique, so microscopy, so atomic force microscopy and polarized optical microscopy, X-ray diffraction, and also, when available, Graeme incidence X-ray diffraction, which is more sensitive to the surface. Okay, so the results. So this is just for PZA. So this is microscope and then AFM here. So if you see, you have some needle-like crystals for both microscopy. As you can see here, also you can with the AFM have the height profile and see more or less the height of this crystal. So it's less than 1 micrometer. And so it seems to be. You see that you have some bright spots here. So some zones where you have more PZA than others. In fact, this is due to the crystallization in solution, and due to here is just the square, which represents in fact the size of the AFM compared to the microscopy image. And then so here in fact this is a sample holder of the spin coating, and you see a pattern. And this pattern is in fact reflected on the images. And this is in fact due, so when we check the literature, this is due to some local thermal differences. So you have some cold zone and hot zones, and so you have local differences in supersaturation. So some points where you have high deposit and other one which is lower. Okay, and so if we check for the forms, so the solid forms, so here you have on top, so the light blue here is the Grisanti incidence X-ray diffraction of the film, of PZA film. And you see here you have one peak here, which corresponds to the gamma form of PZA. Okay, so when you're in thin film, you have gamma form of PZA, so the metastable form. And this is, in fact, reproducible for all the film and even whatever the concentration. Okay. So this is just a higher angle zone. And so for DMU, so you see that now the morphology of crystals is different. So you have some plate-like crystals, okay, which are also well homogeneous on the surface. In AFM, so you see the same kind of crystals. And so if you check out the height profile here, so it's here, so yeah, you have the height of this place, which is the thickness, which is more or less some hundreds of nanometers. Okay, so here you still have, if you check carefully, you have some blurred zones. So you have the same effect as for PZA, so some cold zone and hot zone, so somewhere you have more PZA than at other positions. If I check for the polymorphs, here, so you have DMU form 1, so this is the reference of form 1 of DMU, and you will see the peaks of this form. Okay, so one thing which is interesting interesting in these films is also if you check the stability of these films. So this is day 1 of spin coating of those films, okay, and then this is day 6. So between the two, you see that you have the crystals which has vanished. In fact, this is due to the DMU is known to be hygroscopic, and it can be even deliquescent. That means that it can even dissolve in the water. It has uptake, and in thin film, this effect seems to be even enhanced. Okay, even if normally it is wet, of course, but this is really fast for this behavior, this effect. Okay, so now these are the mixtures that we wanted to see. So the first one is the mixed films, so where you mix all together and then you perform the films. Here you see that there is some kind of segregation in the crystals. So if you check this microscopy image, so with DEU and PZA, 1,1, you have the crystals, so the needle-like crystals for PZA, the very small crystals here, and then here this deposit is more like the DEU crystals, so some kind of segregation. So yeah, maybe there is something. Okay, so in fact it is also due to the solution crystallization. If you think a bit, in fact PZA is not really highly soluble in the solvent. So this is methanol, for example. So the solubility of DEU is more than 10 times higher than the solubility of PZA. So that means that in the zones where you will have that are called the cold zones, then you will have preferentially crystallization first of PZA. So this is why, in fact, you have this kind of segregation. It has nothing to do with some intermolecular interaction between DEU and PZA. And then, so for the bilayers, so bilayer films. So here, in fact, so this is the first layer, so of PZA deposit, then XRD diffraction. So we clearly see that we have PZA gamma form as we obtain, and then we put the second layer and perform X-ray diffraction, and then you see that here this peak has vanished. We only see the peaks of DMU. So normally it should not, because we choose dichloromethane because PZA was not soluble. But here we are in thin film, so maybe we have a partial dissolution of the PZA so that we cannot see anymore this compound. And then we performed AFM to see what happened for this kind of films. And what we observed, so here it's, you remember it was the same morphology of crystals that we see for DMU films. So of course, because they are on top. And the most interesting thing is when you check the height profile. So here you have a 3D map of the whole image. So you can see here the height evolution. And if you compare with the DMU films that were so spin-coated without the PZA below, you see that the roughness is much higher for those films. So here it's the same scale. So you have here a roughness which is a matter of some hundreds of angstroms, so tens of nanometers, while here is hundreds of nanometers. So maybe it's an effect of the PZA layer which is beneath, but okay. So I will just finish here with this result. So we can obtain crystalline films of PZA, also of the additives and also of the mixture. For PZA, we see that form gamma is always obtained, so it's quite interesting because it is a metastable form. Of course, we have to check for the stability of this form. Does it stay for a long time? So this is one of the perspectives. And for the specific interaction at the interface, we have not the solution yet, but we do see an effect, okay, for the bilayer films. So of course, what we want to do is to continue those investigation, notably on those bilayer films, and why not using DEU, because it's less hygroscopic, so it's easier for the manipulation of the film, and maybe use some other techniques like X-ray reflectivity that can give you information on your different slabs, your different layers. And this is also an idea that we have, is to try also to see high surface area like nanoporous particles, and to check if we have the same behavior in polymorphism. Okay, so these are just the people that have worked on this project. Collaboration with TU grads for the X-ray diffraction, Bayesian incidence X-ray diffraction, with the founders, and I thank you for your kind attention. And
thank you so much, Professor, for such an interesting talk. So now we invite few questions.
Please, when you talk about metastable form, for which kind of polymorphs you're talking about, monotropically or enantiotropically related in terms of temperature? What is the transition temperature? Thank you.
So for PZA, in fact, the 4 polymorphs are enantiotrophically related. So we know that so from alpha it's room temperature, and then gamma it's at high temperature, and you have an enantiotropic relationship.
So I have a clarification. So did you use any other method for making the thin films apart from spin coating?
Yeah, so I have used mainly this one, but you have other ones. So you can have drop casting, which is more simple, just to drop your solution and then let it evaporate. And one thing that would be interesting for us, because for example, PZA sublime very easily, it's to use some vapor deposition techniques. This can be interesting because you can control the thickness and control everything.
Did you try the reverse of depositing the PZA on the DMU film?
Yeah. So this is more difficult because, in fact, PZA is DMU or DEU are soluble in a lot of solvents. So, in fact, if you deposit DMU first and then you deposit the PZA layer, you can dissolve, in fact, the DMU layer which is below. Sorry? No, I have not tried. And I hope to try it because in TU grads they this kind of approaches. So this is something we expect to do.
So well, join me in thanking Professor Babode for such an interesting talk.
Thank you.
So with this, we conclude the first session of this conference, and I have some important announcements. I request all the speakers of this session to please assemble here right after this for a photograph. I promise we won't take much time because I'm sure everyone must be hungry. And apologies to the chair of the next session for extending the session a bit because of the technical glitches. And we expect everybody to be back after lunch by 1:50, so enjoy your lunch. And the winners for the surprise gift, we have the gift for you here, so we'll distribute it. Thank you.
should start. I'll let the last people get their seats. So I'm Graeme Day, chairing this session. I'm from the University of Southampton. My co-chair, Luca Grisanti from Zagreb, is going to be co-chairing with me. So we have the next 20 minutes to give a bit of an introduction to crystals and computers. We're going to share the time and then hand over to our exciting list of 5 speakers. And I think we've got quite a nice sort of variety of stuff going on. So I'm looking forward to this session. So had a little bit of a think of what to do with the time, I guess, to introduce it. And I thought just sort of maybe to put things in perspective from my personal point of view, at least for the first half, in terms of where computers come in to what we're doing, right, and what we're talking about at this conference. One of the positive sides of lockdown is that you have to keep children entertained, I guess, and you get to know them. And I actually got back to growing a crystal, which I haven't done in about 20 years. So I grew some citric acid crystals with my daughter, so I thought I'd show that off for anyone who doesn't believe that us computational chemists can do it. Citric acid is pretty easy, but yeah, let's pretend we have a crystal structure and then we have a nice powerful computer, and what do we want to learn about what's going on in between the molecules in that crystal structure. One of the big things, I guess, that a lot of us are academics, and what we're interested in is just that fundamental understanding, right? We have a structure. If the crystal looks like this, we can probably get a structure out of it, single crystal diffraction. So what computers allow us to do is really start to pick stuff apart. I mean, we can do that just by visualizing a structure, but what comes in with the computer is starting to quantify the stuff that we see on the screen when we visualize things. So that's one side of things, and that's sort of ongoing, is can we just really make sure we understand why those molecules have come together in the way they have, how they're interacting, why the molecules have chosen that structure, and how it impacts on properties. So that's the second part of things, right? Once we have these structures, the list of computable properties now is really growing, right? And that's quite exciting, because there's now a database of over 1 million known crystal structures. That's growing daily. And so if we can start to compute properties from these, then the computational work can really start to build up our understanding of structure-property relationships, okay? Again, complementing what we get from experimental work and building on the experimental work. But it can add a lot, I think, and we'll probably see that through this afternoon session. So those 2 arrows were going out of the crystal structure. We have a crystal structure, how we can pick it apart, or how we can start to predict behavior of properties of that crystal from the structure, but sometimes we might not have a material that's nice enough to get a structure. Maybe we're thinking about a molecule that we haven't even made yet. So there are arrows going in as well, where computational work, and this is really building up in recent years, starts to help us out. So sometimes it's just sort of helping to piece together parts of the puzzle. We might have some experimental information. Something that's really been growing and getting more powerful year by year is the topic of N-bar crystallography. We're going to see that in our final speaker's talk. And what's, I think, critical to that as a method that's starting to work is that we have quite powerful computational methods to go and sort of allow us to propose structures which can be confirmed or refined using things like solid-state NMR. Okay? And that extends to other methods. This is the type of approach that's been used from powder X-ray diffraction as well for many years, electron diffraction, etc. So computational work can help us piece together a puzzle. And as I already mentioned, maybe we don't even have a material, we haven't even decided to make the molecule yet, but we want to think about how a hypothetical molecule is going to crystallize, and that's where structure prediction starts to come in and becomes a bit of a playground where you can, before you've gone in the lab, start to, if you trust the methods, start to I guess, see how hypothetical things are going to behave and crystallize. So that's sort of the toolkit down here, I think, of the sort of things that we try to do with computers. I probably missed things off because this is my own personal perspective. And so this is maybe the modern crystal engineer who has a lab coat on, so probably grows crystals as well, but also spends time in front of the computer understanding things, what they've grown, predicting things before they've grown them. So yeah, we're trying to understand those structures, maybe control structures. Often people talk about things like control of polymorphism, especially maybe in the pharmaceutical industry where you really need strict control over the solid form, and design and discovery, of course. I put them in together because I guess depending on your personal viewpoint, whether we actually design chemical systems or whether we just discover things that are latent and structures that are out there waiting to be discovered is maybe a sort of slightly philosophical debate. But anyway, this is where I think things start to help us out. It's always good to have these sort of plots to show that a field is growing, right? So I did a quick Web of Science search. And this is not meant to be comprehensive. I mean, the number of relevant papers is surely more than 750 or so. But I just did a search on the fields of crystal, organic, and computation in Web of Science a couple of days ago. And you can see this is about when I was doing my PhD 20 years ago. And the growth up till nowadays it shows that these methods are being used more and more, okay? So I wanted to spend a few minutes maybe picking apart a little bit more some of those things that I talked about in terms of how we use things. Crystal structures are great. I find them very useful for even in the teaching setting of teaching undergraduates about intermolecular interactions, because looking at how molecules arrange themselves in a crystal structure, laying on top of that some calculations to show them sort of relative strengths of stuff like electrostatics and polarization, and telling them that, okay, you got taught in school that dispersion's weak, but no, it's not weak. It's actually quite strong, often stronger than a hydrogen bond sometimes, and telling them about those magnitudes of interactions, right? And it's useful to pull them out of crystal structures because you can show them. You can say we can actually pretty much see where the atoms and the molecules are arranged in a crystal structure. And so these are how molecules are actually interacting. You can also say, okay, what's the difference between a hydrogen bonded interaction or a pi-pi stacking? And that's that fundamental understanding. So we have some computational methods. We have lots of computational methods sort of at hand now that allow us to, from a structure, pick things apart, start to quantify those interactions that we see, right? If we look at this structure, we can see that pi-pi stacking is important. We can see that hydrogen bonding is important, but it allows us to put that in quantitatively relative importance in terms of the overall lattice sums, as Craig was talking about yesterday when he was referring to Kitty-Gorodsky's sort of groundbreaking work. So we build up our understanding of intermolecular interactions, and that allows us to put together various models for the energy surface of what's going on. So this is maybe what an energy surface looks like of the energy of perhaps a crystal structure against some of its structural properties. Okay? And you expect it, well, the crystal structure to be roughly at a minimum, and its behavior around that can also be informative, right? So these numbers and also known structures and maybe sometimes experiments can inform the buildup of some model potentials that we have to now start to explore things other than just the interaction energies in a static crystal structure. So we have that model potentials built up, be it the atom-atom potentials, Kitty-Gorodsky and Pertzin's early work, or the modern stuff like the DFT methods. And what can we do with them, right, beyond the static structure that we have from, say, X-ray crystallography? One thing is we can start to help interpret experiments. I put this as an example because this is something I worked on quite a few years ago, and it's been mentioned already in our meeting, things like the lattice vibrations. Okay? You can get spectra. In this case, it's infrared terahertz spectra. but we can also do this with the Raman spectra that Luca was talking about in the last session. And the modeling and the understanding of the shape of the potential energy surface around that minimum, around that crystal structure, can tell us about now the dynamics of molecules in crystal structures. So we can start to interpret what's going on with each of these peaks. Okay? And you saw the power of that then in terms of looking at the phonons and how that might help us understand, say, transitions in structures. So with that, we can now start to build up those property prediction understanding, and it's because we have a model which models the surface away from that minimum. Okay, so I've stolen a couple of pictures from people's graphical abstracts, so we're going to hear about things like crystals that bend and crystals that blow up, apparently when you hit one with a hammer, which doesn't seem wise for an energetic material, but anyhow. Thermodynamic properties, so free energies, of course. In the last few years, some of the work has been moving away from just static energy crystals and static energy calculations towards free energies with the entropy, so we can understand what happens with temperature and stuff, reactivity, etc., response properties. Okay. So this is where things are fitting in. So now I change that picture. If we have a model potential, which knows how to calculate the energy of a structure, given structural coordinates, then we don't have to stick to the local region of a crystal structure. We can think more globally. So if we couple up model potentials with methods for how we might explore, walk around, or sample the energy surface, then there's a lot more exciting stuff we can do as well. I put structure prediction top because that's the area I work in, so that's top of my mind. But other things that sort of need to know a little bit more globally about the energy surface, things like phase transitions, how do we get from one crystal structure, one polymorph to another, and how that might impact on, well, maybe a crystal jumps when that happens. Nucleation also needs to know the energy surface as a function then of crystal size, okay? And so then the surface area comes in, and growth of these crystals. Okay. So this is sort of my mental picture that I started to put together as I was thinking about introducing the session. Before I hand over to Luca, I'll just say a few things, I guess, about the tools, because I was glad to see Kirigorodski's book come up. I was lucky enough to find a library that was discarding this book. All right, they were throwing it away, so I saved it, and I have that on my shelf, because it's hard to get these now. But computational work, you can think almost started before the computers. If you look in his book, Kirigorodski talked a lot about actually thinking about how molecules are going to pack with a mechanical setup, right, where you could fix lattice dimensions and relative orientations and space groups, so space group symmetry operators with this mechanical setup. So we could think of how do all of this, and he started to really understand, I mean, why do we have the space group distributions we see in the database? A lot of the understanding came before we even needed computers, just by, we can do it nowadays, by packing things together, building molecules and packing them together, right? But also, oh, and I put this in there, I forgot about the quote. I dug this out because something interesting that he said, if you go back and you read this 1973 text, is that, okay, with a mechanical setup like this, it wouldn't really be possible to predict structures completely because you would never be able to sample all possibilities of those symmetry operations, of the lattice dimensions, of the relative orientations of molecules. So he sort of, with what they had in hand in the 70s, sort of ruled out, I guess, complete ab initio structure prediction. But then the atom-atom potentials come in. Okay, a lot of great work going through the years with Kirigorodski and Pertzin and Williams and lots of people pitching in on parameterizing these. And then it starts to lay things down in terms of a way that we can put it on a computer. Okay, so 10 years or so later, although Kirigorodski said, okay, you couldn't sample all ways that a molecule could pack, Jabchenko does this with benzene, right? He puts benzene in a box and samples symmetries, samples unit cells, relative orientations, and he finds known structures of benzene as the lowest energy structure with model potentials, okay? Now, benzene's popped up again a few times, right? People have come back to benzene and sort of kind of claimed breakthroughs in computational methods of being able to model benzene accurately, but actually we could predict its structure very early on, okay? And there was really great work happening with the atom-atom potentials. Aurora mentioned this paper, okay? So 2008, I think. Marcus Neumann, I guess, drove a lot of this work. of parameterizing dispersion corrections to DFT, specifically for molecular crystals, and put this into the blind test of crystal structure prediction context, and they got everything right. Okay, so in a way that wasn't the first time we could predict structures, but it started to make things more reliable, okay, and maybe more generalizable to things where the atom-atom potentials weren't working. And people asked questions also yesterday about machine learning. Okay, and that's coming in, the number of papers we see of people applying machine learning in various contexts. Maybe it's just taking an arrangement of molecules and developing some machine learning method to predict the energy, or maybe predict the energy of a whole crystal structure. It's looking quite promising, kind of in a way of shortcutting the cost of what's up here, right? But it's funny because when these methods come in, sort of 10, 15 years ago, the atom-atom potentials sort of went out of fashion, and people sort of didn't use them as much because you could do DFT now, so why not just do DFT? Now people are doing machine learning potentials, which are essentially generalized force fields, and it's in fashion again because it has a new name. So it's interesting. Things come in circles, I guess. There was the question about the protein structure prediction. I don't think we know if that's a breakthrough that's going to translate into our field. I suspect not. Proteins, there's a lot more that goes on in terms of analogy. Similar proteins pack or fold in similar ways. Our exciting aspect of work is that similar molecules do completely different things very often in the solid state. And so at least the approach that they took for AlphaFold, I don't think will translate over directly to us. I'm going to hand over to Luca now, who's going to tell us a little bit more about it.
Hi everyone. Yeah, very quickly, I just wanted to apologize if some of you has already saw this type of pictures, but I just wanted to take advantage to stress the fact that when we move from 0 Kelvin, so from structure, and we want to describe phenomena that have dynamical properties, we need to think about time scales of the simulation as well as sizes. And so each computational techniques that you might want to use has a typical ranges that you can achieve of times, of length of your simulation. And of course, there's an accuracy that corresponds. So there's a cost you have to pay. And so I just try to kind of summarize all the available techniques in the field and how they've been used to material science, especially. So, you know, we have kind of boundary here where the electrons are treated. So we have DFT and more advanced technique based on wave functions on one side, very accurate, but very limited possibility in terms of size that you can cover, and time scales is so you can just be able to compute one single point structure. And then on the opposite, we can get rid of electrons and cover much longer, so nanosecond and microsecond scales. So just it. I don't think I need to, who am I to say what DFT is or classical potential. Just maybe worthy to stress that in DFT has been used a lot in the community. There's still a lot of point that needs to be improved. So correlation, dispersion, localization, there's an open problem in DFT. And on the other side, we have classical potential method being used a lot. You can explore time scales, but of course you can't predict electronic properties because you don't have true electrons in the model. Graeme has mentioned machine learning. So machine learning can be placed somewhere in the middle. So you can use DFT to build your machine learning potential, but it will be good for forces and energy. It will not be good for electronic properties, for instance. So then this is also to keep in mind. It depends in the end, actually, what is the type of problem we have, right? So if we want to compute optical properties, we would rely on electronics. So we would rely on something like DFT. If you want to describe nucleation problems, you probably need to cover such a large time scales that and space scales that you probably need to look at something that's closer to a classical potential. Crystal structure prediction is something somewhere in between. So one has to draw the conclusion based on the cost and availability of the methods. And just one final slide, so that stresses what are the points also in the talks we are going to listen in this session. So one, it's about the connection. One strong point is connecting microscopic and microscopic. So computers help us to be like a lens that we can look at the detail of the structure, understand the different motifs that build up crystals. And so the predictive value as well, and the comparison with the experimental data are very important element for modeling. And so the choice of the method you want to do, it's of course dependent on the problem. This is a trivial conclusion, but we look forward now for the talks before and after the coffee break. I lead again the word to Graeme, so he can introduce, and thank you.
Thank you, Luca. And so we'll move swiftly on to our speakers. First speaker being Carol Morrison from the University of Edinburgh, who's going to tell us about explosive materials. Yes.
Yep. Oh, that's us. We're good. We're good. Right. So I would like to begin by thanking Panche for putting together a really excellent program for the week. Thank you very much indeed, in a beautiful place. I have the opposite problem to the last speaker from this morning's session, in as much as I'm too short. Too short. Sorry, the microphone. I don't think the microphone's working. Is it okay? We good? Okay, cool. Yeah, I'm too short to stand in front of this podium, so it's like the disappearing speaker. Now you see me. Okay. So, and I'm a pacer. I wander. So that's not for me. Okay. So what I want to talk about today is the rational design of energetic materials with tailored impact sensitivities. So before I get into my talk, I just want to quickly go over my acknowledgements, because I want a massive shout out for Adam Michalchuk. So Adam, give everybody a wave. So this work was work that Adam and I started about 5-6 years ago, something like that, when Adam was a graduate student with myself and Colin Pulham. The other names there are students that have been involved with the work, and I'd like to have a special shout out for Cameron as well. Cameron, give everybody a wave. So Cameron is a PhD student with Simon, but I pulled second supervisor privileges about 2 months ago, didn't I, to bring you in on this work. Right. So introduction to energetic materials, just so that we're all on the same page. We are talking about crystals that go boom, basically. Formally, there are 4 different classifications of energetic material. We have explosives, propellants, pyrotechnics, and gas generators. So think about the airbags in your car that keeps you safe if you're in an accident, for instance. Energetic materials can be initiated in 4 different ways. They could be initiated through mechanical insult, so that's impact, friction, spark, or heat. And impact is in red here because that's the topic of today's lecture. And it's also an area where safety is paramount, so safety takes precedent over performance. And if you're working with inherently dangerous materials, you can see there's also an argument that computational modeling must be able to help here. So just so that we're clear, impact sensitivity, we are literally talking about if you're going to hit an energetic material with a hammer. They dress it up a little bit in terms of this ball hammer apparatus. So the dead weight is here, it gets raised up a particular height, your sample is in there, and you're working out the minimum energy required to induce detonation, okay? So it's supposed to be a binary outcome, it's supposed to be go or no go, but unfortunately it's often more like shades of grey, right? You're looking at a white powder that's now become a little bit grey looking, and you're trying to decide, has that gone? Or is it not gone, right? And it's also, so it's subjective, it's not a binary outcome, and the results vary depending upon temperature, humidity, sample purity, crystallinity, operator experience. And also, given that this is one of the main safety tests that they will use for energetic materials, they have to repeat this experiment multiple times. So you're using milligrams every time you do the fall hammer test. And because you're repeating it 15, 20 times, you're almost getting up at gram scale quantities before you can assess whether or not the material is safe to handle. So with all of those kind of crosses, you start to think, is there an alternative way? Is there another way that we can do this sort of safety testing? And if we can, instead of dealing with things on the gram scale quantity, if we can start from the crystal structure, so if you like a single crystal of your energetic material, and do something clever with DFT, right? First principles calculations, burn through a lot of high performance compute time, and then take the output from those DFT calculations and put them through some sort of model, okay, devise some sort of model that will allow you to be able to predict from the crystal structure what the impact sensitivity is. In other words, is this an energetic material which is going to be very easy to initiate, so just the slightest tap will induce detonation, or is it a material that actually will take another energetic material to detonate, to induce a shock wave, to make that material go? Because that's the order of magnitude that we're dealing with here. Now, it goes beyond just, can I go from the structure to predict what the impact sensitivity is, because if you can link structure and property together, then you can push it the other way as well. In other words, say I'm working alongside an experimentalist who's making new energetic molecules, and they only want to make molecules that are going to be safe to handle because they want their PhD students to have all 10 fingers at the end of their PhD project. Can you work out, knowing that you're looking to make an energetic material that's going to be hard to detonate, hard to induce initiation through impact, can we work out what sorts of structures those molecules should have? So that brings me to my talk outline. We're going to start by going over the background to the theory of impact initiation. That will then allow me to be able to introduce the vibrational up-pumping model. Spoilers, we're going to hear a lot more about phonons. So we've already heard quite a lot about phonons in the conference so far. This is another phonon talk. Then once I've gone over how our up-pumping model works, we'll go on to applying it to two different examples of energetic materials. So the first one is finding replacements for lead azide. So lead azide is the primary explosive that's used. It's used in blasting caps. Very, very easy to initiate. The shock wave from lead azide is then used to initiate other energetic materials. But it's got lead in it, okay? So that's a problem. We're looking for replacement primary energetics that are not so toxic. And then I've got a family of tetrazole derivatives that we've looked at just in the last year, and we're looking to be able to identify, can we link from the structure to whether or not that energetic material will present as a primary energetic? Again, that means it's very easy to initiate through mechanical insult, or is it a secondary energetic, much harder to initiate? So that's the outline. Okay, so onto the theory of impact initiation. We know that initiation proceeds via a shock wave that travels close to the speed of sound. The energy is then picked up by the phonon acoustic modes. So we've heard about that already today. So the acoustic modes, for those of us who didn't get to go to condensed matter physics classes at grad school, acoustic modes, those are just like your translational modes of vibration. So it's the way, if you think about a longitudinal wave, okay? So we've got two types of wave. We've got the transverse waves and we've got the longitudinal waves. So the acoustic modes are the longitudinal waves. So in other words, it's your molecules in your unit cell that are translating along plus x, minus x, plus x, minus x, plus y, minus y, plus z, minus z direction. Okay. Now, the energy from the mechanical insult gets passed into these acoustic modes and is then immediately delocalized throughout your unit cell. Now, I'm at pains to point out this is before we get the buildup of hotspots or material compression or fracturing or anything like that. So it's the very first response that the material will have to that mechanical insult. Right, so I've drawn out the vibrational energy levels of a crystal lattice on a y-axis scale because I want you to think about this as being like a ladder, okay? So I've already said that the mechanical shockwave energy is going to come in and it's going to deposit that energy into those acoustic modes. Now, those acoustic modes are sitting right at the very bottom of the vibrational ladder, okay? So they're the lowest possible wave number. Now, I've then drawn a big red block there up as far as a particular parameter called omega max. All of the modes of vibrations that roughly fall from 0 up to about 200 wave numbers, plus or minus 50, are referred to as being the phonon bath. Okay, so that's a phrase we've heard already today as well. It's called a phonon bath basically because we have lots of modes of vibration that are really, really close together. So it's almost like we have a continuum of vibrational states. Okay? So because they're all kind of overlapping and joined together, it means that that mechanical shockwave energy, which gets deposited into the acoustic modes, is then immediately spread over all the other modes of vibration that occur up to the top of omega max. Omega max then marks the transition from being a phonon type mode, where it's really the molecules are rigid bodies and it's the space between the molecules that are changing. So these are all translations, rotational type vibrations. Once you get up past omega max, you're then into the molecular vibrations. So that's where you get your angle bends, torsions, bond stretches, and so on. So molecules are rigid bodies down here, molecular based up there. And I've drawn that in as red because this is now hot. Hot, hot, hot. We're talking about thousands of degrees Kelvin in terms of the vibrational motion of the molecules in that region. So we've got a really, really hot phonon bath. That energy has to dissipate. It has to transfer through the crystal. And how it does that is it works its way up into the molecular vibrations. Okay? It can't go down because it's already at the bottom of my vibrational ladder, so it passes up into the molecular regions. So we then define a vibrational up pumping window that lies between omega max and 3 omega max. And the way we are able to transfer this energy from here up to here is through vibrational up pumping. And again, we've heard about this already today because people were talking about phonon scattering. So what happens is we can take 2 molecular vibrations from down here, so Q and Q prime, or Q prime and Q double prime rather, and they can scatter off one another, and then they can create a new phonon state, which I've labeled big Q, which lies within my vibrational up pumping window. And if the 2 phonons are identical to one another, then the big Q peak that I will make will just be double the frequency of the original vibration. And to borrow a term from vibrational spectroscopy, that should remind you of something called an overtone mode. Okay? So if both of the modes of vibration are identical, we create a new vibrational state, which you can think of as being a bit like an overtone vibration. If the 2 modes of vibration are different to each other, so say it's a mode of vibration from down here and another one from up there, then the new Q peak that we make would be the sum of those vibrational modes, and that's a bit like a combination band from vibrational spectroscopy. So that's the mechanism by which the energy from down here passes up through the vibrational rungs of the ladder to be able to transfer that shockwave energy into the molecular vibrations. Okay, so in terms of our workflow, that's our recipe up on the top right corner. And what we're calculating using density functional theory are the vibrational densities of states. So now I've taken my vibrational ladder, if you like, and I've turned it round on its side. So wave number is now along the x-axis. So the grey that you see, that's what we're calculating from first principles. So once we have the modes of vibration, we can look at the eigenvectors and we can work out where omega max lies. So there's an example image of what one of these phonon bath vibrations look like. So as I say, these are all translation, rotational type vibrations. And then we can identify where the 3 omega max limit will lie as well. And as I say, all the modes of vibration that lie within that up-pumping window are molecular mode based. Right, so we use density functional theory to get us the grey density of states plots. We then wrote an in-house code using some Python to create the vibrational up-pumping effect. So this is giving us this pink envelope, which is called the 2 phonon density of states. So that pink envelope is all the different combinations of the phonon modes from down here scattering off each other to then create that envelope. And then quite simply, we then project that pink envelope onto the grey peaks underneath, and then we integrate. Okay, so integrating where the pink and the grey overlap gives us a number that's then a representation of how efficient that molecular crystal is at channeling that shock energy into the molecular vibrations. So this model then allows us to be able to answer questions about why does one particular energetic appear as a primary, whereas another appears as a secondary. So I've got 2 energetic molecules here, HNB and TATB, and I'm aware right up at the back of the room you probably can't see the difference between them, but HNB has 6 NO2 groups around the ring, whereas TATB alternates between NO2 and NH2. And what I want you to take from this plot is HNB is very efficient at channeling that shockwave energy in. You can see we've got a large 2 phonon density of states peak, whereas TATB is much less efficient. So you can see the pink 2 phonon density of states envelope, which is drawn on the same scale, is much smaller. So if I was to go back to my analogy of being a ladder, you can see that HNB, the vibrational rungs on that ladder, are just in the right place to be able to be much more efficient at channeling that energy into the up-pumping window, whereas this TATB vibrational ladder is not the sort of ladder you would want to climb up, okay? There are gaps in the rungs, which means that the energy is not so efficiently channeled into the molecular motions. Right, so, as I say, taking where the pink and the grey overlap gives us a number which we can then plot on a graph, and as every good scientist knows, if you only have 2 data points, you can fit a perfect straight line, and your work is done. No? Okay, so let's add on a few more data points. So, and also, before I add on the extra data points, remember, along the x-axis here, I've got impact sensitivity, so that's an experimental observation. Along the y-axis is my prediction. Okay, so that's from our up-pumping model. So I've got 2 data points, a perfect straight line. Let's add on another 3 data points, and that's not bad. Okay, if you think about what we're doing, this is a first principles model to be able to predict how easy it is to induce initiation in a molecular crystal by hitting it. Okay, that's not bad. Right, full disclosure, the data points that I've got there, each of those took a solid month on a high-performance computing resource to be able to generate. And the reason for that is it's from full Brillouin zone sampling. So the density of states that I've got in this inset here, the blue, is from the full phonon density of states. Okay, so what do I mean by full Brillouin zone sampling? Well, if I've got my unit cell here, imagine a mode of vibration where all the molecules in the unit cell are doing that. Okay? Now that unit cell is going to be surrounded by another unit cell here and here, here and here, and front and back as well. If I'm allowing full Brillouin zone sampling, then the same molecular vibration appearing in the unit cell next door may be in or out of phase with that one. Okay, so it could be doing that. Okay? And all sorts of combinations. What about the unit cell next door? Is it in or out of phase with my original unit cell and so on? So if you allow for all of those possible combinations, that gives you what's called this full Brillouin zone sampling. Now, that takes a long time to compute. So instead of doing full Brillouin zone sampling, the question is, could we get away with doing gamma point sampling only? And in gamma point sampling, that means that all neighboring unit cells are exactly in phase with one another. Okay? So that's what my black line is. So if you look along the x-axis here, so there's my phonon bath, so you can see I do lose quite a few phonons, densities, by dropping down to the gamma point only, but my molecular vibrations are more or less exactly the same. So if I was to drop down to gamma point sampling only, each of those data points would take less than a week to be able to compute. So what do we get? So dropping down to gamma point sampling only, so it's a similar looking line, except it's now a curve. Okay, my y-axis has dropped down in intensity a bit, so it goes up as far as 25 arbitrary units, whereas before I was up at 45. Okay, so that makes sense because I've got less phonons to scatter. And yeah, instead of this nice, almost straight line, I've now got a curve. However, as I say, each of these data points were substantially quicker to calculate. I can still pick out my primary energetics, and I can say that HNB is more impact sensitive than beta HMX, that's correct. And I'm clearly separating out my secondary energetics as well. Now, because I'm now on a curve, what I'm less able to do is to be able to say, is NTO actually safer, or rather, is TATB actually safer to handle than NTO? And answer is probably not, because I'm flatlining at that stage. So I'm going to gamma point only. I've sped the calculations up quite a bit, but now I'm kind of reduced down to saying, is something appearing as a primary energetic or a secondary? But it does then allow you to add in more data points. So if I had bigger unit cells, so it's not just about being impatient waiting for the calculations to finish, but if my calculation model is more streamlined, then I can start to look at larger and larger unit cells. So I've got a few more data points in there, which were larger unit cells that I wouldn't otherwise be able to calculate if I was looking at full Brillouin zone sampling. So our vibrational up-pumping model is doing a pretty good job at being able to order the relative impact sensitivities of our energetics. So we now have a model that we can start to unpick to be able to say, why does something present as a primary energetic? Why does something else present as a secondary energetic? So we can start to unpick the model to look for clues. But it shouldn't come as any surprise, this is all going to come down to resonance. So it's all about having the right peak in the right place to be able to channel that shockwave energy towards the molecular vibrations. Okay, one other thing that I've still to tell you about, and that's there's a very special region on the phonon density of states called the doorway modes. They lie between 1 and 2 omega max. And the reason why these modes are so important in here is there's actually a third vibrational up-pumping pathway that I haven't told you about yet. And that is, in addition to picking up 2 modes of vibration that lie in the phonon bath, we're also permitted within the anharmonic approximation scattering model to pick up modes of vibration that lie in here as well, okay? And that's really important because you can see the more modes of vibration, that sit within this region of the spectrum, the more likely we are to produce a much stronger two-phonon density of states. So if you look at the number of modes that I've got in the doorway region for HNB and contrast that with TATB, we can start to see why does this one do so poorly at channeling that energy into the molecular vibrations. So we can come up with a number called the doorway density where we simply integrate out the number of peaks that lie within that part of the spectrum, divide it by the total density of states, so that goes all the way out to 3,500 wave numbers or so, and multiply it by the size of that window. So it just gives us a metric that allows us to say something about, is it a dense doorway region or a sparse doorway region? So if we plot out again, so I've got the black dots, that's the up-pumped intensity peak, so you've seen that already. The blue squares now, that's the doorway density for each of those energetic molecules. And you can start to see there is a loose correlation between the two. Okay, so a more dense doorway region, you're more likely to be presenting as a primary energetic. And that's really important because that's really the first clue that we're able to offer back to the experimentalists to say, if you are specifically looking to design a primary or a secondary energetic, you need to think about vibrational spectroscopy and you need to be thinking about the window roughly between 200 and 400 wave numbers. Right. We can unpick it a little bit further. So here's beta HMX. There's its density of states and its two-phonon density of states. We can pick those eigenvectors apart to be able to say what modes of, or what bond stretches are active in those eigenvectors. So we've analyzed the eigenvectors to say, is the CN bond, the NN bond, or the NO bond active within those regions? And you can see that the CN bonds and the NN bonds all vibrate across the up-pumping window, whereas the NO bonds not so much. Okay, well, why is that important? And the reason for that is we can take it all the way back to be able to calculate the local force constants. So the local force constants is a direct measure of the strength of those bonds. And so you can see that our two weakest bonds in our molecule are active in the up-pumping window, whereas the NO bond, which is much stiffer, much stronger, is not. Okay, so there's another clue to give back to the experimentalists, that you want to have weak bonds that are vibrating within that region to be able to make a primary energetic. Right, so that's the up-pumping model. It's now time to apply that to two test cases. And yeah, to me, the beauty of having a predictive model is that you can start to understand the why. So why does one particular energetic appear as a primary, whereas another appears as a secondary? And if you can do that, you can start to think about making materials that are specifically tailored towards those sorts of properties. Right, so two test cases to talk you through. The first one is to find replacements for lead azides. So as I say, this is the most widely used primary explosive, but it's got a big old heavy metal in there that affects all stages of manufacture, storage, processing, use, and disposal, and so on. So there's a big push in the energetics community to replace lead azide with another energetic that doesn't contain a heavy metal. So one of the leading candidates for that is a copper nitrotetrazolate, which goes by the Montclair DBX1. But there's a couple of problems with it. So the first one is the synthesis is not at all straightforward. They don't really understand the mechanism of formation either. And it's really, really pernickety on the purity of the compounds that you start. So the textbook synthesis for this compound is you start with the sodium analog, and then you react it with these things. I'm not a synthetic chemist, I'm not pretending I know what they do, but apparently that's supposed to swap out the sodium for the copper. Now, depending upon the purity of the sodium species, however, you might actually make a completely different product. You might make this one over here, okay? So this one over here is the copper chloride form of nitrotetrazolate. Here's its crystal structure. I'm calling this DBX2 because that's too much of a mouthful, and if they're calling that DBX1, I'm going to call this DBX2. Now, it's thought that this is the first thing that crashes out in solution and that this actually seeds the formation of that. So over the course of time, you're going to start with this and then you're going to end up with that. Now, bearing in mind, this is a primary energetic. If you look at it funny, it will explode, okay? And this impurity that you're effectively starting with is even more dangerous to handle than that one, okay? Now, this was only reported back in 2020, but in the US, they're already talking about scaling up this compound. So scaling this up to an industrial scale, and yet the textbook synthesis would have you making this first, which is even more dangerous to handle. So from a computational perspective, there's a couple of questions that immediately need to be answered. First of all, what is it about lead azide and DBX1 and DBX2 that make them primary energetics in the first place? So our vibrational up-pumping model should be able to give us clues for that. And then secondly, why is this guy so much more impact sensitive than that one? Right, so here's how our vibrational up-pumping model performs. So you can see we're correctly predicting everything to be a primary. It's way up at the top of the graph. And moreover, we're also predicting that DBX2 is more impact sensitive than DBX1, so that's really good. So let's dig into the model then. So here's the vibrational up-pumping windows. There's our 2 phonon density of states. And the first thing we see is that we're getting a really pronounced 2 phonon density of state envelope for these 3 compounds. So if we follow the path that we were looking at before, the first place that we would start to look on the density of state spectrum is there anything special going on in that doorway region? So when we look at the doorway densities for this, the answer is kind of a mixed, well, kind of yes and no. So DBX2 has a high density of states here, but the other 2 do not. So if it's not the doorway region, the other obvious place to look will be in the phonon bath itself. Is there anything special going on in the phonon baths for these compounds? And that's when we realized that actually this phonon bath is enormous. So the number I told you earlier for where omega max typically lies is around about 200 wave numbers, plus or minus 50. Here we're way up over 300 wave numbers, okay? So there's a really big phonon bath here. And that comes down to the fact that these compounds are all coordination polymers. And when we look at the phonon bath density for our 3 primary energetics, we'll see that it's higher than the others, okay? So it's the actual fact that these materials present as coordination polymers seems to be directly correlated with why these materials present as primary energetics. If we look further into that phonon bath region, so here what I've done is I've pulled out the partial densities of states. This is for the metal, so you can see big old heavy lead is contributing to the lowest energy phonons here. Lighter copper is kind of more spread out over the phonon bath, as is DBX2. Now if we integrate out the size of the phonon baths, we can see lead azide has the most dense bath, which kind of makes sense because that's the most primary of all of the energetics. DBX2 is the next highest number than DBX1, so we're following the correlation there. And if we look at the percentage metal contribution to the phonon bath, again we can see that, DBX2 has a much higher number. It's almost double what DBX1 is. So the contribution to that phonon bath from the copper seems to be much, much higher in DBX2. So that makes you think, well, actually, is there anything going on with the formulas of these compounds that might be accounting for this? And when we look at the copper content for these 2 materials, we see that the copper content by weight for DBX2 is much higher than for DBX1. So in other words, simply just packing more metal into the structure, these are heavy atoms that, kind of move around and kind of bulk up that phonon density of states. That again seems to be another indicator as to why these materials are presenting as primaries. Now that's all well and good, except we then went and made a third copper nitrotrotazolate. Now we didn't get clearance from UK MOD to be able to show you that structure before the conference circuit started this summer. And when UK MOD is funding your science, you do what you're told, okay? So underneath that graphic is the third crystal structure, but I cannot show you it. But I can tell you it's another copper nitrotrotazolate. I'm going to call this DBX3, and experimentally this seems to be an even more impact-sensitive compound than the other 2. So let's follow the same thread. Is it, okay, first of all, let's see how our up-pumping model does. So DBX3 we're getting out here, okay? So we're thinking from the theory side, it looks like it's closer to the impact sensitivity of DBX1, but we're certainly predicting that it's a primary. So experimentally it should be all the way up here somewhere, so we're a little bit lower than we should be. However, still predicting it to be a nippy primary. So if we follow the trend that we were looking at before, we can ask, well, is this directly linked to the copper content in these materials? But we discover that the copper content of DBX3 is actually lower than the other 2, right? And yet, if you compare the copper content for this one with DBX1, it's almost like higher up than you would have thought it would have been. So if there's a direct correlation with the amount of metal that's there, we would have expected it to have been lower down on the graph. So it's not so much just the amount of copper that's there, but what the copper's doing. And that got us into the idea of thinking, well, maybe those copper ions are less tightly bound in the crystal lattice. They're just kind of rattling around a little bit more. So this is where we got Cameron involved with the work to start thinking about the active void space in these crystal lattices. So what Cameron did, he deleted out the copper ions, and then he flooded that space with all of these sort of little pink probe spheres to be able to map out the shape of the cavity that is left, assuming that all of those neighboring atoms are adopting their standard van der Waals radius. And so these are the average void spaces that you calculate, and you can see that, yes, indeed, in DBX3, that those copper ions appear to have more space. So if they have more space, they're going to be rattling around a little bit more, and therefore contributing more to the phonon bath. Right, so the take-home messages, our vibrational up-pumping model is telling us that all of these compounds present as primary energetics because they are coordination polymers. That gives you that large phonon bath, and also the percentage metal content and the metal cavity size, if you like, are giving you fine tuners to be able to push that impact sensitivity even higher. Right, now on to the tetrazole derivatives. So this is work that we were just looking at in the last year. So taking from a paper here by Klepotki, so a whole bunch of energetic molecules. They're all based on the tetrazole ring, but they're presenting across a massive range of potential impacts or experimental impact sensitivity values. So the red ones are the primaries, the blue ones are the secondaries, and I've grouped them together on the page like this to be able to ask, a couple of leading questions. So first of all, just substituting out that side chain, NH2, for a hydrogen seems to massively affect the impact sensitivity. So the leading question here is why? Secondly, if an NO2 group is put on the sidearm here at this position, it seems to massively drop the impact sensitivity value down. So there's a second question. What's so special about putting an NO2 group on here? Why does that seem to tip the molecule towards primary behavior? Third question is, even just changing the position of that methyl group makes a change, so it's enough to be able to tip this from being a primary to being a secondary. And then the last question, probably the most important, what is it about TET1 and TET2, so this one here and that one there, that make them the most impact sensitive of the whole set? Okay, so let's see how we do when we put it through the vibrational up pumping model. So again, red are the primaries, blue are the secondaries. So you can see we are correctly putting everything in the right place. So we're correctly separating out the primaries from the secondaries. But there does seem to be a bit of an elephant in the room because TET6, which is this one down here, we seem to be predicting as being much higher up in impact sensitivity than was experimentally suggested. Now that's really odd because whenever we kind of come across a data point that we have to fight with a little bit, so I've already highlighted DBX3 was a little bit lower than we hoped it would be. We always seem to be under-predicting the impact sensitivity. We've never over-predicted the impact sensitivity before. So we've looked at about 30 molecules so far, and this is the first time we've ever seen one that's sitting above the line. So we're going to throw that back to the experimentalists and say, you probably want to have a look at that one again, okay? So we think this is possibly down to experimental error because that Fallhammer test is not without its own pitfalls. So, next question, why are TET1 and TET2 the primary energetics? So here's the up-pumping 2 phonon densities of states. Up at the top is pure tetrazole, so this guy down here, and you can see there's an almost negligible 2 phonon density of state. This molecule is almost impossible to initiate through hitting it. TET1 and TET2, so those are the primaries. You can see there's a much more pronounced 2 phonon density of states for those two compared to the others, okay? So this just comes down to resonance. It's having the right modes in the right place to be able to promote. Am I okay for time, Graeme? Perfect, okay, right. So that accounts for why TET1 and TET2 are presenting as the primaries. It's just the right modes in the right place. So let's just dig into that in a little bit more detail. So here's TET1, and again, I've just drawn out the phonon densities of states, and I've color-coded it according to which of my NN bonds are active in each of those eigenvalues, or eigenvectors rather. So I've got 3 types of NN bond. I've got a green one, I've got an orange one, and I've got a pink one here. And you can see that this bond here is active in all of those eigenvectors, not so much this one and not so much that one. And if we correlate that back with our local force constants, remember this is a direct measure of the bond strength of those bonds, again we can see it's the weakest bond which is active in the up-pumping window. That carries through to TET2, so again that's got that very weak bond there, so that's the weakest bond in the molecule. That bond there is much stronger, and you can see that it's only involved in the modes of vibration from 600 wave numbers and above. Similarly for TET3, that green NN bond again is active in the up-pumping window. And in TET 5, where we don't have that bond, you can see that we've got a much sparser doorway region. Okay? So we can see that this is the weakest bond in these structures. That creates a busy doorway window, which tips the behavior of the energetic towards primary behavior. Ditto with the waggly arms. Okay, so TET 1 presents as the most sensitive energetic, basically because it has the busiest doorway mode window, and the reason for that is just because it's a really floppy molecule. So lots of low energy vibrations channeling that shock energy into the molecular vibrations. And as for the placement of the methyl group, well, that's just down to resonance. So even just really small changes in your molecular geometry is enough to tune those vibrations to sit in the right place to be more efficient at energy propagation. Okay, right, all well and good. Bonus slide. If people in the room know about energetic materials, then they'll be thinking that there's one particular notable energetic material which has been missing off my slides, and that's RDX. So RDX tends to be the compound that all new novel energetics are ranked against for impact sensitivity. So people working in energetics will have a source of RDX as well, and they'll hit RDX first, and then they'll hit their new compound with the same amount of energy and go, right, well, it takes more energy than it did RDX to induce initiation or whatever. So it's like the international standard. And I haven't told you anything about RDX so far, and the reason for that is RDX has stubbornly sat way below our line, okay? And Adam and I have been having long conversations about RDX for a while, haven't we? Okay, now, one thing I haven't mentioned at all yet is polymorphism. And of course, we know polymorphism is extremely important. And if you know your RDX, you'll know that there's actually 4 polymorphs of RDX. So we ran all 4 polymorphs through our vibrational up pumping predictor. And funnily enough, one of them appears to sit on the line. Now, gamma RDX is the high pressure form of RDX. And so what we're proposing actually is that if you take alpha RDX, which is the polymorph that is typically used in energetic materials, and you subject it to the Fallhammer test, the process of measuring the impact sensitivity is actually inducing a high pressure phase transition. So what you're actually measuring is gamma RDX and not alpha RDX. And this is a whole new concept, a whole new ballgame for the energetic community to get their head around. And bearing in mind, these are often engineers that we're talking to. These are often formulators. And you need to educate them as to what polymorphism is in the first place, okay? And it really, really matters. If you care about structure-property relationships, polymorphism really matters. So let me just wrap up. What I've shown you, vibrational up pumping model successfully predicts the impact sensitivities for a broad range of energetics. And we now have the tools that allows us to go from structure to property, and I would argue also to go from property back to structure. So something I haven't touched upon is Graeme and I have been working together for the last couple of years as well, because obviously if we can bring crystal structure prediction into the equation as well, then we have an entirely in silico material prediction tool to design new energetic materials. I've shown how we can unpick that structure, unpick the vibrational up pumping model to really start digging into the structure property relationships. And I've exemplified that with work on primary energetics that we've done recently and the tetrasols as well. And the final point, I mean, it's obvious to this crowd, right? But polymorphism is really, really important. Okay, and that's me. I'm all done. Thank you very much. Okay.
The dot flare model which you're using is for thermalization of mechanical. The dot flare model you're using
yes.
is for thermalization of mechanical energy.
Yes.
The problem with it is it's known to take at least 100 to 200 picoseconds for the process to occur. An initial induction of explosion is on the order of tens of picoseconds. So that model is very questionable. Tadeusz Luti and Ordon and I had a paper several years ago where we used electronic arguments to deal with that time scale and show that the flare dot model is too slow for most explosives. It's not to say there isn't thermalization, it's just too slow. And the hammer experiment is a slow time scale measurement and does not measure the initial onset of explosion. Secondly, argument you gave about weakening of bonds and such is essentially one of electronic states. And so our argument is, and the calculations, which does explain RDX as it is, and HMX also, is that you're driving up the potential well on the repulsive side, and you're crossing over to a dissociative state. And that is a very rapid process.
Okay.
So I question that this model is general.
Okay, so if I could counter that, so first of all, there are lots of theories to try to be able to predict impact sensitivity. So people have looked at electronic effects, they've looked at electronic band gaps, they've looked at bond strengths and so on. And they tend to work quite well if you stay within a particular family of molecules, but don't tend to then propagate towards to be able to be a more general form that would be applicable to a broader range of structures. We think our model does actually tie in with the electronic effects as well, because remember what we're doing is we are massively vibrationally exciting the molecules, okay? And we looked at a series of azide derivatives, and we were able to show that actually the molecular vibration that's active in the window is the angle bend, okay? So if you take an azide molecule in a crystal lattice, which is normally about 180 degrees, and you massively vibrationally excite it so that the angle bend changes to about 140, 150 degrees or thereabouts, and you calculate the electronic band gap on the fly. Okay, so in other words, you're looking to see how does the electronic structure of the crystal lattice change as a function of exciting that eigenvector. And what happens is the band gap collapses. Okay, so on the time scale of that molecular vibration, you're altering your material from being an insulator to being a conductor. Okay, so we think the vibrational excitation is definitely valid, but we think it's carried on a vibrational wave.
I think they're still too slow to do that.
Okay, I'll have another look at your paper. Thank you.
Okay, Gérard Coquerel from the University of Rouen. Thank you, Carol, for this wonderful presentation. I won't challenge your computation and your interpretation. But what I can say about RDX especially is that the sensitivity of those materials depends highly on the inclusions in the crystals.
Yep. Ah, okay. Voids.
And then if, you know, the TET6 is not on your curve, you should also ask the experimentalist to look in the crystals. Because if you have inclusions in crystals, then it means that the shock wave, which is crossing the particle, will make an adiabatic compression of the liquid inside. And then it is clear and documented. I can give you references on that.
Yes, I know the papers.
You have a very easy explosion.
Yep. So you're absolutely right. It depends really much on particle size, how the material's packed, etc., etc. But I would also make the argument that the void argument appears on a much bigger length scale and time scale. Whereas what we're calculating here, you can almost think about as being like the intrinsic impact sensitivity that an energetic would have if it presented as a perfect crystal.
Yeah, for sure. It's I'm talking about three-dimensional defect in crystals.
Sure.
But maybe also bidimensional and single-dimensional defects could also have an impact, because what you worked on is on a perfect crystal.
Yep. Correct. But, you know, RDX is, you know, it depends which lab you send it to as well, what value you get. If there's any HMX entrained within the RDX, that will affect the value as well. But, you know, to me, that only makes the argument that you need a computational model to be able to predict this all the more important. Okay, thank you.
Kevin Roberts, University of
Leeds.
Kevin. Hi. Yep, I enjoyed your talk a lot. When I kind of wistful really about the effects of the crystal orientation on detonation, and I don't really know the answer to my question at all, but if you look at, I don't know, TNT, two polymorphs, the orthorhombic polymorphs are quite unstable. If it transforms to the stable monoclinic form, then it creates a lot of void space in the crystal, and so is it the void space in the crystal that makes it a much more unstable situation? There've been quite a lot of accidents that way. And is it something to do with the surface properties of the material? So if you've got packed polyhedral crystals of a material, what's the interface doing? Because at the interface, the molecules are under-coordinated.
Yep.
And it seems to me that when you get molecules at surfaces, that under-coordination makes them more reactive.
Yes, yes, I hear what you're saying. So we've looked at the two polymorphs of TNT, and they differ. And they differ by quite a marked amount. So sorry, so I was going to point to it on my graph, but I'll not go and find it. So yes, just the sort of intrinsic ability for the two different polymorphs of TNT to channel that shockwave, there are fundamental differences.
So does the void do the same as what Gerard was saying with the solvent inclusion? Is that a similar effect?
Yeah, so again, I would say that's a longer time scale and a longer length scale. So this will not tell you anything about grain boundaries, okay? And it never will. What our community needs to do, and interesting, I've come straight from a Gordon conference on energetic materials just last week, and I sat through 2 days of hearing about void calculations, and then I stood up and said, okay guys, now we're going to take it down a length scale, we're going to go under the hood, if you like, and start talking about the condensed matter physics that's there. And to my mind, I think the two communities need to link up better, because it's almost like, if you want a fully computational process to be able to say, for this molecule, what do I think its safety metrics are going to be? There's a whole series of processes that need to be under that hood. This is one of the early ones, okay, because you can vibrationally up-pump anything, right? You can vibrationally up-pump a non-energetic material, but it's not going to go bang. So after the up-pumping, it's like you need a thermodynamic, routine to say, is that actually going to cause irreversible damage to the structure or not? And that tells you, is it energetic, is it not? Then I think the next module along then needs to be about length scales. Let's now start thinking about voids. Let's now start thinking about interfaces. But you can't have that bit either without this bit as well. So we're dealing with the same problem but on different length scales. And the information that one gives you needs to be passed on to the next.
And one just related question. If you look at the fact that most of the materials are held together with dispersive forces,
exactly. Okay.
Then okay. Is a model that has a dispersion correction DFT, is that valid when it's only dispersion? It's not a correction, is it? The whole lattice energy is dispersive.
Yeah, but I think it's unusual to have a lattice that's entirely held together by dispersion for these compounds. Okay. All right, thank you. All good, all done.
It's back. Okay, good. Thanks, Carol. And I'll invite the next speaker up stage. Martijn Zoinenberg from University College London. Where's your laptop? He's going to tell us about something a little bit different, I think. So I'll hand over to him.
Okay. Yeah, because it's mini USB, so it's fine. Don't worry. Okay, thank you, Graeme. Yeah, I'm going to talk about something completely different, and that's about the effects. Basically, we're able to predict the electronic and optical properties of organic materials. And this is like, I come from a slightly different community, and this is how I probably would normally start. We're interested in organic materials, we're interested in sort of finding the right material for a job. What the job is, we'll come back to in a couple of slides. In the context of this session, I will talk a little bit about how it works, electronic properties, how do we predict them, and how do we get the right material, of how the right calculation, but maybe via the wrong way, or basically via error cancellation. So my group at UCL, we work on lots of areas. So we work on nanoparticles, predicting their properties, predicting properties of polymers, and using machine learning to do that. And predicting self-assembled materials, their properties, predicting materials for photocatalysis, and sort of predicting their activity. And we do a little bit of work on crystals, some involving also the chairman on covalent organic frameworks and hydrogen-bonded hydrogen-bonded organic frameworks. And what you will see now from that is my first confession to make in this talk is most organic systems we work on are amorphous in the solid state, or at best poorly crystalline. So bear with me in that respect. And the application that we're mostly interested in, the application that I'm going to sort of apply the results in this talk to, is in the area of solar fuel. So that's basically the process of converting sunlight via artificial photosynthesis into either hydrogen via water splitting or by reducing CO2 to CO or alkanes. So basically, turning sunlight into energy and potentially converting CO2 back into useful organic molecules. So this is where we're going to apply the materials and the results that we're talking about in this presentation. Just to give you some context, because I'm probably, I expect a lot of you are not aware of this, you can actually use polymers, organic polymers, or even actually organic molecules in combination typically with a noble metal co-catalyst to do photocatalysis. So this is a slide work from our experimental collaborator, Seb Sprick, then in Liverpool, now in Glasgow, where basically we take these polymers and we put some platinum on them, and we put particles of these polymers in a mixture of water and a sacrificial electron donor. So we're not oxidizing, we're not doing overall water splitting here, we're not oxidizing water, we're oxidizing this organic molecule triethylamine, and basically you produce hydrogen. And so this is some of the results there. You see that you evolve steady amounts of hydrogen, and different polymers show different activities, and we basically get EQEs. They say something, there's a quantum efficiency, they say something about how much of the sunlight or how much of the light the material absorbs gets converted into hydrogen. So we do quite reasonably, so we're going 7 to roughly 10. The best record is currently like 20% of the light absorbed gets converted into hydrogen. And importantly, because there's always a thing that people ask you, there's no signs of polymer degradation when you look at the material after use, and we evolve many more times hydrogen as present in the polymer. So it's not the polymer falling apart, it's really the polymer acting as a photocatalyst. So the light gets absorbed, charge carriers get generated, and they reduce hydrogen, protons to hydrogen, and they oxidize, in this case, triethylamine to affect ultimately diethylamine and acetaldehyde. Okay, so this is the current state of the art, just a bit of context because we're going to come back to it later. Polypyraphenylene, we refer to this typically as P1, was the first reported example of a polymeric photocatalyst. This was in the mid-80s, work from Japan. But basically nothing really happened as a result of that until in 2009, a group in Germany, they basically showed carbon nitride, which is also an organic material, if you like, because there's no carbon-carbon bonds, only carbon-nitrogen bonds, and they showed that basically could both reduce protons to hydrogen and oxidize water to oxygen, and this basically kickstarted the field. And currently, in the order of 150 plus polymers are known to be active for sacrificial hydrogen evolution. This includes the linear polymers that I showed you, but also conjugate microporous polymers, covalent triazine frameworks, and in context of this meeting, very maybe important, covalent organic frameworks, which are the most crystalline of all these materials that we discussed here. And a much smaller number of polymers are known to be active for sacrificial water oxidation. So most of these are like 150 plus known to evolve hydrogen. I'm going to say 10, 15 are known to be able to oxidize water to oxygen, and even less, of the order of 4 or 5, are known to experimentally do the whole process of both proton reduction and water oxidation, and giving rise to overall water splitting. And that's what you want. You don't want to oxidize a sacrificial electron donor, because that molecule probably contains more energy than the energy of the hydrogen you produce. Okay, and in order to understand this, and in order to be able to predict which materials should be good, or to basically rationalize the activity of materials, we need to be able to understand if a polymer should be able to absorb light, it should be able to thermodynamically drive the reduction of protons and the oxidation of water, or if you're doing sacrificial work, sacrificial donor, those should be wettable and dispersible in water. And the polymer or co-catalyst should also be able to catalyze a hydrogen-hydrogen, oxygen-oxygen bond formation. And in terms of the thermodynamics, we should basically be able to predict the reduction potential, the oxidation potential of the charge carriers in the polymer. So think of it as the conduction band minimum and the valence band maximum. And so that means that to understand why polymers and organic materials more widely can act as photocatalysts, but not only photocatalysts, but light absorbers in light-absorbing layers it should be solar cells, not solid cells, and light-emitting layers in LEDs, etc., we need to be able to understand and predict their electronic properties and their optical properties. And it's the same when we want to predict, or more controversially, as Graeme already alluded to, design. Because do we ever design really new organic materials for such applications? So this is where my second confession comes in, because this conference is on the organization of the solid state. We generally ignore the effect of intermolecular packing and focus mostly, when we do our calculations, on calculations of an isolated polymer chain embedded in a dielectric continuum. However, having said that, I'll come back to the effect of explicit packing effects at the end of today's talk. So, as I said, we generally ignore the effect of intermolecular packing and focus just on the isolated polymer chain embedded in some sort of dielectric, which basically describes the effect of the environment. So we basically only sort of expect the long-range effect of the environment, but not the hybridization between the polymer molecule we're modeling and all the molecules around it. And we do this for two reasons. For reasons of computational tractability, partly because most materials, as I alluded to earlier, most materials that we're interested in, they are amorphous, and so it's not an easy question of like, if you want to take into account packing, how you would do that, and what are representative structures. But also because a lot of our experimental colleagues are interested in high throughput screening and coming up with materials very fast, and clearly, if you can do the cheapest possible calculation and get good results, that is obviously advantageous in terms of the time it takes. But also because we make the assumption, rightly or wrongly, that packing effects wash out for the mostly amorphous materials we're interested in. Okay, so far so good. You can say, well, that's great that you say that, but is that true? Well, that means that we have to obviously validate our predictions to either experiment or by calculations with a higher theory. And obviously, when we compare to higher level theory, we're never going to be able to include the packing effect because these calculations are too expensive, so we really should compare to experiment. Now, when it comes to spectra, that's relatively easy, with an emphasis on relative. I mean, obviously, the experiment is relatively easy to do. When it comes to electronic properties, and so we're thinking, for example, here where the electronic bands sit in the material, this is a little bit harder. For example, in the case of a polymeric photocatalyst that we're interested in, this sort of the potential, so the valence band maximum, conduction band minimum equivalence, there's basically no experimental measurements of these things under operating conditions. What I mean with this is that we're interested in obviously where they sit in contact with water or in contact with an aqueous solution. And the sort of experiments that you can do typically don't allow you to access this information under these sort of conditions. Other than electrochemistry, and electrochemistry on the solid state on polymer samples is typically horrific. You get, I don't know how many of you know about cyclic voltammograms, but there's like a textbook picture. If you look at these ones, they're like as broad you can drive a London bus through them. So they're very non-informative, and there's a lot of interpretation or wishful thinking in trying to interpret them. There's photoelectron spectroscopy. Obviously, that doesn't work under operation conditions. That typically, well, it used to happen in vacuum. It's available for a selected number of polymers, and it's generally old. It's basically data from the 70s to the 90s. More modern, or nowadays people do photoelectron spectroscopy in air, PISA, which is easier to run, is a sort of like modern alternative. but it can be sometimes hard to reconcile the data obtained with PESA with those obtained using other methods. So there's some, we don't necessarily know all the, sometimes the effects we don't properly understand in the experiment. So what we've done here is we have taken our model, a single polymer model, combined it with a box standard DFT functional. We've done some calculations. This is work from Adriano, who was a postdoc in my group, and Pierre, who was a PhD student in my group. And so we looked at a bunch of polymers for which there is data in the literature in the solid state. So these are solid state samples, typically amorphous, which people have done photoelectron spectroscopy, and people have either measured the ionization potential, so the top of the conduction band, electron affinity, bottom of the IP, top of the valence band, EA, which is electron affinity, which would be the bottom of the conduction band, and in some cases, excited state information available, so excited state potentials. And what you see here is the thick lines are the experimental points. The thick lines are our predictions. The thin lines are the experimental data points. And for some materials like polythiophene, there's a range of data, and there's quite a bit of dispersion in there, which is partly due to the materials being different, and partly due to the data is inherently giving some noise in there. But I mean, roughly, the single polymer chain results seem to give the right sort of numbers, the right sort of trends. So it all looks, we were quite happy with that. Now, if you actually then look at specifically at one polymer, which is polyparaphenylene, what you see on this slide is a table with lots of numbers in there, but basically what you see is that actually for the solid state data, for all materials we predict the same trend. That's cool. And this is also the same trend as experiment, but for the solid state data, we're the closest to the experimental numbers, and we're actually further away for the gas phase data and for the solution data, which was obtained by chloromethane using electrochemistry. Which is odd, because in a way, the gas phase and the solution data is closer to what our model is, because in those cases, you can assume that basically you're doing experiments really on single chains. In the solid state, obviously, we make the assumption that we can model with a solid state with a single chain, but it's not actually obviously experimentally true, which suggests that probably the success of the single chain model is due to error cancellation. Error cancellation working in our favor is great, but there is a caveat there. There is probably error cancellation at play here, as often when you apply DFT to a material. More recently, we did some work. Our experimental collaborators made some new materials, and they did some PISA measurements of photospectroscopy in air. And the calculations were done by a postdoc in my group called Liam. And basically, again, they found that we basically agree to a large extent with the experimental PISA measurements, which is great. So what I have shown you, or hope to have shown you, is that basically the single polymer chain model, while not perfect, combined with delta DFT appears to work, give reasonable predictions for polymers in the solid state, and does this by giving predictions reasonably in line with experimental photoelectron spectroscopy data on organic polymeric solids. As I said, actually gives less good predictions for oligomers in the gas phase and in solution, and that suggests to us that there is error cancellation at play, something I will come back to at the end of today's talk. So far, so good. We've shown that it works. Now let's show some examples of where we apply it, and I'm going to give you two examples. Although actually, we have applied this approach to many materials in many different studies, but I'm going to give you just the two examples here. The first example is going to focus on a trend in the hydrogen evolution rate for thiophene-phenylene copolymers when we change the amount of thiophene in the polymer. And the other example is basically showing that when you have a simple model of the polymer, you can basically do high throughput screening to answer questions about what is possible or not with polymers, in this case, in the context of overall water splitting. So this first example, so our experimental collaborators in Liverpool, they made these polymers. They're all copolymers. They go from pure polyparaphenylene, to pure polythiophene, and they basically changed the amount of thiophene in there. And the reasoning was that this is good because obviously we're trying to make a photocatalyst. We would like to absorb as much of the solar spectrum as possible, and incorporating more thiophene in the material basically shifts the onset of absorption to the red. However, when they did so, what they saw was that when you looked at the trend of the hydrogen evolution rate with a fraction of phospine, they saw initially it goes up, as you would hope, but then it goes down, and we have this sort of like maximum in our trend. And they didn't know what was going on. So what we then did is we basically calculated our potentials, again using the single polymer model in contact with, embedded in a continuum of water, in this case. And what we see is that, now let me see if this, yeah, so what we see, if you, basically we want to do two things here in order to evolve hydrogen. Our polymer should be able to reduce the presence of hydrogen, and it should be able to oxidize TA. And if we look at our potentials, you see that they taper inwards when we increase the amount of thiophene. So our ionization potential gets less positive, and our electron affinity gets less negative. And what that means is that we're basically reducing the thermodynamic driving force for both half reactions. And specifically in the case of the oxidation, we end up in a scenario where, yes, we can overall oxidize. So TA, the typical half reaction is where we do the 2-electron oxidation of TA to diethylamine and staldehyde. That's perfectly fine. All these materials should be able to do that. But only the materials early on are able to not only do the 2-electron oxidation of TA, but also the first single electron oxidation of TA to the TA radical. And so our explanation for what they see experimentally is that basically the problem lies with this driving force. So yes, increasing the thiophene content is fantastic for reducing the optical gap, for increasing the amount of light that's being absorbed, but not very good in terms of the thermodynamic driving force for the half reaction, specifically for the oxidation of TA. And so based on that, we basically postulate that basically what's going on here in this region, where the rate increases with incorporating more thiophene, we were light absorption limited. So our material could oxidize TA fine, but what we were limited by was the amount of light that the material absorbs. While at this part of the graph, where our activity goes down when we increase the amount of thiophene, we said, okay, that's probably due to the fact that basically now the material absorbs a lot more light, but we're paying for that in terms of the ability to actually drive the oxidation half reaction on TA. So this is typical. Basically, what we can see is that these predictions on the single polymer strands embedded in water combined with DFT, they are basically able to rationalize a lot of the experimental points. Now we go a step further. So what we saw in the first example is we were trying to predict results where our experimental colleagues had already made the material. So we're basically trying to understand, trying to rationalize. But in principle, as Graeme alluded to in the introduction, if we have a computational model that works, we can also try to go further, and we can try to basically truly predict, and answer questions that you might not be able to easily answer using experiment alone. And I've shown this slide before, and I would just like to draw your attention to the thing at the bottom. There's this interesting question about why are there so many more polymers known to experimentally to be active for sacrificial hydrogen evolution compared to the number of polymers that are active for water oxidation or overall water splitting. Obviously, we really would like to have more polymers than are currently known that do overall water splitting. Just many more polymers that can do sacrificial hydrogen evolution is not going to be useful for anyone. Where these materials might offer some sort of solution in terms of like the transition to more renewable energies is when we split overall water, because that's where we're generating new energy rather than effectively burning a sacrificial electron donor. So our logical hypothesis looking at the state of the literature was that due to the fact that water oxidation, that half reaction where we only have those few materials that can do it, is so much more harder thermodynamically than oxidizing a sacrificial electron donor, and that is why there's so few polymers known. And it sounds very fair. I mean, it sort of makes sense. But we wanted to test it. And so what we did is we basically said, if we have a large library of polymers and we look at their fermionic ability to drive sacrificial hydrogen evolution and overall water splitting, then if the hypothesis is true, we would expect there to be many more polymers that can do one than could do two. And so it allowed us to basically sort of test this hypothesis computationally. And it's nice to do this computation in the sense that we can generate a large library of materials. That's very easy for us. And we can also eliminate lots of complicating experimental factors. So hydrogen evolution activity, photokinetic activity of polymers is obviously a composite property of many things, and sometimes in experiment, the issue is that actually the trend you're observing has nothing to do with the inherent, innate activity of a material, but actually due to particle size or co-catalyst loading or all kinds of complicated things that do not exist in our model. That's both a strength, that we can work around these things, and obviously also sometimes a weakness in the sense that we might not be able to explain experiment because of these complicating factors, but in this case it's clearly a strength. So what we did is we built 3,240 copolymers computationally using a library developed at Kim Jels's group at Imperial. So we built all these models computationally using a whole range of these monomers that are given here. We then find the lowest energy conformers computationally, calculate their properties. We now don't use DFT, we use tight binding DFT because to do this, even with DFT gets computationally expensive. And we have previously fitted a model where we basically take tight binding DFT values and be able to map them back onto the DFT model. So we can basically compare and contrast. And we're going to make some assumptions along the way. So we're basically going to say that hydrogen and oxygen evolution are catalyzed by a metal co-catalyst, that the sacrificial electron donor is going to be non-catalytic, and that we need to consider all these half reactions that I previously mentioned already. And we also look at overpotential values, although I'm not going to bother with those much today. So the first thing is we looked at, we just predicted the ability of these polymers, this large library of polymers, to be able to do sacrificial hydrogen evolution. And what we see two red line and a blue line in all these graphs. The red line is when we just say, oh, our material should be able to reduce protons and derive the two-hole oxidation of TA. The blue line is say, oh, it should also be oxidized TA and do also the more challenging first electron oxidation of TA. And then the gaps here are as a function of the band gap. So we say, oh, all polymers, we basically include all polymers, and then basically we only include polymers with an optical gap, which below 3.5, below 2.5, below 2 eV. Because obviously we would like to have the optical gap as small as possible. And these are the sort of results. And on the x-axis is the overpotential. So how much extra energy should our material provide on top of the thermodynamic potential values? And we see that basically we get a large number of polymers, in our data set are able to sacrificially evolve hydrogen. The more overpotential we require, less polymers survive. That's so far so good. The other thing we see that if we want a polymer that can do this and have a small optical gap, absorb most of the solar spectrum, then that gets more challenging. And basically every polymer known experimentally to work this fits within our data set. So it's very nice to see. We had, again, in line with the fact that our screening, that this polymer model works practically, is that we basically correctly predict the polymers that are experimentally known to be active to be predicted to be active. Now the surprise came when we applied this same model now to overall water splitting, and what we see is actually the numbers are quite comparable, especially if you look at the sort of pH value where you are when you do sacrificial hydrogen evolution, which is sort of like pH 11 or pH 12. And so basically the same sort of data we now show here again the fraction of polymers that are able to do it, able to predict overall wall splitting. Now the overpotential are the different colored lines, and on the x-axis we have the pH because obviously we can play around with the pH. And we see that very similar number of polymers are predicted to derive overall splitting as sacrificial hydrogen donor, sacrificial hydrogen evolution, sorry. And also what we see is that similar as for the sacrificial case, that the problem really comes when we say, oh, we want a polymer that is able to thermodynamically drive overall wall splitting and have a small optical gap. so absorb most of the solar spectrum, there where it gets hard. Now, that feels at odds with what we know from experiment. So what's going on here? Because clearly our model worked for the sacrificial case, so why are we predicting something different in experiment here in the context of overall water splitting? And also, what might be able to tell us about how we can turn our experiment around, if I can be so arrogant? Firstly, you could say, well, maybe your model doesn't work for overall water splitting. That's possible. But what I can say is that all the polymers known experimentally to be active for overall water splitting are predicted by our model to be active for overall water splitting. All the polymers that we have done ourselves, or our collaborators have done themselves, which we know from their work, which we trust to be not active, we predict to be not active. So that feels like the model should be getting things right. So what is the difference then between, experimentally, between these polymers that, for the case of overall water splitting compared to the case of sacrificial hydrogen evolution? Well, that is to do with the water oxidation half reaction, but maybe not for the reasons we initially thought. So we initially said, okay, the water oxidation is thermodynamically hard, and that's why it's not happening. But we're wondering now, instead it is that it is to do with the catalysis of this reaction. So water oxidation is inherently a very sluggish reaction and requires 4 holes, 4 electrons if you like, to oxidize 1 molecule of water to oxygen. And that will make it sensitive to electron hole recombination. And so our new hypothesis is that the scarcity of polymers active for overall water splitting is most likely due to dominant parasitic electron hole recombination rather than being due to any inherent thermodynamic constraint. And in line with that, if you go back in the literature and you dig through, you find those papers where people report polymers that are active for overall water splitting, they were initially typically first reported to be active for sacrificial oxygen evolution only, and only became active for overall water splitting when people optimized the co-catalyst. So that's in line with our hypothesis, and it's also in line, and it's a good, that's what it's a good thing because, and actually I'll come back to that later. And what it then allows us to do is basically suggest lots of polymers and say, well, look, our experimental colleagues, these are good polymers to focus on and to make and see if they're active overall splitting. Because, and this is where computational screening comes in, the strength of the library, the possible space of materials to make is gigantic. I mean, if you're easily talking about millions to possibly even billions of polymers, especially if you go beyond binary copolymers and you could ternary or quaternary polymers, which are often used, for example, already in the context of organic electronics, you're not going to sample that sort of chemical property landscape experimentally, even not with the robots. So somebody mentioned, I think it was Luca before, in this morning mentioned these robots that Andy Cooper has in his lab in Liverpool. We work a little bit with Andy, or actually we work quite a lot with Andy, though not on the computation, on the robot side, but you're not even with robots, you're not going to sample this experimentally. So you need to somehow first whittle down the space on a computer and then try to focus your efforts in the lab only on those polymers which the computer predicts to be active. Yeah. So a month on the computer can save you a couple of years in the lab, or at least that's what our sales pitch would be. And so the screening conclusions, I already alluded to them. Similar number of polymers are predicted to be able to drive overall water splitting and sacrificial hydrogen evolution, and basically electron hole recombination is the issue killing most polymers experimentally for overall water splitting, and that means that if you have a suitable water oxidation co-catalyst, a lot of polymers which are already known in the literature could or should become active for overall water splitting, and also it might be good to make heterojunctions because again they help separate electrons and holes and minimize electron hole recombination. Perhaps the biggest challenge is finding polymers that are both active, thermodynamically active, and have a small optical gap. That's what our calculations borne out, that basically that is the real killer issue. And actually this is where, compared to inorganic materials, we have the same issue. Because also on the inorganic material side, there's lots of materials that are active, but only active when you shine UV light on them. Okay, so this I showed you here for polymers, but in principle, this equally holds for molecules and for other materials. But yeah, this was all done for polymers. Now, I promised that I was going to come back to the single polymer I was going to come back to how we can go beyond the single polymer molecule model at the end of this talk. So this is that moment. I hope I've shown you that the single polymer / molecule model clearly works in practice, and I put a lot of emphasis here in practice. I'm not saying that the predictions are necessarily I'm saying that we're making use of error cancellation here, but it works practically to predict things which are useful when it comes to experiments. So why would we go beyond it? Well, there's different reasons why we would go beyond it. Firstly, I already alluded to it just now, is because its success clearly arises from error cancellation and hence is not intellectually very nice. But also, because obviously we by design, we cannot say anything about the effect of packing on the properties of the polymer, which maybe for amorphous polymers is something we can get away with, but even in amorphous polymers, there's going to be some sort of organization. We'd like to be able to address that computationally. And also, there's lots of applications beyond photocatalysis where we have polymer particles or particles of organic molecules where we want to say something about what happens at a certain distance away from the solvent. So this could be photocatalysis, could be batteries, this could be all kinds of other applications. And so we can't address those sort of questions where we modeled our materials a single polymer strand or a single molecule embedded in a dielectric continuum because there is only one molecule. And so those are sort of reasons to go beyond this. Now, we're not the only people that have done it. So obviously, clearly, there's people that have done for crystals doing periodic calculations. But when it comes to but those periodic calculations don't give you access to everything, especially not when you want to take into account also relaxation effects. So this is why the sort of molecular-based QM-MM sort of like calculations are interesting. But yes, other people that have looked at it are, for example, a group of Chad Risco and Breda. And now I forgot the name of these people. Xavier Blas in France. So they have also looked at these sort of effects. And so how can we do this? Or how do we do this? And this is work which is currently ongoing. So we model organic solids as molecular clusters embedded in a dielectric continuum. So we still have our continuum that we saw before, but now instead of having one molecule in a continuum, we have large organic clusters. We built these clusters using conformer searching, between inverted commas, because they're not strictly speaking conformers, but the CREST code, which was developed by Stefan Graeme, basically allows you to also look at the energy landscape of aggregates of molecules. So we use that combined with manual construction to build models, basically to sort of find additional structures which are not necessarily lowest energy structures. We then calculated the electronic properties of these aggregates, both using DFT, or delta DFT, because we calculate the molecule, the situation both as a neutral molecule and a molecule with one extra charge and one less charge to get our potentials. But we also use Green's function theory here. And so why are we doing this? Green's function theory is a much more expensive computational calculation, because when you do this sort of modeling, the functional choice when you use DFT becomes very important. So normally, we only concentrate on what the function does in terms of the properties of the single electron properties of the single molecule. When we have these aggregates, what we need to describe, these organic molecular aggregates, we need to describe both are the inherent properties of the molecule, but also how they couple together. And when it comes to the dielectric coupling of these molecules together, it turns out that in DFT, the amount of hybrid exchange we put in there basically fixes this parameter. And if you can have this perverse situation where people often use functions with different amounts of Hardy-Fock exchange to get some properties correct of the single molecule, but then we basically also impose a dielectric screening onto our molecule in a cluster which is not the correct one. So we can test that with using GW, which doesn't have that problem. And so the test example that we're currently working on is quaterthiophene. So we're now packing quaterthiophene oligomers together in different ways. So these structures all come from CREST. So we basically have these stacks where it stacks on top of one another, like a deck of cards, like pie stacking, but also we have these more complicated motifs, two-dimensional and three-dimensional motifs coming through. And then after we found them at Crest and manual construction, we then use DFT to study the electronic properties, and specifically we use PBE0. Why do we use PBE0? Well, we use PBE0 because the amount of Hardy-Fock exchange in there gives us roughly the experimental dielectric constant, which has been measured for polythiophene, which is 4. And so we're dialing that in. Ideally, and we haven't got around to this, we could also predict the dielectric permittivity of these aggregates directly and plug it back in and make a self-consistent sort of cycle, but we're not there yet. Now, I'm not going to show the result because we haven't really sort of analyzed them yet, and they're quite complicated, but I just want to sort of share with you some observations we have, which are also in line with previous work from Blas and Chadresco's group. So basically, these edge states, so the bottom of the valence band, sorry, the bottom of the conduction band, top of the valence band, or your EA and your IP, they basically shift together, both as a result of packing, so hybridization effects between molecules, and the dielectric screening by the environment. The relative effect of the hybridization contribution, the packing contribution, basically goes down with the dielectric permittivity of the material in such environment. Because the charges that we model become more localized. Now you might say, well, what's the point of that? Because isn't that dielectric permittivity of the environment fixed? Well, yes, if you'd have a bulk material, it obviously would be, but for a lot of applications we're interested in a polymer sort of in contact with some sort of dielectric like water, and obviously there the dielectric gets fixed to a large extent by the environment. The effect of packing hybridization further reduces when taking polarons into account, when basically taking into account that these charges distort the material by localization. And that further localizes the charge and reduces the number of molecules involved and reduces the contribution of molecules beyond the molecule in which the charge gets localized. And we can basically get in errors as small as 0.2 eV with respect to extrapolated bulk by clusters as small as 4 molecules. And yeah, we can, the error cancellation that I mentioned before, basically for the single chain model, we can basically explain in terms of the error between the DFT and the GW calculation. So basically, the reason DFT works, ironically, for the single chain molecule is that it predicts the wrong values when compared to the exact, well, for you can call EV-GW exact. It basically corrects back, and that's the Behrheim error cancellation that we're seeing. Which brings me back to the acknowledgements. So I want to thank all the students in the postdoc in my group that have contributed to the work I've shown you, all our experimental collaborators in Glasgow, Liverpool, Imperial, and Tokyo, who have basically contributed to validating some of our predictions. Our computational collaborators at Imperial that basically made the software available that we use to build some of our polymers. And finally, in the context of this meeting, Sally Price, who is one office besides my office. I would like to acknowledge her because a lot of this stuff on organic materials arises from us chatting on the corridor, because this is much more her field than mine. This is where I would like to finish, and I hope I haven't bored you too much with my slight deviation away from crystalline single molecules, for crystalline well-defined molecules. Thank you.
Thank you, Martijn. Do we have some questions? I will start, I think. In your large-scale screening study, there was a conclusion that perhaps the sort of electron-hole recombination is to blame. What do you need to know? I guess you need a model for the full structure in order to be able to model this. Is this simply a function of mobilities of electrons and holes, or what would come into that rate if you wanted to be able to predict that?
I think actually this goes beyond the polymer or the organic molecule, because this sort of conclusions would hold similarly probably for covalent organic frameworks or hydrogen bonded organic frameworks, which are obviously crystalline. I think what you need to know is basically, to answer that question, is much more to do about the co-catalyst, how quick it works and about the electron transfer rates between your polymer / organic crystalline material and the co-catalyst. And so the sort of suggestions that we make, okay, find a better co-catalyst, that's sort of easy. Or find a heterojunction where basically electrons go right, holes go left, and that are sort of the easy suggestions. But to actually design this is a much harder question because just, yeah, and actually the hard questions are not on the organic side there. The hard questions are on the typically inorganic catalyst and or the interplay between the inorganic catalyst and the organic material.
Okay. Right. Thank you. Perhaps people are eager for coffee, so thanks again to Martijn and also to Carol for 2 great talks. We've gone from 20 minutes behind to 30 minutes behind. Should I say 25-minute coffee break instead of half an hour to sort of 15-minute? Okay, so we'd be coming back at 5 to. Yeah. Okay, thanks again.
I only could stop you before you made trouble for me once more. Tonight would be the happy man if he only would hear my advice. Have respect for the good ones. Tonight would be the happy man. I have never been very far, so despite you, I've both seen very depths of sin, and it moves me. Ooh, love. She has her hold on me, and need to feel that free. If I only could stop you before you made trouble for me once more. Tonight would be the happy man if he only would hear my advice. Have respect for the good ones. Tonight would be the happy man. I won't try to hide the old embracing feel that I'm in displaying here. If I only could stop you before you made trouble for me once more. Tonight would be the happy man if he only would hear my advice. Have respect for the good ones. And I would be the happy man. Let's set each other's lonely nights, be each other's paradise. Need a picture for my frame, someone to share my ring. Tell me what you wanna drink, I tell you what I got in mind. Oh, I don't know your name, but I feel that's gonna change. You ain't gonna be my lover, for you to call me baby. Never been about
Hello? Yes. We slowly start after this coffee break for the second part of this session about crystal in computers. We have 3 talks for this part. So the first one is from Snežana Zarić from University of Belgrade in Serbia, and she will talk about interaction in aromatic systems.
Thank you. So I will talk about interactions of aromatic rings, actually about aromatic interactions in crystal structures. My group in Belgrade developed original methodology to study non-covalent interactions. So we actually combine searching crystal structures with quantum chemical calculations, and from the crystal structures we look at the chemistry structural database and protein data bank. And actually, by getting data from these data banks, we get huge amount of data. We analyze these data, and based on that, we can find particular interactions that exist in the crystal structures, and we also can find the most frequent geometries of these interactions. However, from the crystal structures, we cannot get interaction energies. So in order to get interaction energies, we perform quantum chemical calculations. And not only that we get interaction energy of particular interaction, we actually calculate complete potential surface for the certain type of the interactions. And in that way, we can find the minimum on this potential surface, and in that way, we get the most stable geometries. And we also calculate electrostatic potential maps that can help us to understand some interactions. So about importance of the interactions of aromatic molecules, this is from the paper from 2019, and they actually find that actually the number of the papers working with pi-pi interactions, which are basically aromatic interactions, is increasing from decade to decade. The aromatic interactions are important because they can exist in nucleic acids, as it is very well known. They exist in the proteins. It is very interesting that this is one example where the protein was disordered, and when the histidines were mutated, with aromatic amino acids, they obtained ordered proteins. So it tells us about importance of aromatic interactions in proteins. This is quite old paper, but actually a long time ago, they found that 60% of aromatic side chains are involved in aromatic interactions. 80% of them are interacting from 3 or more interactions in the side chains. 80% stabilize tertiary structures, 20% stabilize quaternary structures, and also aromatic interactions are conserved in the proteins. Also, we can have the interactions between proteins and DNA. We can have application of these aromatic interactions in making homogeneous catalysts, heterogeneous catalysts. Most of drug molecules contain aromatic rings, and these are examples of different medications that are based on naphthalene ring. And also, of course, these aromatic molecules in the drug molecules interact with the aromatic rings in the active center. This is the example of the hydrogel, where if you have more aromatic groups in the hydrogel, it is more dense. With the less aromatic groups, the hydrogel is less dense. So then the basic to study aromatic interactions are 2 benzenes, actually benzene dimer, and people studied that a long time ago, and they found this data about the energies of benzene dimer. So if we have the sandy geometry, it is not particularly stable. It is about 1.6 kilocalories per mole. If we have this parallel display geometry, it is more stable. It is about 2.7 kilocalories per mole. T-shaped geometry is also about 2.7 kilocalories per mole. And actually, this is the most stable geometry. It is some kind of T-shaped geometry, but it is tilted, and it is 2.8 kilocalories per mole. In comparison with the water dimer, so the hydrogen bond in the water dimer is 4.4 kilocalories per mole. So these interactions between benzene molecules are significantly weaker than the interactions between two water molecules. Considering a situation where we have the heteroatom in the ring, and the example is pyridine dimer. Pyridine dimer makes stronger interactions, so the sandy geometry can be parallel or anti-parallel. This anti-parallel is more stable, 2.9 kilocalories per mole. Stacking geometries, this parallel displays about 3.7 kilocalories per mole. And it is interesting for the pyridine that actually these T-shaped geometries are less stable than the stacking geometries, differently than with the benzene. And now if we get that compared together, so 2-benzene is 2.7 kilocalories per mole, benzene and pyridine is 3.3 kilocalories per mole, and 2-pyridine is 3.8 kilocalories per mole. If we have more heteroatoms and even some substituents, like in this nucleic basis, we actually have stronger interactions, so the interaction between two uracils is up to 10 kilocalories per mole. If the aromatic system is larger, so here we have the naphthalene, the energies are stronger. And for the stacking geometry, it can be about 6 kilocalories per mole. T-shaped geometry is also stronger than for the benzene. It is 4.6 kilocalories per mole. However, in this case, these T-shaped geometries are less strong than the stacking geometry. So for the larger systems, actually stacking geometries are favored. This data for the benzene dimer can be explained with a simple electrostatic model. In this simple electrostatic model, the benzene molecule can be considered that has a positive charge in the plane and has negative charge above and below the plane. And this representation is quite good because it actually corresponds to calculated electrostatic potential map for the benzene molecule, where we really have the positive charges on the hydrogens in the plane, and we have negative charge above and below the ring. So considering this simple model, if we look at this sandwich geometry, we see that we have the negative charge and the positive charge close to each other, so it is not particularly stable. This geometry here, parallel displaced, is more stable because we have positive, negative, so it is electrostatically more favorable, and also edge to face or T-shaped geometry is also a positive to negative, so it is again favored. So most of this, what is done about aromatic molecules, are some quantum chemical calculations, with exception of this data that I showed you for the proteins, aromatic interactions in the proteins. And then the question is, so we know quite a bit about calculations on aromatic interactions, but the question is what is really going on in the crystal structures? What aromatic interactions in crystal structures? And that is the question that we wanted to answer. And we first work on the benzene dimer. So we searched the Cambridge Structural Database, and we actually had some geometric criteria, so some limitation in the bond distances, actually in these distances between the centers of the ring. And what we obtained was quite surprising. So this is the most stable geometry, and this most stable geometry does not have large number of the structures with this the most stable geometry. Actually, the largest number of contacts between two benzene molecules is geometry like this. And I mean, when you look at that, you have the impression that these two benzenes are almost not interacting. You just have the hydrogen atoms one above another. So in order to understand what's going on there, we did quantum chemical calculations. And considering quantum chemical calculations, this part of the curve, so we calculate potential curve by moving two benzenes, one in respect to other. So here they are in the standard geometry, here with the small offset, here they are with the large offset. So this part of the curve was very well known, and I mean, this is the structure with the most stable structure with the offset of 1.5 angstrom. It is this slip parallel geometry that I already showed to you. However, what we did differently than other people, it is that we calculated, when we moved the benzenes, when we changed the offset, at the same time we also changed the normal distance. So differently than other people, we obtained here this plateau, so that at relatively large distances from 4 to 5.5 angstroms, these two benzene molecules have energy of 2 kilocalories per mole. So actually, when we looked at energy, here is 2.8 kilocalories per mole, and here is 2 kilocalories per mole, we can realize that at these large offsets, 70% of energy is preserved. So for these geometries here, these are the geometries that we have at these large offsets, where it looks like benzenes do not overlap, they actually preserve 70% of the strongest interaction between two benzene molecules. So when we put now together data from our calculations and what we found in the Cambridge data bank, we actually see that this maximum in the structures, crystal structures, corresponds to this what we calculated here, that is 2 kilocalories per mole. And then the question is still, I mean, why in the crystal structures two benzenes do not have the most stable geometry, and instead of that have these interactions at large offsets? And the answer is that, the answer is in supramolecular structures. So here, where you have the most stable geometry, this face of the benzene, of this one benzene, and this face of the other benzene are blocked by this benzene-benzene interaction. If we have this interaction at a large offset, then this face is free for additional interactions, and this face is free for additional interactions. And here is one example where it is clearly shown. So this is how these two benzenes overlap with the hydrogen atoms. So in order to overlap in that way, they lose 0.8 kilocalories per mole. However, at the same time, they are able to make here CH-pi interactions, which are at least 2 kilocalories per mole. So they lose 0.8 kilocalories per mole, and they gain twice 2 kilocalories per mole, so they gain 4 kilocalories per mole. So altogether, this supramolecular structure is more stable with the benzenes at large offsets than with the benzenes at small offsets. So, this part about benzene, we can say that benzene interactions are at large offsets, and that actually they are stabilized in the supramolecular structures. Then we wanted to see what's going on, if we can have different kind of influence on aromatic interactions in the crystal structures. So we looked at the heteroatoms in the aromatic ring. We look on the substituents in the aromatic ring. We look also what's going on with aromatic rings that are coordinated to the metal atom. And we also look what's going on, what is the influence of environment, of the surrounding of supramolecular structures on the aromatic interactions. So these are data for two pyridines. So this again, search of the Cambridge database, and this is what we obtained. So we again obtained really large number of interactions at the large offsets. However, here we have some peak also for the interactions at smaller offsets. And here is calculated potential curve for two pyridine molecules. So here is the minimum. We can see here some plateau, when we compare what we obtained from the crystal structures with the calculated potential curve, we see that here where we have this plateau, we have a large number of the structures. However, we also have some peak, a certain number of the structures for the minimum of the calculated at a potential curve. And actually now when we compare the curve for the benzene and data from the crystal structure from the benzene and for the pyridine, we actually see that in the benzene we have the smaller difference between this energy at the large offsets and at the minimum. And we have most of the interactions, I mean, more pronounced tendency to have interactions at large offsets. For the pyridine, this difference is larger. So pyridine is losing more by making interactions at a large offset. So we have also a certain number of structures at a small offset. So considering influence of the heteroatom in the ring, these pyridine-pyridine interactions, they show tendency for the large offsets, but the tendency is smaller than for the benzene-benzene interactions. And the interactions between two pyridines are stronger than interactions between two benzenes. Then considering substituents, we again look at the data from the Cambridge structural database. So we looked for the toluene and for paraphenol. And we again had certain geometric criteria, how we obtained interactions of these two molecules. We looked actually for the stacking interactions of these two molecules. And here we have the possibility that these substituents are oriented in parallel or in anti-parallel way. So for the paraphenol molecules, we actually obtained certain number of structures with a parallel orientation, certain number of structures with anti-parallel orientation. Very interestingly, in between, there are almost no structures with any angle in between parallel and anti-parallel orientation. For the Tylenol molecule, for the toluene molecule, we actually obtained almost exclusively anti-parallel orientation. There is very small number of structures with a parallel orientation. And these are the data from the crystal structures. So this is the offset that we obtained from the crystal structures, this offset here. So for the paraphenol, we see that we have certain number of structures at a small offsets. Again, the large offsets are preferred. For toluene, we actually have similar shape as for benzene, so we don't have the structures with a small offset. And here, if we compare that together with the benzene, we can see that toluene has very similar shape as a benzene, while this paraphenol has somewhat different shape of the diagram. Then we calculated potential curves, again, by changing, by moving the offset. And actually, there are three possibilities. There are three ways how we calculated that. So you can move these rings in this direction, you can move rings in this direction, and we also moved rings in diagonal. So we actually have three curves for these stacking interactions of the phenols. And also phenols can be parallel or anti-parallel, so these are parallel phenols. So for these parallel phenols, this is the starting geometry corresponding to the offset 0. And then we obtain different minima here. So this is geometry of this minimum here. These are geometries for this minima here, and they are the most stable geometries. We have here for these two minima also geometries. For anti-parallel orientation, this is the starting geometry. We have here minimum correspond to this, the geometry corresponding to this minimum here. This geometry correspond to this here. We have more geometries corresponding to different minima. And then when we compare these potential curves for parallel orientations and for anti-parallel orientations, we can see that these potential curves are quite similar. We have some relatively stable structures for parallel orientations, relatively stable structures for anti-parallel orientations, and in the crystal structures we see both parallel and anti-parallel. Considering this certain number of structures at a small offset, actually we have here quite stable geometries, and difference between these energies here and the energies at the large offsets are quite large, so that is the reason why we have them at a small offset. Also, environment can influence that, but I will talk about it later. So this is comparison with the benzene. So here we have larger tendency for the small offsets because this difference is larger, and this black line here is the benzene. So we can see that for the benzene, this difference is much smaller than for the phenol. Considering calculations on toluene interactions, if we compare the curves for the parallel orientation and anti-parallel orientation, we can see that these parallel orientations have less stable structures than anti-parallel orientation, and it is in accordance with what we saw in the crystal structures. So in the crystal structures, we have a preference for the anti-parallel orientation and not for the parallel orientation. These are the minima that we obtained for the parallel orientation. These are the minima that we obtained for anti-parallel. So these two are the most stable geometries. Then we have this other minima here. And again, when we look together, so I already said that we have preference for anti-parallel orientations, and also we have preference for the large offsets, because here we have very stable structures at the large offsets, but we also have relatively stable, so these curves goes also to relatively large offsets, and this is also relatively large offsets. So the difference between the energy here and here is not so large, and actually we have similar shape of the diagram for toluene and for the benzene. The other influence that we looked at was what's going on when the benzene is coordinated. So when the benzene is coordinated to the metal atom, it forms organometallic compounds, and actually it can form these half-sandwich compounds, and it can also form these sandwich compounds. And again, we look in the crystal structures what's going on with the directions of coordinated benzenes. And for the coordinated benzenes, you can see that we obtained certain number of structures at the small offsets. We obtained also certain number of structures at the large offsets. And when we compare half-sandwich compounds and sandwich compounds actually have larger tendency to make interactions at the large offsets in comparison to half-sandwich compounds. We calculate potential curves for sandwich and for half-sandwich compounds, and half-sandwich and sandwich compounds have minimum at the similar place and with the similar energy, so the energy is about 4 kilocalories per mole in both cases. However, they have different shapes of the curves for the large offsets. So here for the sandwich, this difference is relatively small, and here for the half-sandwich compounds, difference between the minimum and the large offset is relatively large. And here we have even the data that at the offset of 5 angstroms, 47% of the energy is preserved. However, for half-sandwich compounds, it is 46%. And it is quite interesting that actually what we saw in the crystal structures, we obtained very similar numbers. So we obtained that 79% of structures is at the large offset for the sandwich compounds, and for half-sandwich it is 46. I think it is just accidentally, but it is interesting that the numbers are quite similar. So again, when we compare what we see in the crystal structures with calculated potential curves, here, because difference is quite small, we have more sandwich compounds at the large offsets. Here, because difference is larger, we have smaller number of half-sandwich compounds at the large offsets. So finally, we can say that this coordination influence the stacking interactions between coordinated benzenes. First, these interactions are stronger than between non-coordinated benzenes. These half-sandwich compounds have a smaller tendency to make the stacking interactions at large offsets, and half-sandwich compounds have even smaller tendency than sandwich compounds. Then we wanted to see what's going on with the influence of the environment on aromatic interactions. And in order to get that, we compared the data from the Cambridge Structural Database and from the Protein Data Bank. And from the Cambridge Structural Database, we analyzed benzene interactions between two benzenes, between two toluene molecules, between two phenols, From the PDB, we had phenylalanine and tyrosine. And you can see we obtained a certain number of structures, certain number of interactions, so large number enough that we can do statistical analysis of the data. And what else we were able to compare, it is that here for the toluene and for the phenylalanine, we actually have the carbon atom substituted on the benzene ring. And here for the paraphenol, we have OH group and some substituent in the para position, and very similar for the tyrosine, we also had the OH group and carbon substituted in para position. So this time we did not look only for the stacking interactions, we actually looked at the angle between these two aromatic rings. So you can have these two aromatic rings being parallel, they can have angle 20, 40, 60, 90, so actually you can have any kind of angle. So practically here we looked what is the tendency for these two rings to be in parallel orientation or in T-shaped orientation or something in between that. And these are the data from the Cambridge structural database for the benzene, phenol, and toluene, and all these three molecules, when they make dimers, they have tendency to make parallel interactions. So in the crystal structures, they are mainly in the parallel orientations. Then we analyzed for each of these angles what is the offset, this offset here, how they are placed one in respect to other. And here we have the presented data for these offsets for the angles up to 60 and angles after the 60, larger than 60 degrees. So these structures to angle up to 60 have tendency to make the interactions at a large offset. And the structures where the angle is larger than 60, they don't show preference for any of the offsets. So they can have different offsets. So these were data for the benzene. So here there were data just for the benzene, and here I have also these diagrams for the toluene and paraphenol, and you can see that they have quite similar shapes. So they have tendency up to angle 60, they have tendency to be at large offsets. After angle 60, they don't show any particular preference for any offset value. So we can say that most of interactions are parallel at large offsets, and we also can say that these shapes are similar for the different molecules. And here are actually these typical geometries. So these are geometries for two benzenes, for two toluene molecules, and for the two phenols. These are the data from protein data bank, data for phenylalanine and tyrosine, and again, we were looking for different angle between these two rings. And as you can see in the protein data bank, they don't have tendency to be parallel. Actually, they can have any of these angles, but they don't show preference to be parallel. So when we look again for these offsets for different angles, we again have these offsets shown up to angle 60 and for the angles larger than 60. And here we see that up to angle 60, they don't want to have small offsets, they don't want to have large offsets, but in between any of these offsets are possible. For the angles which are larger than 60, they have tendency to have small offset values. And it is valid both for phenylalanine and for the tyrosine. There are certain differences, but the shapes of the curves are quite similar. So practically, for this data from the protein data bank, most of interactions are not parallel. If they have a large angle, then they have tendency to small offsets. And shapes are similar, independent of the substituent. And here are two examples of these geometries where actually they are under certain angle, making some kind of CH-pi interactions. So now, when we compare data from the Cambridge database and from the protein data bank, we actually can see that in Cambridge Data Bank, we have parallel interactions, stacking interactions with the large offsets. In the protein data bank, interactions are not parallel and the offsets are small. Then we did also calculations, so we calculated now complete potential surface for two benzene molecules. So we did the calculations for the parallel geometries. It is something that I already showed you, but for the angle of 20, 40, 60, and 90, and these are these curves, and because you cannot see very much, I will restrict this just to 3 curves. So this is the curve for the parallel orientation. This is the curve where 2 rings are under the angle of 60, and this is the curve for when 2 rings are under with the angle of 90. So we can see that these curves have quite different shapes. So for this parallel orientation, that is, I already talked about that, we have here the plateau, we have the minimum, and we have plateau here. For the angle 60, we have the minimum at a smaller offset value, but then we don't have any plateau, and for angle 90, again, we just have increase in the energy. Not only that these 3 shapes are different, but also here where we have parallel and where we have angle of 20 and 40, so parallel orientation and 20 and 40, they have quite similar shapes of the curves here. So all these 3 angles have plateau here. These calculations for the angle 60, they have different shape, and then the 90 has even more different shape. So when we look at this together with the data from the crystal structures, we actually can see that we have different shapes here for the data from the crystal structures, for the offset, for the interactions up to 60, and for the interactions after the 60, for the interactions that have angle larger than 60. So obviously these shapes here are correlated with that potential curves are different for the angles up to 60 and after 60. So this was the benzene, so from the CSD, and this is phenylalanine from the protein data bank. So here we have different shapes, but again, shapes are different for the smaller angles and for the larger angles. So in Cambridge Structural Database, I already talked about that we have these interactions at large offsets because actually we reach this plateau here, and these structures are stabilized because of the surrounding, because of supramolecular structure. So they are not at the minimum here. They are here at this plateau because this difference in energy is relatively small. In protein data bank, they are not parallel, and they have small offsets. So they have actually something like this angle of 60, 90. So they are actually here at the minimum. So what we see in the protein structures are the geometries that are close to this minima here, because here we have a larger difference between the minimum and the geometries at the large offsets. So I'm again repeating that. In Cambridge Structural Database, we have parallel interactions at large offsets. In protein data bank, they are not parallel, they are at small offsets. They are in better agreement with the minima calculated at the potential curves, what practically means that there is a smaller influence of the environment in the proteins than in the crystal structures. So this is what I showed you for the influence of the environment in the crystal structure, why these 2 benzenes prefer to be at a large offset, but it is not the only type of the influence that influences the packing of the benzenes in the crystal Cambridge Structural Database crystal structures. So now, using the same data, we want to compare what's going on if we have the same substituent. So here we have paraphenol and tyrosine, and actually when we compare the shapes of these distributions, they are quite different from the Cambridge database and from the PDB. And also when we compare the data for the toluene and phenylalanine, again, these shapes of the diagram are quite different, what practically means that environment has stronger influence on the aromatic interactions than substituents on the rings. So the last thing that I want to talk about are aromatic-aromatic interactions and aromatic-aliphatic interaction, actually the comparison of aromatic-aromatic and aromatic-aliphatic interactions. So this experimental data for vaporization energies for benzene, liquid benzene and liquid cyclohexane. So liquid benzene and liquid cyclohexane have the same vaporization energy, 8 kilocalories per mole. Then the question is what we would have if we have the benzene and cyclohexane. I don't know about this experimental data, but actually we have the calculations. So for interaction between two benzenes or between two cyclohexanes, calculated interaction energies are almost the same, and it is in agreement with this experimental data that experimentally the vaporization energies are the same. What is quite interesting, it is that the interaction between benzene and cyclohexane is actually stronger. It is, these energies are about 2.8 kilocalories per mole. This is 3.27 kilocalories per mole. So benzene actually interacts stronger with cyclohexane than with another benzene. And then if that is the case, if benzene makes, if aromatic-aliphatic interactions are stronger than aromatic-aromatic interactions, why do we have impression that aromatic-aromatic interactions are somehow special and exist in so many systems, and we have impression that they stabilize different systems if aromatic-aliphatic interactions are actually stronger? So that is the answer that we wanted to answer. And before we try to answer that question, a number of people also tried to answer the same question. So people did this SAPT analysis, this contribution of dispersion, electrostatic, and so on the interactions between two cyclohexanes, cyclohexane benzene, and benzene-benzene. And they realized that electrostatic is the strongest for the cyclohexane benzene, and it makes cyclohexane benzene more stable than benzene-benzene. Then people try to explain that also considering different size of the system. So if you have just one ring, and you have aromatic molecules, you have aliphatic molecules, if you increase the size of the system, and they analyze all this in details theoretically, and so the final conclusions are that if you have larger aromatic systems, like several rings together, then these larger aromatic complexes have advantage, and they are more stable than aliphatic or aliphatic aromatic complexes because they have larger dispersion, smaller repulsion, shorter intermolecular distances, and because of that increased electrostatic and dispersion contribution. But they were talking about larger aromatic systems. So the conclusion was that larger aromatic systems have advantage to aromatic-aliphatic system. But the question is still, what about small rings? What about benzene and phenylalanine if benzene has some advantage to benzene cyclohexane, or it does not have any advantage? So then we did a Cambridge database search for the interactions between benzene and cyclohexane. Actually, this was cyclohexyl phenyl in order to find a enough large number of interactions that we can analyze that. And so you can see that if we have the benzene and cyclohexane, then we have a quite large number of interactions at the small offsets, and not so significant number of interactions at the large offsets. Then we calculated potential curve for the benzene cyclohexane. No, I'm sorry. Yeah. We calculated potential curve for the benzene cyclohexane, and this is the minimum here. It is, again, at 1.5 angstroms, and this is the geometry, and these are the geometries at the large offsets, and this geometry is 3.27 kilocalories per mole, and at the large offset energy is relatively small. It is 1.2 kilocalories per mole, and actually we have that only 38% of the energy is preserved at the large offset. And then when we compare that with the data from the data bank, from the crystal structures, we see that we have here a relatively large number of structures since this difference in energy is relatively large. And when we put together cyclohexane benzene, and this curve is for the benzene, we can see why cyclohexane, because of this larger difference, has a larger number of structures at a small offset than benzene. So, energy of benzene dimer is 2.84 kilocalories per mole. Energy of cyclohexane benzene is 3.27 kilocalories per mole. However, area for benzene stacking interactions is larger than the area for cyclohexane benzene. So this is the figure that is very, very interesting. So we put here in the blue interactions which are stronger than 2 kilocalories per mole. So for two benzenes, area in which interaction is stronger than 2 kilocalories per mole is really large than the area for cyclohexane benzene. So cyclohexane benzene can make stronger interactions, but in very small area. For benzene, this area in which they can recognize each other is much larger. So it is probably the reason that aromatic rings can recognize each other at a large offsets, and then they can attract each other to whatever is the favorite geometry. So the conclusions. We use this combined analysis of the data in the crystal structures and quantum chemical calculations. CSD benzene interactions, stacking interactions are mainly at the large offsets. It is because this potential surface potential curves show small difference between the energy at the minima and energy at the large offsets. And this supramolecular structure actually stabilizes these aromatic interactions at the large offsets. If we consider different influences, if we have the heteroatom makes interactions stronger and less tendency for the interactions at large offsets. If we have substituents in the aromatic rings, they again make interactions stronger. However, they almost do not influence that if interactions are going to be at the large offsets. They are quite similar as for non-substituted benzene. If a benzene ring is coordinated, then it has significantly stronger interactions. However, it has less tendency to make interactions at large offsets, and this tendency is even smaller for the half-sandwich than for sandwich compounds. And then we can say that environment has strong influence on the aromatic interactions, and this influence is stronger than the influence of substituents. And then finally, this about aromatic aliphatic interactions, that probably the advantage of aromatic interaction is that they can make interactions at very, very large offsets. So the large area is actually capable of attracting two rings. So finally, I hope that I convinced you that our methodology is quite successful in getting data about aromatic interactions. Thank you.
Thank you, Snezhana, for the nice talk and yet very general. We are on dimer, so there are a few questions. Please, thank you.
Thank you. I just want to make sure, if you have aromatic, but many of them, will then you have also this slight shift, like the 1.5 angstroms or whatever? Let's talk about a big stack of aromatic.
Okay.
And then I'm asking about this slight shift.
Offset.
Offset.
What will be the offset?
Yes, the offset, sorry.
Mm-hmm. Yeah, they are probably shifted a little bit because it is favored by electrostatic interactions. Yeah, they probably will not stack exactly one above another. They will not make sandwich geometry. I mean, I had the data for the naphthalene where also this displaced geometry is more stable than sandwich geometry.
So the collective effect will not change this offset. That's what you mean?
Probably not.
Okay. Thanks.
Yeah, I mean, if you're asking if you will have this attraction at a large offset also for the, if you have more, if there are more rings, is that the question? Yeah, I mean, you will have this. We had some data for the naphthalene. So yeah, you again have at large offset this attraction. Yeah.
Yeah, please. Sorry.
I've got a couple of questions, actually. One's really quick. Is there a co-crystal of benzene and cyclohexane?
Oh, I'm not sure.
Okay, right. And I'm not aware of that.
I'm sorry that I don't know that, but I'm just realizing that I don't know that.
Okay.
Because we looked for all possible interactions, so I'm really not sure.
Okay. My main question was the influence of metals. So you showed that the metal increased the strength of the stacking interaction between the two benzenes, and I wondered why that was. Is it simply because the metal complexes are bigger and therefore more polarizable, and you get a bigger dispersion interaction, or is the metal actually doing something? Did you, for example, try changing the identity of the metal in your calculations?
Yeah, both answers are yes. So dispersion is larger because the metal is there, so the system is larger, so dispersion is larger. However, by coordinating to that is quite interesting. By coordinating to the metal, electrostatic potential of the aromatic rings can change completely. So we just published a paper where in the half sandwich compounds, benzene ring is completely positive. There is no negative area on benzene ring when it is coordinated. And then benzene ring is pure benzene, I mean, not pure, coordinated benzene ring in half sandwich compounds is capable of making anion pi interactions. So by coordinating, these aromatic rings are getting quite different. Then it depends very much if it is sandwich compounds or half sandwich compounds. It seems that it is not so crucial what is the metal, but it is more crucial what are other ligands in the complex. So other ligands actually can because they can move electron density towards themselves or not, and they can change a lot electrostatic potential of the benzene, coordinated benzene.
Okay, thank you very much.
Thank you.
I wish to ask you, you talk about residua of amino acids that are non-polar with benzene rings and even pretty polarizable phenol type. And also at the beginning and at the end of the lecture mentioned the influence of environment to interaction. Having in mind that you did a survey in protein database, I'm eager for getting know the methodology, because in proteins, even in peptides, the amino acids residue depend on the sequences, how they are connected, linked one to another. So I consider that neighboring amino acids residual influence one to another, especially forming that tax of amino acids residual, also forming one kind of microenvironments. Also, you mentioned at the beginning and to the end polar type of amino acids, like as indole rings in tryptophan, and also it's a pretty problem with imidazole in histidine amino acids, especially when they are linked by peptides bonds as a tax of histidine, and it is a very strong environment, either basic or acidic also for tryptophan. And from that terms, I'm consider that it is pretty strong influence of the microenvironments. From the other side, depend of the system, how it is protein crystallize in which kind of solvent, and in that solvent the heavy metals ions also influence the non-covalent interaction and conformation of the protein structure. Have you did any survey in this polarized type of?
Sorry, I invite you to shrink a bit the time because we are already late. So
thank you.
I cannot take more questions actually.
I mean, you are right. There is. I mean, I'm not saying that there is no any influence of the environment in the proteins, especially about these polarizable molecules. We did not look at them. We just looked at the tyrosine and phenylalanine. But you have less influence than in the crystal structures. That is what I want to say. That there is less influence.
Yes, sorry, there were two more questions. You can discuss over the poster session. We need to go on. I'm sorry. Thank you once again. Thank you, Snezhana. We now move to the last two talks of this session. The first one is from Lyubcho Peyov from the local University of St. Cyril and Methodius in Skopje, I guess. Is it? Yeah. Which will talk about structural and vibrational properties of bent molecular crystals.
Okay, hello everyone. First of all, I would like to thank the Scientific Advisory Board of this conference, and also the chairs and co-chairs who obviously had their contribution to all that, for their kind invitation. And it's indeed a great pleasure and honor for me to have the opportunity to speak in front of this audience as someone who is coming from a bit different field, but who had tried to see what can be done with some of the methods of computational theoretical chemical physics in this field. As you can see from the title of my talk, I'm an expert in coining long titles, but the comforting thing is that I'm not the only one if you go through the list of lectures, so that's a bit comforting indeed. And to make the long story short, I'm going to talk about the bent crystals and what can we see about them, about their structure, applying experimental methods of infrared, micro-infrared spectroscopy, and how can we, maybe it's too pretentious to say predict, but to rationalize the experimental spectroscopic data with the aid of computational methods. And just in case I do not manage to convince you that the approach is really useful and what's this all about, I will advise after the lecture to go to a different expert in the field who usually convinces me what's that all about. But okay, let's get to the point. It is well known, and we have heard on several occasions here, that there are certain crystals that bend without fracturing. Crystals bend when they are subjected to localized force or pressure, or it can be even illumination by light, usually from the UV or visible spectral regions. There are certain, I would call them extreme examples of some perhalogenated benzenes, for example, hexachlorobenzene, the system that I will focus on in my talk, that can plastically be bent to practically 360 degrees. And there have been many studies in the field since the first discovery of the phenomenon by Reed, and many groups have worked in the field, and Professor Panchanumov's group at Smart Materials Lab at NYU is one of the groups that made certain fundamental contributions to the field, and that's how I got involved, actually, with the computational methods in the field. So you can see here a very pictorial example taken at the Smart Materials Lab, along with the crystal structure of hexachlorobenzene, which can be really very extremely bent plastically. Yeah, but if we consider malleability of the crystals, of molecular crystals, it sounds quite counterintuitive. We wouldn't expect at first sight that phenomenon. We would expect molecular crystals to be, first of all, brittle. But it's a very, very brilliant and drastic example of how weak non-covalent intermolecular interaction can act in a cooperative manner in order to maintain the crystal integrity. And if one looks at this problem from a broader perspective, from the viewpoint of the mechanical properties of these 3D periodic objects, molecular crystals, this is what makes them in a sense, closer with their properties to soft materials or even inorganic materials such as metals and alloys. However, if you want to go into details about which perturbations have been imposed on the crystal by bending, it's far from an easy task. It is said in the literature that it can be even an intractable problem, because the diffraction methods that are widely used within this community usually are heavily affected by the bending, so that the diffraction images are blurred due to the distribution of different lattice geometries and orientations and all that. So these widely used methods do not appear to be very suitable for this purpose. So several groups have taken the advantage of other spectroscopic techniques, such as, for example, infrared spectroscopy, the micro-IR variant with synchrotron radiation, and the results seem to be very promising. However, when you get a spectral picture of some not so straightforwardly explainable phenomenon, you need a tool to, in a sense, disentangle the relations that are inherent between the perturbations induced by bending and molecular vibrations. So, can something be done? Yes, a lot has already been done by Pancha's group, and they were able even to explain why the bending occurs when the force acts normal to some of the crystal planes, and it doesn't occur when it acts along some other crystal planes. But still, the application of this standard, I would call it reasoning borrowed from mechanical engineering to this problem, is still not, I would call it atomistic. So what we try to do is to shed some more lights on their data. So the basic idea behind our approach is the following. We can do, of course, periodic DFT calculations, and I have to be very careful after yesterday's Aurora talk, because I couldn't agree more on some aspects that she mentioned, that whenever you use DFT, you have to be very careful. I can assure you about that from my personal experience. So what we did in our study is we tried a wide range of different periodic DFT approaches with different functionals, with different fundamental approaches such as, for example, the first one is the approach where crystalline orbitals are expressed as linear combinations of block functions which are defined in terms of local functions. So atom-centered basis sets, like the methodology implemented in the crystal series of programs. And in parallel, we have tested the pseudo-potential plane waves theory, like implemented in the custom series of codes. So I certainly got an impression that we spent much more time on testing than on productive calculations. However, we found out that there is a range of different DFT methodologies, both dispersion-corrected and those which are based on using, I would say, functionals with a correct asymptotic behavior, which finally, again, reduces to correct description of the long-range and dispersion interactions. And, of course, by choosing appropriate DFT methodology, we can do the following. We can fix the unit cell parameters at a range of different values, and then apply a geometry optimization algorithm in order to optimize atomic position, and then compute the dynamics metrics at the gamma point, and compute the vibrational frequencies. And if we do this for sufficiently wide interval in all of the relevant lattice parameters, for example, A, B, C, and the angle beta in the case of hexachlorobenzene, we can do several things. If we want to focus on the dependence of frequency on the deviations of the lattice parameters induced by bending, we can perform a standard Taylor series expansion and then calculate all these derivatives, for example, by interpolation, successive interpolation differentiation techniques. But, and we had done that for the purpose that will become clearer later. But what we wanted to do is to propose a rather general and flexible theoretical basis, which would account not only for the position of the bend peaks, but also for the shape, for the overall bend shape. So let us introduce a generalized coordinate Q, which is in a sense of a 4-vector containing the relevant lattice parameters. Then let us, for the beginning, consider just a single normal mode of the crystal, which is characterized by a bend-shaped function denoted by f with the index j, referring to the particular normal mode. Of course, since it is a bend-shaped function, it depends on the frequency, or maybe what is more common in the spectroscopic community, wave number of the incident light. And it is also dependent parametrically on this generalized coordinate Q. So, we have, in the case of straight crystal, of a non-perturbed crystal, some inherent bend-shaped function which we can derive from the experimental spectra of the straight crystals. But then, we have to find the dependence which is here introduced as a parametrical dependence on this coordinate Q, and consider the distribution function, the probability distribution function of all the possible distortions which are induced by bending of the crystal. And this is the probability distribution function, the normalized one that we introduce here. So, what we experimentally observe in the spectrum of the bent crystal is practically a convolution of this straight crystal jth mode bend-shaped function and the probability distribution functions of all the perturbations introduced by the bending. So it's a rather conceptual theory. Of course, now you can describe the bend-shaped functions by different analytical functions, such as, for example, Gaussian function, or even Cauchy function, or linear combinations of Gaussian and Cauchy, or even maybe a convolution of Gaussian and Cauchy, which is the Voigt profile, which has been much used in the context of spectroscopy. So, of course, here we have certain parameters which contain certain inherent properties of the jade mode for the unbent crystal, for the straight crystal. And all the solid-state physics is phenomenologically, in a sense, gathered here. So it is contained in this parameter. If we want further to consider different mechanisms of broadening of bands and all the other stuff, then we can incorporate them here. So, of course, the overall spectrum is a sum of all the contributions of all the relevant normal modes, so it is a sum over these convolutions. If we fit the band-shaped function of a jth mode of each of the modes that we have considered in our study, then we can adjust this coefficient and even maybe this sigma in principle. What we did in our study was to just fix this sigma and play around with aj, so that the intensity waving is automatically included in our model. We don't have to additionally introduce the intensity waving. So we have a simple, relatively simple conceptual theory in which the spectrum of a bent crystal is a sum of these convolutions in which the band-shaped function determines the general trend, which is for each particular considered mode directed by it, and it includes the inherent effects of lattice distortion on the intramolecular frequencies, which are included via this parameter here. And then we have the distribution of lattice distortions, which are along the path of the infrared beam. Maybe in certain cases they reflect correctly the overall distortion distribution throughout the whole crystal, but that would be just for certain particular cases. Yeah, of course, we have to be sure first that our DFT methods function rather well for straight crystal, and we focus on 4 particular modes, 2 of which are most precisely described as CC, stretching vibrations, with the BU symmetry, and the rest 2 are the stretching CL BU modes again. We have chosen those particular modes because they give the most intensive bands in the spectra, and so you can see that the best method that we have chosen is in rather good agreement with the experimental data from the studies published by Pancha's group and with the other literature data. Of course, here we work in the harmonic approximation, but it is rather well satisfied for such modes. We don't have here live atoms, so we don't have some large amplitude motions, etc. Although the method could be easily extended accounting for the unharmonicity. That's a certain thing in which I have quite a lot of experience. So, since this is just a 20-minute talk, I will just focus on the main points and our main conclusions. So I'm going to present just a part of our simulation data. What we have done first is to consider uniform cell deformation in the sense of expansion and contraction, where we have simultaneously enlarged the values of the 3 unit cell parameters, and we have simultaneously compressed them and see how it affected the spectra. Then we considered a wide range of non-uniform deformations, some of which have been omitted in this presentation. So here are the results. Here we have the general trends imposed by the 2, exhibited by the 2 carbon-carbon stretching modes and carbon-chlorine stretching modes when the lattice parameters are simultaneously changed. So the plus direction is the direction of expansion, and the minus sign refers to the direction of contraction. As we can see here, from the insets which show the derivatives, the first derivatives for the red curves, for the simplicity of presentation, the contraction tends to affect more significantly the vibrations, and it causes the blue shift, while the lattice expansion introduces a red shift, and the derivative is a bit smaller, significantly smaller, I would say, than in the case of this region. So it is relatively easy to propose a simple explanation of these trends. When you shrink the lattice, you bring the molecules closer together, so you impose a confinement on each of the oscillators, and when an oscillator is confined, even within the harmonic oscillator approximation, the force constant changes in such a way that the frequency goes up. It's a known so-called wall effect in the intermolecular interactions. So the same trend is also in the case of CCl modes. The corresponding trends in the equilibrium CC and CCl distances follows the trend. Of course, when the CC distances enlarge, the frequencies go down, and the same for the CCl distances. On the other hand, there is a pretty much linear relationship between the frequency and the equilibrium distance for both types of the oscillators, as would be expected from the simple quantum mechanical theory of harmonic oscillations. So we then proceeded to consider some non-uniform deformations in which we have simultaneously change either A and B parameters, A and C, or B and C parameters. And you can see here the so-called response surfaces to these perturbations. And we can see that the vibrations are most sensitive to the changes in A and B parameters. As you can see from the crystalline structure viewed from the C-axis, it is exactly those two lattice parameters that would bring the molecules within the crystal in the closest constant upon shrinking. So this significant increase, blue shift in frequencies, is self-understood. On the right-hand side of this figure, you can see the contour plots of these curves. So, these are the similar trends observed in the case of CCl modes, and the trends are basically the same. We can even say that the carbon-chlorine stretching modes show a greater sensitivity to the shrinkage of the lattice vibrations. And so, if we want here to treat the delta nu values, we can simply either use this simple Taylor-like expansion, or we could fit the complete surface and then introduce these dependence in our model band shape function. When it comes to the angle dependencies, we found out that the frequencies are less sensitive to the changes in the angle beta, although it is not easy to provide a straightforward explanation of this phenomenon, because change in the angle beta introduces quite non-uniform distortions of the lattice. So you cannot simply speak about the wall effect or simple confinement of the motions. So let us just take a brief look at the effect that compression and expansion along either one single or combinations of two lattice parameters or all the three lattice parameters, we can see that compression has much significant effect than the expansion. And the effect is blue shift in the case of compression and red shift in the case of expansion. And it holds for both types of these modes. So let's see about the experimental data, how it all fits. Obviously, I cannot go into details, but what we have done is we had taken careful look of the experimental data. We did the fitting, both with simple Gaussian melioration functions and with our approach, and the general spectral picture is in accordance with our model. So we see the greater tendency towards blue shift with the small side bands which are right shifted. So, yes, we can basically propose such generalized theory which reduces to the theory of single mode absorption if you have a distribution function of a direct type. So just a few more words and I will conclude. The main issue here is also, can we do it? Can we do everything of this backwards? Can we address the inverse problem? When we have the spectrum, can we get the probability distribution function? That's the main question, actually. So, yes, we can. The answer is we can, because this equation is a Fredholm integral equation of the first type. And we can solve it under specific circumstances by Fourier transforming of the experimentally measured spectrum or a band profile for a single mode of the band crystal. And then by inverse Fourier transformation of this ratio, we could, in principle, I would say, get again the probability distribution function. So some of the results were already published from this study, and okay, I'm sorry if I went a bit over my time. So thank you for your attention.
Thank you for this beautiful talk connecting theory and experiment. Are there questions? Yes, I see one, at least.
Did you look at the second order, like see if you get mixing of modes?
That's what we are looking at now, actually, because we worked in a harmonic approximation up to this point. But yes, we are now considering the inherent coupling of the modes in the case of straight crystal and the possible couplings that could be introduced by bending, for example, by a symmetry reduce. Yeah, and that's a very interesting point, of course. Going beyond harmonic approximation is always a challenge. Yeah.
Okay, as I don't see other questions and we are a bit late, maybe you can answer to more questions in the poster session. And so I invite now, thank you again, first of all. I invite now the last speaker of the session, Marta Dudek from the Polish Academy of Science, which will talk about the relation between conformation and crystal structure prediction.
So thank you for the kind introduction, and I'm really, really happy to be here and to present some of the results from our studies. So my group is partly interested, so part of our research is focused on using so-called NMR crystallography approach to determine crystal structures in the cases in which we cannot use single crystal X-ray diffraction, mainly because our crystals are too small. Even though we can use even smaller crystals, we do not always have an opportunity to obtain sufficient crystals for the technique. What we can do in such cases, we can use solid-state NMR combined with powder X-ray diffraction and with DFT calculations to obtain crystal models corresponding to the experimental crystal structure. And I'm going to show you today a few examples from our laboratory in which we used that kind of approach combined with crystal structure prediction. And today I will mostly focus on two cases. One is furazidine, which is urinary tract infection drug, and the other one is anti-inflammatory drug meloxicam. So I will start with a very, very brief introduction to NMR crystallography. So in principle, we use solid-state NMR data to extract experiments, to extract as many structural constraints as we can, so as many information about the model we are studying. And usually we are able to say quite a bit about the system. We are able to say about how many molecules in a asymmetric unit cell are there in a structure. If we are lucky, we can even extract some atom-atom distances, so actually nucleus-nucleus distances in a crystal. The problem, however, with NMR crystallography is with solid-state NMR, actually, is that many of the spectra are overcrowded because you have very broad resonances, even though we are spinning our samples under very fast spinning. We are not able to average out all the interactions that are present in a solid. So we have a problem of signal overlap, but we also have a problem of differentiating between inter and intramolecular interactions, because you do not know a priori whether the interaction you observe in a spectrum originates from molecular conformation or from the fact that another molecule in a crystal is close to the molecule you are looking at. The other thing is that NMR do not say us anything about the long-range order. It says about local structure around a molecule. But to have an insight into long-range order, you need other techniques. That is why we use powder X-ray diffraction. And those two techniques combined, in principle, could deliver enough information to build structural model. Then you can refine that kind of model with computational methods and calculate NMR parameters, compare with the experiment, and if you have a sufficiently good agreement, you found your structure. However, it is often the case that we are not able to build viable structural model. And fortunately, we have then crystal structure prediction calculations, which in principle do not need any experimental data to be able to deliver some structural models. So the way we do crystal structure prediction is we use Global Lattice Energy Explorer, which is based on quasi-random sampling, which is a code kindly provided to us by Graeme. The main thing which will be important for my talk today is that this method uses mostly, it is possible to use some flexibility, but mostly we use rigid entities. So we treat molecules as rigid at the stage of crystal generation process. And because of that, we want our molecule that we use in crystal structure prediction to be as close to the one actually present in a solid as possible. So typically, in our protocol, we first use conformational search and produce all viable conformations. Then each of the conformations separately is used to build crystal structures, to generate crystal structures using Global Lattice Energy Explorer. And then those crystal structures are optimized in respect to intermolecular energy. And up to this stage, we treat the molecules as rigid entities. And only at the last stage, we take the lowest energy structures and allow for full flexibility and calculate their, or optimize their geometry at the FTD level of theory. So And by doing that, we hope that intermolecular interaction in a crystal will act as like forces in a real crystallization experiment and will like distort a bit this molecular conformation from its gas phase minimum. So the beautiful thing about crystal structure prediction is that you can do it for any molecule you like. You can just make a 2D model, make the 3D model out of that, and then do crystal structure prediction. And in reasonably short time, you are able to generate thousands, even hundreds of thousands of crystal structures, which can be, of which one can be your experimentally observed crystal structure. On the minus side, there are a lot of possibilities. So there is like a vast space to be searched through. And also, as I mentioned, we use rigid entities, which might be a bit problematic. Despite that, this approach works amazingly well for some systems. And the first system I'm going to show you is furazidine, for which there were two polymorphic forms which were disclosed in a patent, but they were characterized only by their powder X-ray diffraction data. So when we obtained those two polymorphic forms, we first extracted some constraints from powder X-ray diffraction in terms of space groups. We also did conformational search, which yielded 8 stable conformation. And then we did solid-state NMR spectra. And as you can immediately see, in form 1, many of the resonances are splitted. And this means that we have actually Z'2 polymorph, which may or may not be problematic. So then we did more advanced solid-state NMR experiment to extract some structural constraints. And unfortunately, we succeeded only for furazidine form 2, so the simpler one. And this was done by using this single interaction here, which is actually a close proximity between C-gamma proton and H5 prime hydrogen. And this allowed us to narrow down the number of conformations to 4. But we were not able to do that for this more difficult polymorph. And it meant that we have to consider 8 conformation. And because this is Z'2, so every combination have to be accounted for. So this yielded 33 independent crystal structure prediction searches. There was one actual valid structural constraint, which we were able to obtain from proton-proton solid-state NMR spectra, and this was NH proximity between molecules A and B of furazidine. So this means that they probably interact forming dimer here or here. This is the crystal energy landscape of form 2 of furazidine. So this means this is the plot of energy versus density, and each point corresponds to a different crystal structure. So typically we look at the lowest energy region of such landscape, 10 or 50 kilojoules per mole, and we calculate those structures using DFTD, and we calculate NMR parameters, which we then compare to the experimental data. And after that, you look at all the structures that give reasonable agreement with your experimental data. And we use well-established in the literature cutoff values. These are this half ppm for proton NMR data and 3 ppm for carbon NMR data. And as you can see here, there are 4 structures which fall below this cutoff for proton data, and out of those 4, only 1 falls also below the cutoff value for carbon-13 NMR data, and this unambiguously indicate the correct crystal structure, which of course was then confirmed by comparing powder X-ray diffraction experiment. So the case of form 1 which is Z prime 2, was a little bit more complicated. First of all, because there is a larger number of structures that have to be geometry optimized, but also because if you look at the agreement of in terms of proton data, you can see that there are 3 structures, and out of those 3 structures, there are 2 which also give good agreement with carbon NMR data. So when we looked at those structures, not surprisingly, we saw that they are built by the same conformation, and they are actually pretty similar. They both fulfilled our only experimentally derived constraint, structural constraint, and they pretty much had similar hydrogen bonding patterns. So what do you do in that kind of situation? Where first of all you look at the energy, so we tend to assume that the lower energy structure will be the one that you have, but then also at powder X-ray diffraction pattern, and in this case it indeed turned out that this lowest energy structure is the one that is observed experimentally. We also did similar searches. I will show this very, very briefly for cyclic dipeptide, for which we obtained 4 polymorphs. And we were lucky enough that after registering proton NMR spectra, we were immediately able to say what is the conformation of this molecule inside the crystal. And this is because you see a very peculiar chemical shift, which was negative, so below zero, which is very uncommon for molecular crystals. And this means, this is only one possibility explaining this observation. This means that the proton which yields this resonance is in a shielding cone of aromatic ring, and this immediately showed us what is the conformation of this molecule inside the crystal. And indeed, we were able to obtain 2 structural models of 2 of those systems, one of which was a monohydrate. So going back to, going further to the second main story of meloxicam, this was kind of started as a very simple project. So we thought, okay, we will obtain 3 polymorphs, which were disclosed in the patent, but again, not characterized structurally. And we will use NMR crystallography, establish their structure, and we had some other plans also for this molecule. But it turned out that it is not that simple. So when you look at the patent and read the actual experimental procedure to crystallize those 3 polymorphs, you will see that there is a very simple description on what should you do. So every student should be able to repeat this process. So 3 researchers in our laboratory did that, repeatedly did that, and randomly obtained either form 1, which was already known, or a monohydrate, so form 4, which was also already known. This kind of confused us, as we were not at all able to obtain the elusive 3 forms of meloxicam. So then we looked at the literature, and it turned out that we were not the only ones. So someone before us also reported failed attempts to obtain those polymorphs of meloxicam. So what we did some preliminary crystal structure prediction calculations in order to see whether there will be some prevailing hydrogen bonding pattern, which is different from the one that is observed experimentally. And it turned out that, so the majority of crystal structures are formed by dimers found in form 1. But there were some low-density structures which showed different hydrogen bonding pattern. And again, we looked into the literature and found this excellent paper in which the authors used nitrogen-containing heterocycles to direct crystallization towards like other crystallization routes. And indeed, when we used that kind of additives in our crystallization, we were able to obtain our 3 elusive forms of meloxicam. So then we used solid-state NMR and immediately decided that we won't do crystal structure prediction for polymorph 4-5 because this is Z prime 6 polymorph. This is seen here. We thought, okay, we can forget about it. So if anyone from electron diffraction community wants to give it a go, I will be more than happy to provide this polymorph for you. But form 2 and form 3 of meloxicam looked really nice. So they were both Z prime 2 polymorphs, but both molecules seem to be very similar. And you can see that because only some resonances are doubled in the carbon-13 NMR, solid-state NMR spectrum. And also, when we looked at chemical shifts of all the resonances, they were pretty similar. So this means that they also show similar hydrogen bonding pattern, which we kind of expected also. So when we did Z'2 crystal structure prediction search, we found without any problems form 2 of meloxicam, yielding excellent agreement with the experiment. But what about form 3? It is supposed to have the same conformation, or at least very similar, similar hydrogen bonding pattern. We searched through many different space groups. So what is going on? We tried to figure out doing more and more crystal structure prediction, but failed every time. Fortunately, one of my colleagues did not stop attempts to obtain to do crystallization of of this form. And in one crystallization, we observed some forms which were morphologically a bit different than form 1, with which it concomitantly crystallized. And we were able to do single crystal X-ray diffraction experiment. And what we found was a structure which indeed fulfilled all the conditions that we derived from our experiment. So what is going on? Is our method not working? Why we did not find this crystal structure in crystal structure prediction search? So when we calculated this structure, it turned out that it should be somewhere here on the landscape, but it's not. We first looked at conformations of the two molecules which are present in this form. And as you can see, they do not differ significantly from the conformation we tried. So actually, that kind of differences, as you can see, in terms of atomic positions, are usually totally negligible. So we can do crystal structure prediction for that kind of conformation, and we should find our polymorph. But we did not. So maybe our method is not working correctly. So what we did to check our methods, we took experimental conformers to generate crystal structure, and indeed, there you go. There is form 3 of meloxicam on the landscape where it should be. So we decided to take a more closer look into that, and we even did crystal structure prediction calculations taking two molecules A from the experimental polymorphic form. And molecule A and molecule B differs in terms of conformation 0.09 angstroms. And despite this, we were not able to find experimental crystal structure. So we found this structure only when taking exactly experimental conformations. So finally, we asked also Isaac Zagden from Imperial College of London to do flexible crystal structure prediction search to see whether we will be able, maybe when we include flexibility at the stage of generation of crystal structures, we will be able to find our experimental crystal structure. But the result he obtained using crystal predictor were exactly the same as ours. So including flexibility, the way in which crystal predictor does, did not help in any way. And funnily enough, we also find similar case for furazidine form 3. So actually, after publishing our paper on furazidine polymorphs, Agris Berzins, who is from University of Latvia, who is also here at the conference, asked us to, told us that he found experimentally a new polymorphic form of furazidine and asked us whether we found it in our crystal structure prediction search. And it turned out that we didn't, despite searching through the correct crystal structure, and despite the fact that here is an overlay of experimental polymorph, experimental conformation, and the one that we tried in our crystal structure prediction search. So as you can see visibly, there are no differences. There were some tiny, tiny differences. And we are still not sure why this is the case, that we cannot find that kind of differences causes such huge differences in what we can find. But what is clear to us is that this computational elusiveness of meloxicam can give us a hint about experimental elusiveness, so why it is so hard to actually obtain this polymorph. So first of all, we suspect that it lies in very shallow local minimum, so that it pretty easily converts to form 1. And secondly, both of these molecules, so both meloxicam and furazidine, are basically planar conformations in their gas phase minima. And in order to form the dimers needed to form form 3 of both molecules, they have to ever so tiny be distorted from this planarity, which is very, very minor change, but apparently a very significant one. So with this, I would like to thank all the wonderful people I have worked with, in particular Professor Graeme, who introduced me to the beautiful field of crystal structure prediction. And thank you for your kind attention. Thank you.
Thank you for the beautiful talk. We have time for, unfortunately, one question only, or maybe 2 shorts, if there are any. No? Then I would... yes, there is one.
Thank you for the beautiful talk. I was wondering for I think the last molecule that you crystallized with additives.
Yes.
So how did you do it? Was in sublimation or in solution?
Yes, it was in solution, and this is a kind of different approach because usually you use like tiny amounts of additives, and in this case we used 1-to-1 molar ratio.
Okay.
But those additives are very easy to they are actually not present in the final sample because they have very low, they vaporized at low temperature.
Okay.
So you can obtain pure polymorphs.
Thank you.
Thank you. There is one request, but the organizer is a very short, I'm sure it will be a very short question, so please.
Thank you, Marta, for this beautiful talk. I think it connects very well with our talk on flexibility, and the dependence between flexibility and crystal structure. My question is, I couldn't understand exactly why was form 3 very difficult to predict by computational method. Was it too similar with the other forms, or there's some other reasons?
Clearly, this is conformational issue, so there is a huge, the conformation of experimental form is very similar to that which we tried in our search. And despite that, we did not find it. But it's not like this is a single parameter which differs the two conformations, so like a torsion angle, which you can like change easily, but the many tiny changes which result in this molecule being a little bit twisted. So it is conformational issue, and as Aurora told us yesterday, this is like extremely important. And in our case, it was like more than we have ever expected.
Thank you, excellent. So we thanks again all the speakers and Marta for this nice presentation. The poster sessions start straight away, as far as I know, so you can move there. And if the speaker of this session wants to take a picture, they could come to the stage, the one of the afternoon. Otherwise, it's not necessary, but thank you.
Yep.